Good morning and welcome back to the auditorium. The talk is about to start, so please take your seat. And if you want, there are many seats available in the front area.
Hi, good morning. Welcome back to the day 2 of the KAUST Research Open Week. For all the external guests, hopefully you have enjoyed a stay at KAUST in this very wonderful weather this week. And thank you for coming for this very exciting keynote on the future of semiconductors. My name is Xiaohang. I'm an associate professor of electrical and computer engineering of the SEMC division at KAUST. So, as you know, the semiconductor technology is arguably the most important foundation of the modern society, as well as the third and fourth industrial revolutions. And it is also a great contributor to the sustainability as well. In the past decades, the semiconductor technology has reduced the energy consumption per computing process by many orders of magnitude. And at KAUST, the semiconductor research is a robust and active area as well. We have dozens of faculties and hundreds of students and researchers working on materials, devices, circuits, and systems related to the semiconductor technologies. However, the semiconductor technology industry is having a severe problem these days. First is the supply chain issue. As you know, there's a global semiconductor chip shortage that has impacted the life and livelihood of billions of people around the world. And also, the scaling of transistor, or the so-called tracing of the Moore's law, has slowed down dramatically due to the limitation imposed by quantum mechanics and the processing technologies. So in this uncertain period, we need leading expert and visionary to point out future direction for us. So who else is better than our guest today, Professor Aaron Thim? Aaron is the Dean of Engineering at National University of Singapore. And he received his bachelor and PhD degrees from University of Illinois Urbana-Champaign in the United States, where he was awarded the Greg Stillman Semiconductor Research Award for his PhD thesis. And prior to joining the NUS, so he has served as a leading positions in many institutes and companies. And most notably, he was the Vice President of Logic Technologies and a Director of Logic Device Research at IMEC. He has worked on CMOS technology from 32 nanometer, 28 nanometer, down to 7 and 5 nanometer and below. And also, he was a leading researcher and manager at Qualcomm and Motorola as well. In addition to his hundreds of technical papers and more than 50 US patents, he has received numerous awards. Most notably, he has received the Compound Semiconductor Industry Innovation Award for his group's breakthrough in 3.5 FinFET work. And in 2013, he was given the Best Collaboration Award from Samsung Electronics Korea for R&D collaboration, contributing to the next generation CMOS technologies. And he also received the 2010 Young Alumni Achievement Award from his alma mater, University of Illinois Urbana-Champaign. And most recently, he was recognized by the Singapore's National Research Foundations as a returning Singaporean scientist. So please join me to welcome Professor Thim to talk about the low thermal budget functional material and their application to enhance flexible and beyond electronics. Professor Thim, the stage is yours. Thank you for being here today.
Thank you. You guys can hear me well? Okay, so maybe I'll start. First, I really want to thank the organizers of the KAUST Research Open Week for inviting me and to be part of this function. I apologize that I can't spend time physically there. It sounds like an exciting time. And also want to thank Professor Bradley for inviting me. I think we met 2019 at EMRS, where he was awarded the Jan Krukowski Award for his work in electronics as well as electronic materials. So I just want to take this opportunity to thank everybody for inviting me here. So my talk is really about materials. Professor Bradley actually said that I'm a born-again material scientist. I think it's true. My training is really in electrical engineering, but I see the opportunity in materials, in advanced materials. And I'd like to tell that story a little bit through the work that myself and my group is doing here at NUS, and specifically at this low thermal budget functional material and how it's relevant. So let's start. Okay, I just click next. Okay, so I'm just gonna. This is a set of slides which I've shown last time at the EMRS also, which basically. Next slide. Can you click a few times? Sorry. Go ahead. Yes. So this shows the evolution of sort of the use of materials from the perspective of the periodic table in terms of electronic materials engineering, right? So since the early 70s, during the early age of electronics, the number of materials being used and utilized and exploited from the periodic table has been increasing tremendously. And if you see today, almost all the materials on the tables is used. And with the exception of, obviously radioactive materials, which is not safe to use within the electronic components. So the semiconductor industry really is a major consumer of new materials, and the new materials offer new opportunities, both in functionality as well as integration. And I think we are actually in a period that's leading up to very exciting times, which I'm going to talk about in a moment. As what my host just introduced, I think the semiconductor industry is facing challenges, but with those challenges comes opportunity. And I think that's the message I want to highlight through this. So this is my view of where things may be heading. And first, if you look at this slide, which shows, obviously everything is driven from applications. We are entering an age where there's increasing diversity in terms of applications. Right? We're seeing it: wearable technology, AI, smart cars, 5G to 6G, everything. It's starting to happen. And now, obviously, supporting these applications is really semiconductor chips. So, the semiconductor has been cranking along for a long, long time, 50 years or more. And part of that is driven by, now the famous Moore's law, scaling, being ability to basically scale transistors and circuits down and increasing circuit density. That actually reduces cost per device and add a complexity to our technology. Now, at the same time, we're entering into a period where the value in terms of scaling is diminishing, not because it's not valuable, it's still valuable, but people are still expecting more functions, cheaper overall chips. So folks are looking into system level scaling. And the way they are doing this is that they're putting little chips together and making bigger chips that are more complex. So this is so-called scaling the system. So multi-chip packaging, heterogeneous integration becomes more and more important. So you start to hear this now, chiplet technology. You hear folks basically using something called interposer, where they add different chips together and then they package it together to make a big compound chip, right? That's what they're doing. Now, the third direction that's also happening is form factor. I think this is important. As we develop more electronics that are interacting with humans more closely, then the consideration for its form factor, how small is it? Is it soft? Is it easily carried? I mean, the phone is a great example, right? We are now having like foldable phones and stuff like that. It's becoming more important. And this form factor scaling drives another direction. And that direction is new manufacturing techniques that are sort of beyond conventional chip process technology, which is mostly rigid in form, in the form of a wafer, right? So these three things, I believe, are going to bring upon a convergence and an increased opportunity in terms of new materials. And this material innovation, it will basically drive what new opportunities are at the horizon in terms of new electronics, right? So these new applications will definitely bring upon a next level of heterogeneous electronics, in my view. Okay, so this is one slide that I kind of borrowed from Saif Salahuddin's paper that was published a year or 2 years ago. And I think the reason why I borrowed this chart is that it kind of summarizes where industry have been in terms of scaling, transistor count, and then over the years, right? I'd like to borrow this slide to illustrate a few points and also point to new directions where semiconductor technology is heading. So here's where we are today. And you can see that the entire industry is still very much focused on driving circuit density. Makes sense, because with increasing circuit density, you're going to get more complexity, you're going to get more functions. But because of the limitations in terms of our technology today, there's a lot more need to co-optimize. That means the people working on a process and the people working on a design working much more closely together to exploit whatever opportunity that's left in terms of scaling. And so this is design technology co-optimization, DTCO. It's a buzzword today that's used in industry a lot in terms of advancing the scaling further, right? And if you look out from this point in time, what we look at as opportunity are new computing systems. And these new computing systems drive the co-integration of logic and memory. And especially today, I think everything, machine learning and AI is a big hot topic, right? And machine learning and AI are not power efficient, and because they still run on conventional computing hardware. And I think in the near future, there will be new hardware that's customized really for AI, not just the GPUs, for instance. And this is where opportunity to bring memory and logic together becomes sort of a holy grail for research today in semiconductor technology. Another trend that you see, which is on the materials aspect, is that comes to the original point I made about the periodic table. I think you can see here, that the sort of the process technology is getting so complex. A lot of new materials are coming in at a very accelerated rate, and that's interesting for us who are doing research in this area. But definitely, it's a challenge for the industry. How do you maintain new materials to be added into the technology without affecting time to market, which is important because every new material you add complexity. But there's no choice because people are demanding functionality. And so this brings in new opportunities, new materials, especially the materials that could co-integrate nicely with our CMOS chips that we have today, and becomes part of the topic that I'm going to cover in the subsequent slides about low thermal budget materials and why is that important, right? And these new low thermal budget materials also drives opportunity for new innovation in terms of materials science and technology. Okay. So, flexible electronics, another exciting area, typically it runs parallel to semiconductor technology, also underwent its own evolution. And I think it's at the cusp of also a revolution to come, right? I'm not going to dwell too long in this, but again, looking at a similar format, here's where we are. And I think over the past years, more and more applications are driving diverse needs for sensing, power source, and then more sophisticated integrated circuits. We see, in the early days, polymers are the main focus, and soon there are people looking into oxides because they are low thermal budget, inorganic transistors, and even more recent times, we're looking at new materials like graphene and nanomaterials that can offer some of these properties at low thermal budget as well. Okay, and then even today, people are looking at self-generating energy, triboelectric, and self-healing materials. So you can see here that even flexible electronics is undergoing the same evolutionary path, right? Driven by increasing applications and need for integration, that there is a sort of a growing evolution of more materials to be integrated in, more innovative materials to be developed. Right. So one example where these two areas come together, right, where traditional semiconductor and flexible electronics come together in this flexible hybrid electronics, right? This is an example of from a recent paper and it shows, for instance, the different components of flexible hybrid. Let's see. Click next. Yes. So you have traditional chips integrated onto the substrate. You have flexible printed sensors that much larger, can interface with the environment. You have flexible display, obviously has to be big enough to be seen. You have large antenna systems that and wiring. And ultimately you have energy source. So here you see a range of sizes, right? As I mentioned, that form factor, it meets the form factor needs by going to flexible, but it actually leverages the performance of rigid semiconductor for the performance. Right. So that's where these two areas kind of converges. Let's see, next slide. Okay, so here are examples, some of the work that my group have done in this area, right? So an example of this is some of my graduate students worked on an ECG patch. You can see here it's actually a patch that's embedded in elastomer. It has a chip on board. It runs off a coin cell battery for a day, and it has interesting materials integrated in it. For instance, the interconnect that connects to the electrodes are made of liquid metal. And the whole thing is obviously encapsulated in rubber, clear rubber, elastomer. So let's look at this. And so the chip itself is not a very advanced chip, but it's a very reliable chip. So we fabricated the chips on a board to make the analog digital converters, 180 nanometer SOI CMOS chip. You can see the circuits here, and it's supposed to be low noise and high sensitivity, right? And then we integrated with liquid metal interconnect. So I think liquid metal, there's a well-known example, which is mercury. So we're not using mercury because it's poisonous, but we're using a eutectic mixture of gallium. In fact, it's gallium. So gallium has a melting point at 29 degrees Celsius. So if you mix in with other metal, effectively you could lower its melting point to about negative 19. So this is gallium, indium, and tin. And it stays liquid most of the time. Why do we want to do this? Well, this metal has high conductivity, but it's essentially very pliable because it's a liquid form. So the students of mine basically, in fact, decided to use this as a means of making a wire. Let's look at how that's done. So now the issue with this is that obviously if you use something liquid as a wire, you can't just build it like you would as a solid wire, right? So you have to treat it like, you have to create channels and canals for it where the liquid flow in and out. Now here's an example of what we did at the back of the board. We had these channels of liquid metal that runs around in a loop form, right? You can't put liquid in without bubble unless you kind of create a channel for it. So this channel would interface with the pads of the chip. And this allows us to interface liquid with solid connections. And when you've done that, you have a very interesting form factor advantage. So here's a slide that shows, for instance, on the left side, the board that's completely transferred into a elastomer matrix. And the evaluation board is on the right-hand side. You can see that these two boards is essentially the same thing, but one is completely soft and one is completely rigid and bulky. And with the soft embodiment of this device, you can squish it, you can stretch it, you can wear it in the shower, and it will continue to work. Whereas the board, they stop working. Obviously, if you do anything drastic to it, with the components all exposed, and it's definitely not flexible. So this brings us to why we do this, right? So here's one example where we mix traditional semiconductor devices, components, with non-traditional ways of making new devices, which is, in this case, liquid interconnect with the elastomer matrix. So the innovation here is not only the materials, but also the integration approach, right? And I think going forward, there's a lot of more opportunity in innovating new materials to add into some platforms like this, where we bring new materials that are non-traditional semiconductor with traditional semiconductor components. And that brings us to the next part of the story, which is new electronic opportunities. Now, before we get there, there are some fundamental points to be made about soft and rigid materials, right? So here's actually a slide that actually talks about the fundamentals, limitations of both hard and soft materials. If you look at bond energy alone, right? Obviously, materials that are kind of soft are typically unstable. They have low melting temperature because of weak bonds. Right? Strong bonds means materials are typically more stable and mechanically sturdy. Right? And another way to look at this is look at Young modulus, which is a mechanical property. Polymers are soft, low melting temperature. Semiconductor goes up into thousands of degrees Celsius in terms of processing, but they are rigid and hard. Now, why is this important? Well, the semiconductor technology, the reason why it's so reliable and we are so dependent on it is because it's very, very stable. It's very stable at the temperatures we use it at today, right? So the challenge is that if you were to introduce new soft materials are weaker bonds, then the thermal budget becomes the issue, right? Are they going to be stable enough for use? And that's the challenge that folks working in this area has to overcome. And in the next few slides, I'm going to talk about some of the approaches of achieving stability or controlling stability and controlling change using defects, for instance. Right? So here's a slide so there are ways to approach this. One, you can actually engineer new soft inorganic material composites by adding soft, nanomaterials into soft materials. And you can engineer defects in stable semiconductor material so that it is morphable, so it's changeable. And this is the fundamental approach of how to add functions into these regimes and be able to combine both of them. Okay, next slide, please. Okay, so one example of this composite is this material that we worked on. It's a very low tech material. What it is that we just basically added table salt to a rubber mix. You spin it, you let it set, you boil it, and then you remove the salt that's in it by boiling it in water. So it dissolves, and you create all these pores that effectively a sponge, right? So what's so special about this sponge? Well, in this sponge, in addition to salt that we mixed in conductor material. In this case, the liquid metal that gallium that I said earlier. And that gallium oxidizes and turns kind of grayish. And that's what it looks like. It's a grayish sponge. Now, this grayish sponge has an interesting property. If you were to compress it and let it actually generates energy in the form of triboelectric, which is a fancy way of saying, static electricity. So it generates static electricity from the pores. So here's the example that I gave about how it's made. Let me go fast forward that. And the way it works is that because the pores in this material gets compressed when you step on it or you squish it, there are actually static electricity that form static charges within the walls of these pores. And these static charges are then mirrored eventually onto the electrode, which is then captured as current. So here are some examples of how the current and voltages that we generate using this method, where you just move it, where you squish it, right? Now, let me change the topic now to the other aspect, which is the beyond the composite, about introducing defect into semiconductor and make it morphable. So much of the history of where we are in terms of semiconductor technology has been about how to ensure that materials like silicon, germanium, and all these crystalline materials are, are stable after processing, and they stay reliably stable in our chips. But increasingly, there's a need to basically introduce functionality in this material that's beyond the intrinsic properties of this crystal. And one way to do that is to actually introduce defects into this. Now that may be counterintuitive. Why would you introduce a defect into something which is perfect? Well, with the defect, it creates a degree of freedom for the material to change. And now the goal, the key is to be able to control this such that it doesn't introduce reliability issues into your electronics, right? So why do we want to do this? As I mentioned, that as we move further out along the roadmap towards the future, there's a need to bring memory and logic much closer together. Here are some illustrative example of that's what's happening. So this is a sort of a schematic of a blocks of at a system level how chips are going to be. You have logic chips that process information. You have memory where intermediate results of the processing is kept, and then obviously they get fetched and re-executed, right? There's a trend to move these memory closer and closer in towards where the processing units are. And eventually you can effectively put these memory on top of CMOS chips. So they are very closely located. The memory is located right above the chips. Now to do that, you need materials that are low thermal budget. And here's my attempt to explain why that is. For most of the semiconductor chips today, the back end, which is the wires that connect the transistors, are mostly made of copper. Now copper, it's a fast diffusing element. That means it moves around quickly. So during the processing of chips, the transistors which are processed at the highest temperature are done first, and subsequent, the wires are then put in. But once the wires go in, you do not want to expose the chips to higher temperature. And that temperature, crossover temperature, is about 400 degrees Celsius. Because copper will move out of its barrier and move into and between the materials in the wire. And that causes reliability issue. Now, as I mentioned, there is a sort of a desire to put more transistor in the back where the wires are already in. Now, how do you do that if the transistors are intrinsically processed at higher temperature? So you can't put transistor in the back end of the chips anymore, because if you do so, all the wires will be messed up. And that's one of a fundamental issue of being able to integrate chips with wires, with transistors on top of wires that are already made, right? So we start to look at other materials that potentially allow us to build transistors at lower temperature. And there's a whole range of them. I'm not going to go in the gruesome details of this, but effectively, these are, it sort of categorizes some of the new materials that are very popular today. You have obviously carbon nanotube nanomaterials, two-dimensional material, graphene being one of them. Now, obviously, there is this class of materials, oxide semiconductor, where the flexible electronics folks have been looking at for a long, long time, right? And people are now starting to rethink, can we apply some of these materials to conventional semiconductor? And that's where the exciting aspects are, right? And here is an example where I'm going to look into these oxide semiconductor. So oxide semiconductor is not new. It's been around for a long, long time. But can it gain enough performance? Can you optimize the materials enough so that it gives enough performance to be integrated with CMOS, which is traditional semiconductor chips? And the answer is maybe. And people are starting to relook at this again. One material obviously is zinc oxide, right? And you can actually manipulate zinc oxide by manipulating the defects within the zinc oxide. So here's a new way of thinking about semiconductor materials, right? Where you actually play with the defects to enable its function. Here are some examples of devices we built, and we're trying to get mobility to improve. Now, the devices, as I mentioned before, any device materials that changes at low temperature are intrinsically unstable. So the passivation of these defects and the control of these defects become very important. We looked at amorphous versions of zinc oxide, in this case, indium gallium zinc oxide, a ternary version of it. And we can get also pretty good performance with this, okay? Now, on top of that, you can build memory devices with oxides. In this case, we introduce defects into oxide, and then we can actually create something called a memristor, which is analog memory. And you can store conductance states in it. Unlike digital memories today, a continuous range of states it can store. And these are some examples of work by my students. And postdoc, we're looking at how to basically implement systems that can exploit this kind of memory, which I'm not gonna go into too much detail. And then you can combine the transistors with this memory to make memory cells, for instance. And then you can stack them layer after layer on top of conventional chips. All right. So, and in addition to this memory, I mean, there are also ferroelectric material that behaves the same, which I'm also not gonna go into too much detail. Now, ultimately, what would you like to build with something like that? Here's an example where we could stack 3 layers of chips, right? One on top of another, on top of CMOS. These layers are made out of transistors I've described before, which uses this ternary oxide-based transistors together with memory elements. And because they are all processed at low thermal budget and the properties are engineered by defects, you can operate them and implement them without affecting the CMOS chips beneath it. And that's sort of the holy grail of building circuits on top of conventional chips. So this brings us from a low thermal material to two-dimensional materials, right? So in terms of materials, transition metal, very, very interesting because there's a lot of reactivity in these family of materials. And that means defects are also very mobile and can also effectively alter the properties of this compound very easily. Okay. So one of the things that we look into is, for instance, a material known as tungsten selenide. It's a transition metal dichalcogenide material. We try to make transistor with it, and obviously by modifying the defect with it using plasma oxidation, you can gain quite a bit of performance gain, especially in contact resistances. Okay. And we have envisioned systems where we build layers and layers of these two-dimensional materials on top of conventional chips for the same, based on the same approach of low thermal budget. And you can mix both high mobility, high quality mobility channel with memory that is modified and enhanced through defect engineering. Okay. Here's one example where integrated memory with the transistors, and these are possible futures if we can harness the way to produce these 2D materials on wafer and being able to distribute them and integrate them and pattern them effectively. The neat thing about these two-dimensional materials is that because they are processed in potentially flake form, they can be formed into ink and you can print them. Right? In this case, we have printed two-dimensional material here to make memory devices in the form of an array, and they will form ahead of time and made into inks. And for instance, this is a material known as moly disulfide. And you can make flexible electronics with this, and one way to do it is with this high precision inkjet printing. In this case, the aerosol jet printer, and we can change the properties of the ink and the electronic properties by just changing the flake size of the material itself. So that really opens up a lot of new opportunities. Here are examples where we actually printed it on different surfaces, on different components, effectively with these new materials. And they have interesting properties. In one example here is a memory device that has large memory window. You can see there, and we understand that a lot of these memory properties are also due to defects within these two-dimensional materials. And we can alter the switching characteristics of this material by changing again the defects within them. We can even mimic biological memory. In this case, as the synapse of a neuron, for instance. And so this is interesting in implementing next generation AI, as I mentioned, because these analog memory can store continuous states, and they can mimic, effectively reproduce the neural net in a hardware form on chip, right? If you were to be able to implement these devices and these materials. And then I think that the most exciting work that we are working on right now is to be able to control this material so that they give us new functions. In this case, for instance, we could get two-dimensional materials liquid exfoliated into a form of an ink. And then through the exfoliation process, we can control the fundamental flake size of this material. So they are two-dimensional in form, but they are actually in the form of tiny platelets. And by controlling the size of the platelets, you can effectively control the memory characteristics. In this case, for instance, we could show that this two-dimensional memory composite material could beat conventional oxide-based resistant memory, which is the analog memory I mentioned before. And it's even more reliable. And the physics is interesting. It's all defect engineering. Effectively, the defects are moving on the edges of these flakes, and by controlling the flake sizes, you effectively control the percolation path of these defects. So these new morphology of material allow us to achieve new functions. Right, and we could build arrays of this memory. In this case, for instance, we could build them and program these states to, for instance, write a character here, right? And then we'll continue to look into, post-growth defect engineering. In this case, for instance, we could build something called a MEM transistor, a transistor that has memory. And we introduce the memory property into the device by creating defects by adding, by exposing it to argon treatment, right? And we characterize these materials, and we can show that effective doping of this material can change. We can program the effective doping of these transistors by moving the defects, and the defects can be moved by field effect properties. These are some examples that we do. So, so it comes back to this point I'm trying to make about new functional materials for, semiconductor and for flexible electronics. It comes back to this point that there are regimes where we engineer the materials in different way. For soft materials, we can create composite microcomposites, adding new structure into it so that it gives us new structural properties and even new electronic properties. And for traditional electronics, I think we're used up most of the materials in the periodic table. We're looking at compound. And the next more exciting area to develop is really defect engineering. It's not new, but people are starting to look at it from a standpoint of being able to create new functionality and new materials that are traditionally high temperature, high thermal budget materials, and make them low thermal budget so they can be co-integrated with chips. And with that, I come back to the few slides I started off the talk with, which is the convergence, right? I think we're at the cusp whereby Moore's law, needs help. And the way it's done is that, system scaling is already coming into the picture, and that will add increasing value to, chips that are already been made. I think the next frontier area is form factor scaling. How do we add non-traditional process technology, right? Things that potentially come from flexible electronics, printing into the picture to create these new convergence in terms of, and create new opportunities for material innovation and heterogeneous integration. All right. And then with that, I'd like to say thank you. I'd like to also acknowledge the folks that have supported all the research work in my group at NUS, and I'm open for questions. All right. Thank you.
Thank you very much, Professor Thin, for giving these wide-ranging and also very in-depth talks. So any question from the audience? Yeah, please go to the microphone. Yeah.
Hi, Professor. Really thank you for the very interesting talk. I'm Dhanu Chetri from ASL. Really nice talk to learn about your work from liquid metal to the stacking and also like how do we overcome for the next generation stacking materials. It was very helpful for a student like me learning about your research. I have one question from one of the characteristic that you showed, the transfer characteristic. You have the VTS shift, and it was mentioned that it's unoptimized, and there is an optimized which doesn't have a drift.
I'm sorry, I couldn't catch the question because I think the mic, I'm not hearing the mic properly. Maybe the host can repeat the question.
Yeah, so say your question again.
Yeah. So there was a shift in the drift in the VTH, and it was written unoptimized. Whereas on another figure, the VTH drift, there was no drift. So how the drift in the VTH in the transfer characteristic of a transistor?
Okay, so I think he mentioned that there was a slide showing the transfer curve of the transistor with a node called unoptimized. And so his question is, how to actually engineer the shift of the transfer curve in that figure, right?
How do we not make the VTH drift?
Oh, so how not to make the VTH shift, right?
Okay, right. So I'm guessing that the slide you're talking about is all the transistor curves that move around due to processing, and why. First, I think how not to make transistors that move around like that, right? I mean, to put it in layman terms, the answer is actually what we found is that the source of those movements, there are several sources. Okay, one of them is the gross one is really about exposure to environment. Right, as I mentioned, that these materials are effectively their transport are based on defects, and any changes in environment, whether it be humidity, temperature, the defects will move around and will change its properties. So one example of this is, for instance, the interface between the gate dielectric and, let's say, IGZO, which is the indium gallium zinc oxide. We see that there are a lot of defect transfer between these two materials. So one way to not allow it to move around so much is to make sure that this transfer is minimum. And one way to do that is to make sure that the gate dielectric is stable. So we process the gate dielectric first. We anneal it or we treat it with plasma to reduce the amount of defects in that material before we put the IGZO on. Now, IGZO itself intrinsically is based on defects. So any kind of oxygen and water vapor exposure is a problem. So the next thing you have to do is you have to encapsulate all those materials so that to keep them away from the environment, right? And so these are the two approaches that we do. Now, other than that, I think the operation of the device itself could also cause defect, and that's another story. I hope I answered that question.
Yes. Thank you so much, Professor. Thank you.
Next
You're
question.
welcome.
Next question, please. Yeah.
Hi, good morning. This is Dr. Samuel Gamdi from King Abdulaziz University. I will try to get closer to the mic so maybe Professor can hear me. Thank you very much for this comprehensive talk. You took us from back end of the line to the front end of the line, so thank you very much in a very smooth way. But my question would be about the ink MOS2. I see that you have used that for memory applications, but how can you control the band gap properties of this ink MOS2? Because, you know, MOS2 changes if it's rigid, you know how it changes with flexible, with being flexible and strains, but how can you control an ink MOS2? So that would be the first question. I don't know if you can answer the first question and then go to the second.
Yeah. I couldn't catch it, but
let me repeat the question. So his question about the ink printed MOS2 for memory applications. So his question is because the layer of the MOS2 will determine the band gap as well. So how do you actually control the band gaps? How do you make it consistent for the memory applications?
That's a good question. Yes. Okay. So first, I think in the memory that we are looking at, the band gap is less of the issue because the way that memory is implemented is that it's in series of flicks. So it's really the property of the defect within the material. Now, obviously, if you build a transistor, the band gap becomes important, right? Because the transport is really electronic transport within the material itself. Here, we are looking at the transport of the defect in those materials. So, in fact, the interesting part is that, which I touch upon very briefly at the end, is that we could make flicks of different sizes, which then changes how the defects move between those flicks. It then changes these electronic properties. I hope that helps.
Okay, yeah. I don't know if you can hear me now, Professor. They gave me a new mic.
Yeah, now I can hear you, yes.
Yeah, okay, glad. So the other question would be about the zinc oxide. I know that when one of your slides you said N-type and zinc oxide, and I know the problems with the P-type zinc oxide. But I am quite interested in the passivation. You said you passivated the zinc oxide using aluminum oxide. So can you elaborate more on the difference between thermal passivation and the oxide passivation of the... I know it's always about the application, where to use this material, but if you can elaborate more on what you've mentioned in one of your slides, please.
Yep. Yeah, so the passivation is very important. Typically, it's not the most attractive thing that people work on. So the passivation is important because a few things, right? One, let me explain the constraint. So in semiconductor processing, when you layer things, there must be things that kind of what we call interlayer dielectric that sits between them, okay? And this layer in the dielectric typically in advanced semiconductor is actually a porous material. It's a semi-porous material. And the reason for that is because they have to achieve low K dielectric for low capacitance between wires, right? So this is a horrible material to passivate anything, as you know. They're full of holes. So, in order to passivate something, I think the best passivant that we know today, I mean, in terms of things that we can deposit readily, it's atomic layer deposition technology. So obviously the most easily accessible ALD, atomic layer deposition materials, one of them is high K, it's aluminum oxide is one of them. So we tried different aluminum oxide, hafnium oxide. Now, the issue with these materials also, that by themselves have defects. So you need to make sure that the defect density within them it's not too high. So for zinc oxide, the constraint is temperature, right? If you were to, zinc oxide has with defects within it, and if you expose it to too high a temperature, it starts to turn metallic, or semi-metallic. So that means the passivation layer that you put on top of zinc oxide has to be sufficiently low temperature, has to be sufficiently dense, has to be it shouldn't have too much defect in it so that it can exchange defect with the materials underneath it. So there's quite a bit of consideration in order to get good passivation done for zinc oxide. Now for indium gallium zinc oxide is interesting. It's even though it's sort of the same family, but it has its own interesting property. It needs certain amount of thermal budget to be semiconducting, right? So there, again, we use ALD technology because it can create fairly good coverage with this technology. But then the temperature, ways to tune the temperature is different. And do we expose the entire stack subsequently to heat so that it stabilizes? It's also different with respect to zinc oxide. So the key message here is that different oxide likes different things. They are very finicky, unlike traditional semiconductor. And the goal is to be able to find the right combination, understand how the dynamics between things that's supposed to passivate it and things that activate it, for instance. I hope that sort of answers the question in a short time, yeah.
Very good answers. Next question, please.
Hello, can you hear me?
Yes.
You use the box. Can you?
I
don't know which.
okay.
Yeah, maybe the box will work. Yeah.
Okay. Thank you very much for the informative talk. Honored to be here. My question is, my title is, I'm heading the National Renewable Energy Center here at Saudi Arabia. So just to let you know where is my question coming from. So I'm really interested about the van der Waal materials that you mentioned, and out of the context of transport applications and electronic applications. And renewable energy, for example. Can we use this van der Waal material, for example, using it for some kind of solar or PV or any light-activated energy generation unit? I know they are very thin and they might not produce a lot of energy, but maybe watt per kilograms makes it, makes some prospect for it. So that's my question.
I see. Yeah, so I'm not an expert in that area, but I'm just going to at least try to speculate, right? Based on what I understand. I think the answer is people are looking at this for many purposes. Obviously, the van der Waal materials. The reason why, because there's such a big variety of them, and they have, coming back to the question that was asked by the previous speaker, right? About the fact that band gap can be tailored to your needs. So if you're looking at anything that's optical, that you need to generate stuff from light, obviously it's a very interesting palette of materials to work with, right? That's one. Second is, I think this is intrinsically, it's physics. It has high surface to volume ratio. It's effectively a sheet, all right, or a composition of sheets. So if you were to be able to exploit that for a purpose, whether it be increasing the reactivity, you want to increase surface area, it's definitely interesting to look at, to actually exploit. Now, the third thing, which is also interesting, which is what we did, is to exploit its defect properties, right? Because it's a single sheet, the defect energy on these materials are actually fairly low, so you can move them around quite effectively, and they can interact with the transport and electronic properties of the material. It makes it interesting as an electronic material. So my answer is obviously, it's that just like everybody else, it's encouraging to go look at this. It's definitely. Now, people have been trying to grow this at large wafer level. I believe that there's opportunity for that, but there's also opportunity where you could make solution processable versions of these, right, in small flakes, and tailor the composite material properties through the use of nanomaterials, nano-size materials itself. I hope that it's sort of skirting around the question, but
Thank you for the question. Thank you for the answer. We have a lot of enthusiasm for your talk. So next question, please.
Hi, this is Ahmed Daoud from the Royal Commission for Al-Ula. Just going back to the overarching theme for this week, which is sustainability. Currently, in this day and age, a semiconductor failure on a chip or a processor means that you throw away your entire laptop, right, or your entire phone. We're not back at the days where you can, go out to Circuit City and buy a new processor, get some thermal paste and a heat sink and replace it, right? You're throwing away. That's a lot of electronic waste. A lot of it's not very recyclable, and it has a really big carbon footprint. Yep. And potentially a lot of that has been driven by that obsession to reduce the channel width, right? When we're going down to, from 5 nanometer to 3 nanometer technology, you're increasing significantly the probability of electromigration, thermal expansion, and hot carrier injection, right? So these three types of failures are a lot more likely when you decrease the channel width. Should we then potentially, as an entire semiconductor industry, kind of walk back this obsession, focus back on building more reliable semiconductor and chips that are going to last longer in industrial IoT applications, in consumer applications, and focus more of the research on this defect engineering, spintronics, memristors instead? And what impediments do you see to that happening? So that's my first main question.
So maybe he can answer the first question first.
I think this is a very interesting question. You're making my day, which is great. I don't have a straight answer for you, except that I couldn't say that, I am, just like everybody else, is responsible for this. You could call it waste to some extent. I think, every 2 years, I look forward to a new iPhone and a new Apple Watch. And because there's a market for it, it drives technology. You can clearly see it. I think, all the consumer products, right? I mean, they are, in fact, driving the most state-of-the-art chips. And now, I think to your point, which is that, is this maddening? Is this kind of wrecking our environment and stuff? And the answer is maybe, because if you look at the amount of resources needed to make a tiny chip, it's not small. In fact, if you look at TSMC, which is a big company, with all its gigafab, the new fab that they're coming up is double-digit billions dollars. It uses a lot of energy, uses a lot of water. Now, obviously, in defense for them, they are one of the cleanest manufacturing industry out there in terms of semiconductors. But it's still correct to say that, making electronics consumes a lot of energy. And we are actually fueling it by asking for the next thing all the time. I think my view on this is that, yes, going forward, we need to be more judicious about the materials that we use and look at possibility of recycling. But I think ultimately, the role that electronics and semiconductors should play is to offset the carbon. Use technology to help us, control other manufacturing and other aspects of our society better, so that we can offset our carbon footprint, right? In some sense, carbon footprint. And the reason there is ways to do this. I mean, smarter manufacturing, ability to process a lot of data, right? You see that now. Everything is being monitored and sensed. IoT, through IoT, Industrial 4.0 and above, we can now become more efficient, even more efficient. I think that is how electronics can save us, from the disaster we're heading into, right? And I think we need to let technology help us, not exploit it just for gains, right? And vanity. Yeah, that's my view. Just my view, right? I hope I answered that question.
Somewhat. Thank you for the response. My second question is, do you think that the hype of the so far under-delivering promise of quantum computing has distracted away attention and funding from more promising advancements such as defect design, spintronics, and memristors? Sorry, it's a tongue twister.
Yeah. I think it's an interesting question. The reason why, because at NUS, we are also investing a lot in quantum. In fact, we're moving towards something called quantum engineering program, where we're trying to find translational angle to quantum computing, quantum communications. I think the way to think about it is this. I think quantum has a national security component to it. The reason why, because it factors into decryption, encryption, and technology like that, right? And I think ironically, I think defects are going to come into quantum computing also. Not as a way to help it, but the dephasing noise and problems, that challenges that quantum computer will see as they start scaling will still be, they will start experiencing, and then they have to leverage the know-how from conventional semiconductor. Now, is it robbing funding and attention from the rest? I hope not. I think if you look out at the current horizon, right, as you look out, I think the type of applications is so varied, and quantum computers can't solve all the problems. It's a specialized computing approach, right? We still need the variety, and then that's where the value is. I think lessons learned from chips, the same thing. So we have worked on, there's so many different types of microchips out there doing all sorts of different things, tailoring for different applications. And now even more at system level, we're combining these things. I think variety is sort of the strength. And I think we will move towards more and more technologies that are more increasingly diverse. Interesting for us. Tough for the people who manufacture these technology, of course. But I believe it's exciting times going forward.
Great. Maybe the last question?
Yes, very quick questions. That's me again. Again, for the MOS2, the ink MOS2, you said it's all about the application and the defect transport of the material. Can you mention or explain what is the the scattering mechanism that you use for this? What kind of defect mechanism that you, is it impact? It's liquid, so I don't know whether we're talking impact ionization, we're talking avalanche. I don't think so. But what kind of scattering mechanism that you see in this material?
So the MOS2 itself is actually crystalline flakes. They sit in a liquid matrix. So the liquid doesn't do anything except as a means for us to deliver the material onto the wafer, onto the substrate, right? So the key transport mechanism is really on those little flakes of crystals that are stacked on top of one another. Now, what are the defects? The defects, obviously, the most common, to sweep everything under the rug, they are actually vacancies. They are actually places where the crystals are devoid of atom. And those vacancies kind of move around because the bonding energy is low. And so they can move. Now, obviously, there's a lot of depth and physics behind it in the sense that these defects form complexes. They move by hopping. They move by exchanging position. But effectively, that's the transport. Now, when these defects come together and form structures, that's where you have this conductive path. And then the transport is conducted through electrons effectively. I hope I answered that question.
Yeah. Thank you.
Great. Thank you very much, Professor Aaron Thing, for the wonderful talk, as well as very insightful comments during the Q&A sessions. And although you cannot be here in person today, but we very much hope that you can visit us at your convenience in the near future. Yeah, please give a hand to Professor Thing. Yeah. Thank you very much. Yes.
Thanks.
Yeah.
See you.
Thank you very much for joining this talk. We hope to see you back here at 11 for the panel about sustainability in universities. And please, in the meantime, join the other CRO events. There is a startup area in the lobby, or upstairs, there is the booth area. Thank you.
KAUST Research Week is a new opportunity for us to showcase what we do in our research at KAUST. We are engaging a lot more with our colleagues within the Kingdom. We have many partnerships, we have many projects that involve direct collaborations, and this is a great opportunity to bring people to KAUST. So we have a very wide range of activities. We have an amazing lineup of guest speakers for our keynote talks. Our KAUST faculty are also talking about very timely research topics. We cover a very broad spectrum, so we cover the 5 themes that KAUST is developing. So we cover the environment, we cover energy, we cover water, we cover food and health, and we cover the digital realm. Getting out there, meeting people, getting into the labs, talking to the young people who are doing science, there's nothing better.
Hi, I'm Dr. Nadia Kareem, and I'm going to take you through our booths here at KAUST. For KAUST Research Open Week, we have put out scientific demonstrations for you all to take a look at. Want you to walk through KAUST's efforts for a more sustainable future. Come walk with me. Here at booth number 1, which looks like a very interesting booth, very relevant for where we are in KAUST. We're on the coast of the Red Sea. So please introduce yourself and tell us a little bit about this booth.
Yes, my name is José Hilton, and here I'm presenting an innovative system for divers. If you love diving, this is the booth for you. So basically, we have created an underwater communication system that will allow the divers to communicate underwater. Here, they can use their own smartphones that will be translated. You create a wireless network inside of the water that would be translated in acoustic signals, and these signals will travel inside of the ocean, and you allow them to communicate the same way that you use smartphones outside the water, you use inside of the water.
Which isn't easy, right? Because of the water, you've got waves, you've got murky waters.
Not only that, for example, all the RF communication that we use, that we have for granted here in the system right now, like in the open air, does not work in the ocean because...
So RF is radio frequency?
Yes, RF is radio frequency, and this is all absorbed inside of the water. So you need this kind of technology to translate the RF to something that can conduct in the water, that is acoustics.
Excellent, well done. This is fantastic. Who knew that we would be communicating underwater? Thank you very much, Jose.
Welcome.
Here at booth number 22, AmbuBag-based emergency ventilator. I'm just going to get these guys to introduce themselves.
Hi, my name is Mohammad Popalzai. I work for prototyping and product development core labs.
Thank you, Mohammed.
And Dr. Ronan Carling, I'm working for the PCL lab as well in the core labs.
Brilliant, Dr. Ronan, thank you. So if you could tell us a little bit about your booth and what's going on here. Who wants to go first?
So, we are displaying emergency ventilator here. The concept came from when COVID-19 started, the pandemic started. The emergency ventilators were considered as a very important devices to cope with when the medical grade ventilators were not available. So the Olean group and KAUST executives sat together and decided to design, develop and produce a ventilator for emergencies to cover for the Saudi Arabian shortage of ventilators, the medical grade ventilators. From KAUST, 3 departments worked together during the lockdown, the PCL, Prototyping and Product Development Core Lab, LEM, and Seymour. The engineers from all these 3 labs worked together and looked at the UK's healthcare and medicine regulatory standards and picked up the necessary or must-have protocols to build the emergency ventilator. The team from PCL, Prototyping and Product Development Core Lab, myself, Mishal Abdul Kareem, Michael Bearden, and from Engineering and Design, Dr. Ronan Carolan, and from LEM, we had Haris and Yusuf, and from Seymour, Andres, and Lloyd. They all helped to chip in and make this very difficult project working. So we can see on this booth that this is a live demo of the ventilator. It uses an AmbuBag, which is self-inflating bag, which is used for transporting the patient in the ambulances. And the concept is to make it mechanically active. So we proved the concept, and fortunately there was no further need for these ventilators, and we didn't produce those. But we proved the concept, and this was a very successful project.
Amazing, thank you, Mohammed. So maybe I can hand it over to Ronan now, because a lot of this was locally sourced, done in-house, and you can just tell us a little bit about the engineering.
Yeah, so as you can see here, the AmbuBag, we purchased this online. Most of the valves came from CKD, a Japanese company, and the flow sensors. This is your simulation of a lung. This came from Switzerland. So basically what's happening is the AmbuBag is being compressed. Here we can connect to medical grade oxygen. There's also an algorithm written to control the amount of oxygen that's required for the person's lung.
Wow.
Here on the actual program here, we can change the respiratory rate, we can change the tidal volume. So for a small person, you see a tidal volume of 250 milliliters. At the moment, we've it set to a ratio of 1:1. In a situation like this, with a 1:1 ratio, the person is really, really sick. So normally, you breathe at 1:2 or 1:3, but this is to deliver as much oxygen as possible, medical grade oxygen as possible. The larger the tidal volume, the more oxygen you can deliver, etc.
And the good thing about this is it depends, like the algorithm can work for a person, right? It varies for each person. Is that right?
Each person, the volume of their lungs, etc., etc. And again, you can't deliver a huge tidal volume for somebody with smaller lungs. Depending on how much oxygen is required, depending on how much they're struggling with the virus, it's how much oxygen you can deliver at one time. This is why the ratio will be 1:1. What else can I say? The pressures are set here. You can see the tidal volume in, tidal volume out, all controlled by the algorithm.
Amazing. I think this is an excellent example of what the core labs can produce when they all come together from different strands of the core lab. So excellent work, guys. Well done. I'm here at booth 23. It's about biosensing microneedle arrays designed from renewable polymers. I always love the word renewable because it just catches me, especially for the theme sustainability. Please introduce yourself and let us know a little bit more about this booth.
Hiya, I'm Dr. Huda Al-Fadus, a postdoc here in KAUST, and today we're showing an eco-friendly biosensing device that's 100% biodegradable. So the device is made of two parts. One is a polymer that is sourced from bacteria found in the Sahara here in Saudi Arabia and the sand.
Wow, so locally sourced.
It's locally sourced to reduce our healthcare footprint, carbon footprint. And it's also coated with a natural hydrogel called alginate. And alginate is also sourced from red algae found in the Red Sea. So it also can be sourced locally. So I can show you how they look like.
Yes, please. Tell us a little bit more about the microarrays. Why would we need them? Like, how are they used in healthcare?
Right, okay. So they would be little devices that are non-invasive. And those microneedles can go through the outer layers of the epidermis, and they can go to the superficial dermis and sample the interstitial fluid.
So it means it's going a little bit further than the skin, right? It's going deep down.
Yeah, no, just a little bit further than the skin, but not enough to penetrate into the blood vessels or like make you feel the pain through going to the pain sensor.
Excellent.
So it's just superficial. And the interstitial fluid carries biomarkers for various diseases in our body. So the microneedles are coated with this hydrogel because hydrogel carries the probes to detect these biomarkers. And so the probes will hybridize and bind to these biomarkers in our body, and then we'll be able to look at it again and see what's in there, basically, depending on what we're trying to detect.
Excellent, thank you. So take us through how then these are developed.
Okay, so there are two processes here. The first part is actually creating the microneedles. So I don't know if you can see them, but they are they're like square shaped. They're very small, and they're made, as I say, of a polymer. And then
polymer is another word, kind of, for plastic. It's what plastics are made out of, or polymer. Tell us a little bit more about polymers.
Yeah, so the polymer that we have here, like I say, it's a natural polymer. So it's basically, it's like the material that you sort of make synthetic, hard devices.
So instead of using plastic, you're using naturally sourced, eco-friendly polymers.
That's it. Yes. So it is 100% biodegradable, and it's completely natural and local source. So it kind of allows us to be able also to reuse it. By the way, I didn't mention that, but also if you have this a particular device, you can remove the gel and reapply it again, so you can use it over and over again. But anyway, if you dispose it, it won't be bad for the environment because it can be degraded. So this is the mold that we make it from. Like I say, it's a very small mold, and
very hard to see that, but there was something in that file. Yeah.
Yes. The polymer is PHB, so that's the name of it. You couldn't see it, you meant, but you can see it on the microscope.
I don't know if the camera can make it down into the microscope, but yeah, it's there. It's tiny. I guess that's why it's called microneedle.
Microneedle, that's it, yeah. Okay, he's probably able to catch it, I think.
So tell us a bit more about what's in this Petri dish here.
Okay, so this is the gel that I was talking about, the alginate hydrogel. And I colored it here with two different food coloring dyes, blue and red. And I want to show you how it's cross-linked. So it's usually liquid, and in the room temperature condition, in aqueous solution, there is a salt here, that's calcium chloride. It can be cross-linked, so the calcium ions goes in between and make kind of an egg box structure, and it becomes solidified. So if I take some here, and the color can hopefully show you, and I drop even little drops in the liquid, you can see the beads forming.
That is so cool.
These are gel beads, yeah. So the whole idea is that these beads are put in this shape, and because they are in the salt, they will form basically independent solid structures like that. But also if we coat the microneedle with it, and then we apply the same solution, it will solidify on top of it. And so we have the coating layer, and then we functionalize it.
Excellent. Thank you, Huda. I'm very excited to see where your research goes. Thank you so much. Take care. I'm here at booth 13. We are looking at gas sensors. If you guys could introduce yourself and tell us a little bit about what's going on.
Hello, this is Maniteja. I'm a PhD student at Sensors Lab. I'm from Electronics and Computer Science Engineering Department.
Hi, I'm Alex Pribish. I'm a research technician and, yeah, same lab.
Alex, tell us a little bit about what's going on here.
Right, so we have this gas sensor that we have over here. Well, actually the sensing element is right over there, if you can take a view of that. And we made an integrated system for it so it can actually work in real time. So it's a nice little package that we made there. And it samples gas and warns the user using an alarm siren once it goes above 3 ppm, and then it does a very loud siren once it goes above 5 ppm.
Okay, so these gas sensors are really important, I guess, because there's a lot of pollution going on in the atmosphere at the moment. We're all aware of climate change. And in particular, this gas sensor can be used to detect pollutants. So can you just tell us a little bit about where we might put this gas sensor?
Okay, so I used to work in the mining industry, and over there they tend to use like ammonium nitrate-based explosives, and sometimes they don't properly detonate, and then you just see these huge clouds of nitrogen dioxide. So typically there would be a good way, and like open cast mining. Also underground there's a lot of diesel machinery, and a lot of sort of byproducts from diesel machines also have these like nitrogen oxides that are quite harmful to the health, you know.
Excellent, thank you. Manny, can you give us a demonstration of what happens when it detects at a high level? Maybe put the sound on so everybody can hear.
So we have made sensors that are like transistor based. So what happens is these are very selective to NO2 gas. So these transistor properties will change when there is NO2 gas at very low concentration. So if there is very high concentration, these transistors conductivity of these transistors decreases. And so we have made this detector such that if it goes to that level, and it gives us siren.
Okay, are we going to hear the siren? Because I know it's like a fire alarm going off. Do we have sound?
Yeah, we just muted it just because.
Put it on. Let's get everybody hearing it. So I think the one thing that is really important about gas sensors is they need to be very, very sensitive, right? It's very hard. It's in the atmosphere. It's not something that you can see. So when you say ppm, you're talking about parts per million. And the one great thing about this gas sensor that it is actually very highly sensitive.
Yes, these sensors are like very highly sensitive. It's like when compared to the reported sensors. And another interesting thing is most of the sensors that are already existing, they're very high power consumption because they will work at very high temperatures. But these work at room temperature, so they are low power consumption as well. And usually they will be selective to other gases also, but these sensors are very highly selective to particularly to NO2 gas. That's the another.
Love it. So it doesn't need a lot of energy. It's energy efficient. It's highly sensitive.
We could show you the siren now, but we don't want to really introduce any harmful gases in this environment here, you know.
Okay, that makes sense.
It's against OSHA regulation, if you know what I mean.
Okay, Brill, guys, thank you so much for your time today. Thank you. So I'm here at the semiconductor booth. This is a special booth that we've laid out during KAUST Research Open Week. We wanted to demonstrate KAUST efforts towards a semiconductor research, and I'm joined here by
Professor Xiaohang Li. I'm a faculty member of Electrical and Computer Engineering and Applied Physics. So I'm one of the organizers of this semiconductor booth. And at KAUST, there are over 20 faculty working either directly or indirectly on semiconductor. And as you know, semiconductor is probably one of the most important foundation of modern society. Wherever you use electricity today, you have semiconductor chips at the core of the product. So here at KAUST, we have organized a semiconductor booth and trying to selectively covering some of the highlights of our semiconductor research. So here we have, faculty members such as Professor Nazek working on ultra-flexible and ultra-stretchable silicon solar cells, and this can be used in many, many scenarios from human to different machineries and to different vehicles. And here we have Professor Thomas Anthopoulos, and he has many excellent works on next generation oxide, high speed and low power diodes and transistors for different applications from smartphone to electric vehicles to communication. And right here we have Professor Atif Shamin's work on the fully printed, ultra low cost and also flexible switches and reconfigurable filters. This can have many applications in 5G, 6G and communication and beyond. And here, this is the research of my group. And so we have recently developed the world's first fourth generation CMOS. And that is after the first, second, and third generation CMOS invented by different companies such as Bell Lab, Boeing, and General Motors. And we are very proud of this work, and we hope this work can lead to a revolution in the digital technology in the future. And right here we have Professor Shahika Inan's work. She is a leading expert on the organic electronics, and particularly sensors and different devices used for monitor human health and also environment. And right here, again, we have Professor Thomas Anthopoulos' work on his advanced devices for different applications. Yeah.
Thank you, Xiaohang. This is fantastic, and I think it's worth saying that as well. The semiconductor research, it's a multi-billion-dollar research area, right? So what KAUST is doing is we are creating and developing the next generation of semiconductors.
Correct.
Excellent. Thank you so much for your time.
Thank you very much.
Booth 15, we're going to talk about CubeSat remote observation platform. So if you guys just want to introduce yourself first, then we can go from there.
Samer Masharawi. I'm the field research engineer of the HALO group, Hydrology and Land Observation group, with Professor Matthew McKibben.
Hi, my name is Oliver Lopez. I'm a research specialist in the Hydrology, Land and Observation group.
Hi, I'm Marcel. I'm postdoc in the HALO group also.
Okay, so tell us a little bit about what's going on here. Samer, I'm going to get you to just walk aside because we've got this really funky looking prototype here. Tell us a little bit more about what's going on.
So this is one of the new trend satellites that was created over the past maybe 10 years. This is one model that is one-to-one scale of how the actual satellites are. As you can see, it's a, what do you call it, a shoe box size satellites. I mean, the main advantage of them, they are much cheaper than the larger satellites. They are launching several of them. I think now there is more than maybe 100, 200 of them. We, as a group, we designed our own specification of one of these satellites that we are going to launch, I think, sometime next year. Our satellite is specifically designed for our application. As I can show you here, we have what we call it multispectral cameras. This one has 6 lenses, which means 6 bands. Each of these bands can give us information about the vegetation, either water consumption, health, chlorophyll content, what do you call it, NDVI, one of the parameters that can tell us how healthy the plant is. This is another example, and this has 5 bands. Our satellite will have 100 bands. And the whole point of this research is to test which bands can give a better explanation or better information about the vegetation, health, water consumption, etc.
Okay, so I was just about to ask, what does it actually do? But you just said it there at the end, so that's pretty cool. I guess in a world where there's water scarcity and we need to, be very careful with how we use our water, and especially when we all want to feed the world by 2050, right? This satellite is going to do that job. Can you just tell us a little bit more about the application? Who wants to take that?
Sure. So at the moment, we're using traditional large-scale satellites launched by NASA, by the European Space Agency, but these are multi-billion-dollar projects. So using this satellite data, it can help us to monitor over a large-scale area, even the whole Saudi Arabia. We can monitor where are the agricultural farms. So our group identified more than 30,000 center pivot fields in Saudi Arabia, which was a huge task. And now we're also including water use models. And yeah, this satellite, as Samer mentioned, has even more information that we can use to further use these models.
Excellent. It sounds like you guys are doing an amazing job, especially for the future of Saudi Arabia and the world. Thank you so much. I'm here at booth 21. I see COVID in the title, which is very relevant for the world we live in today. Can you introduce yourself and tell us a little bit more about this booth?
Yeah, my name is Muhammad Tehseen. I'm research scientist working under supervision of Professor Samir Hamdan in KAUST. We here developed this R3T one-step RTQ PCR kit.
Okay, so a kit is very important, right? Because first of all, we can make COVID tests, but we need all the reagents to make a COVID test. And this is when you say you've developed a kit, you have developed all the reagents that might go into a COVID test. Is that right?
Yes, exactly. Since last year, when pandemic struck the world, there was a huge demand of testing the COVID-19 in the world. So all the companies were rushing in to produce these kits, and ultimately, due to the huge demand, there was a less supply, and we have to buy the kits at very high prices. So we came up with this idea, and under the umbrella of KAUST R3T team, we started producing this one-step kit. Since we had the expertise of protein biochemistry and enzymology for the last, we are working in around more than 10 years in this area. So we took this responsibility and successfully produced this kit, which is as sensitive as the other kits in the market. And currently we are producing around more than 3 million reactions a week. And if we have a small facility for the production, we can just increase this to around 10 millions a week. And one of the KAUST startup is currently using this kit, and it is successfully deployed here. And they are taking samples from the KAUST and the surrounding areas as well. And I think they already took more than 10,000 tests with our kit.
Amazing. What's the name of it?
R3T one-step qRT-PCR kit.
Excellent. And it's funny because everyone was locked down, people were at home, but you were in the lab working really, really hard.
Yes, exactly. We have to come, but thanks to everyone for the procurement, all the university teams who supported for the materials to provide us. And luckily, we have all the ingredients in our lab. And then we successfully did it within no time. I think it took us 3 to 4 months to do that. Yeah.
That's an excellent point. I guess when everything closed down, so did the borders. And so what you have developed has all been in-house, locally sourced. So that's an excellent point. It's very important when borders close, what you can and you can't get, right? There's the supply chain closes as well. So congratulations on this.
Thank you so much. And plus, one most important thing about this kit is this is RT and the PCR. So it means it's not just restricted to COVID-19 testing. So it can be used for testing of any pathogens, any virus, RNA or DNA in humans, in animals, and in the plants. But since it's a pandemic, so everyone is about COVID, so we are using it for the COVID testing at the moment.
No, very well done.
And also the most the cost of the kit is around 3 cents per reaction, which is around 100 times less what is available in the market. And at the same time, the sensitivity of the kit is as sensitive whatever available in the market for us.
This kit has definitely been used on me multiple times, so thank you. It was very low cost.
Thank you so much.
It was excellent. The future of healthcare right here. Thank you so much, Mohammed.
And I hope you've been able to join some of our keynotes already online or in person if possible. Today I have with me Frauke van der Swan. She's a professor of earth science. Welcome, Frauke.
Yes, thank you.
Thanks for sharing some of your time with us. We're going to talk about how your work touches towards sustainability, because it's a theme, of course, of the week. And before we go straight into that, I would like to point out Frauke worked with one of our scientific illustrators, Ivan Gromicho, to create in KAUST Insight this new infographic, which is all about the Waba crater. And Frauke and her team were very helpful in the production of this beautiful infographic. Thank you, Frauke.
Very welcome. That's
So
really nice to do.
Thank you. So please tell us a little bit about your research and how it touches on sustainability.
So basically this article shows very nice what our research is, and that is volcanoes. So I'm an earth science professor, and we work on understanding geological processes. Some of those volcanoes are on land in Saudi Arabia, but another place where we have a lot of volcanoes is in the Red Sea. And that's one of the things where I've been pretty active in the last years. And that's understanding how the Red Sea is formed and the different environments in the Red Sea. And we're working together with colleagues from biology to also understand how this is impacted, for instance, biodiversity. There's a large interest from the kingdom and worldwide in protecting environments. So actually I fit more to the teams from yesterday about either water or the team from tomorrow, the environment, where we will also have the Red Sea Research Center open doors, because our work is trying to understand the system Red Sea. And if you want to work sustainable with the Red Sea, if you want to have ecotourism which is sustainable, you need to understand the system. And that's basically where our work is coming into play. Because if you don't understand the system, it's very difficult to work with it on a sustainable way.
Right. You can't conserve it, preserve it, or protect it if you don't know what's there.
Yes.
Right.
So, and especially in the Red Sea, there are many environments that are very special compared to the rest of the oceans. We have more endemic species here in the Red Sea than anywhere else in the world. We have very salty brine pools in the center of the Red Sea. We have volcanoes there, hydrothermal vent fields. So there's many things of the Red Sea that we don't know about, understand really, and we try to study that.
And by learning about these, then we can put plans of action in place to conserve.
Yes, of course. That you need to have this baseline to then start working on how to manage these systems.
And the Red Sea is one of our key research focus areas as well.
Yes,
as Professor Bradley has said. Yeah.
Yes, so the Red Sea is, I think, very important for the kingdom, and particularly if you think on a future with maybe more tourism, the Red Sea is one of the most important places where that can happen. Also the Red Sea is very important for fisheries and coral reefs.
It's super multidisciplinary, isn't
Yes,
it? That's why it was so interesting how you became a part of the Red Sea Center, coming from the Physical Sciences Division, which we haven't had before.
Yes.
So your work is really unique in that sense, I think.
It's basically this new development of trying to work in a more integrative approach, So Red Sea Center used to be more into biology, and now we're trying to bring biology and geology together, as well as faculty which is working on, for instance, sensors in the Red Sea. So we like to study things, but you need a lot of technology development and or machine learning. So there are projects going on which are getting so much data that you can't do that by hand anymore, and that's where you bring in this machine learning to try to understand all these components together.
And once that starts happening, this fits perfectly into digital.
Yes, that's true.
So it will
so I
all
don't
come
do it
around.
myself, but we definitely have a digital part in the Red Sea Research Center.
Yes, the overall scope of the work in the end will touch on probably all points, actually, all of the theme points.
And even in geology, if you have a lot of volcanoes, if you try to understand them, you want to have some parameters in place which can only be done by digital evaluation. Yes.
Feels like everything's going that direction, isn't it?
Probably.
Yeah.
Yes.
Great. Well, thank you so much for coming over, sharing a little of your time, Frauke, and explaining to us how your research speaks to sustainability. Thank you so much. Marine science professor.
Okay, ready?
And that's your camera.
Okay.
Or there, whatever you like.
Ready? Okay.
Hello, welcome back. I'm here now with Francesca Benzone, Professor of Marine Science. Welcome, Francesca. Thank you for joining us.
Thank you, Karen. Good morning.
Good morning. Francesca is here today to tell us how her work touches on sustainability. I'd also like to mention that Francesca is also, and her work is also featured in KAUST Insight. So please pick up your copy from downstairs or online from insight.kaust.edu.sa. Francesca talks in here about coral cultures and identifying corals. So, but in general here we're to talk about sustainability and how Francesca's work touches on sustainability. So Francesca, please tell us.
Yes, a short version of a long story.
Yes, a short version, sure.
Here at KAUST, I developed a lab that tackles different aspects of the fundamental knowledge of the Red Sea ecosystems. And in particular, we focus on bottom dwellers, on organisms that live on the seafloor and build up reefs in the shallow, mesophotic, and deep of the Red Sea. The shallow ones are pretty well known, the deep water ones less. And the organisms that are fundaments for these ecosystems are really hard to identify. They're called generally corals. They're very simple invertebrates, but challenging in trying to put a name on them and understand what they do. Okay. So with this initiative that we developed a couple of months ago in collaboration with NEOM, the Red Sea Development Company, and other universities within the kingdom, we tried to spread the knowledge we've been accumulating in the last decade on Red Sea corals and use it to train those people that go out and do environmental impact assessment, monitoring on the coasts of the Red Sea. So we're trying to build a culture of, how can I say, old school naturalism to try to understand what the resource is and how to best protect it in a sustainable way. And so this is the link with the theme for today. More in general, my lab focuses on different aspects of the evolution and distribution of reef organisms, and we do that through a multivariate approach, including in situ observations and measurings and sampling, and then lab work, especially for the genetics and genomics, and also morphological analysis using the fantastic core labs we have here in KAUST, especially the SCM facility that has really helped us a lot in trying to answer some of these questions. You know, sometimes people say, oh, you're just naming species, and you know, what's the use of it? What's the actual downfall on a sustainable use of the marine resource? Well, in order to protect and manage sustainably something, you have to know what it is. So this is when fundamental research comes into play.
That makes me think back to just chatting with Frauke when we were talking about how you have to understand what's in the Red Sea if you're going to be able to conserve, preserve, and protect it. So
yeah, you know, it's interesting because the Red Sea, in the mind of most people, colleagues and non-scientists, it is a relatively well-known body of water. It's a small ocean, and everybody thinks, oh, we know a lot about it. Turns out that every time we try to understand how it works or to answer a practical question on how to manage it, we realize there is still a great deal of basic information. Not because it's basic, but because it's fundamental. It's kind of building the basis for the understanding of how the ecosystem works. So that's a great challenge, and I am thrilled that KAUST gave us the possibility to actually engage in this and provide a service to the kingdom and to the region in this sense.
Really, it's a really nice thing to be able to do from the university. And I've heard you spoken of by the director of the Red Sea Center, Mike Barrowman, as essentially the go-to know-all person for corals worldwide, essentially. So
our director is very kind. So I have built up 20 years of experience in the region, working as a scientist and as a consultant in my early years. And this has given me the chance to see not only a lot of the countries that maybe are not so easily accessible for purely research objectives, but also to understand how the actual basic study of marine diversity is functional to choices and decisions that will ultimately lead to the management of the resource. So it's really important for me to have that practical link between the research we do and the applications it has in terms of informing the managers about where the resource is and how it is distributed and how much of it is there and why it is there and how we can better preserve it.
That's great. Well, we're lucky to have you.
Well, I'm happy to be here.
Thank you, Francesca. And you have some displays or demos happening on campus now? What have you got going on?
We have booths in Building 2.
Okay.
So I invite everybody to come and check it out, where we present a bit of our collaborative research and our own research. In particular, we are showing some very new ROV images of our own reefs in front of KAUST.
Oh.
So one of my group students is investigating the mesophotic depth, so between 30 and 70 meters, where normally you cannot scuba dive.
Right.
And so these relatively shallow but still unexplored reefs harbor a lot of surprises. And we're finding amazing mesophotic reefs in front of KAUST that will probably serve as, our natural laboratories for more research questions to come, and probably will inform also about other similar environments in the Red Sea, which are so far very poorly known.
It's nice to hear there's some really nice ones out there still, because we've been hearing a lot about how they're all dying. And
okay, so I'm a scientist, so nice for me is also a muddy reef.
Right, okay.
Nice in terms of interesting. So nice for the tourism, which is a very important economical aspect, by the way.
Sure.
Is something. And the Red Sea still have a lot of visually appealing and healthy reefs, although we see an increasing impact of different local and global factors that really impoverishes them. And this is very visually, immediately visible for even the recreational divers. Divers are really important sentinels for us, because they go out and they see a reef and they'll go, this has gone down since the last bleaching event. So it's, but...
And we love to take photos.
We do, and those are super useful because they allow us to extend our knowledge of size where maybe we cannot go and dive directly, but that information, that visual information, is data. And we're building a large data set of images and measurements and samples. So that's another big challenge for us, to try to organize that and make it accessible, not just within KAUST, but also for the kingdom, really.
Okay. Again, touching on digital.
Yes,
it doesn't seem like
absolutely.
you would think marine science is going to be aligned necessarily with the theme of digital, but almost everything is now. So
everything is, and the new Red Sea Research Center setup really focuses on trying to bridge the gap with all the initiatives that we have. I mean, actually, there is a lot going on at KAUST that touches on the Red Sea, and it's Red Sea research, whether it is geology or sensors or marine biology, as traditionally we have done. There's a lot going on, and connections are being built. And the digital theme is really one of those that connects for not just for display, visual display, but also for analytics and faster ways of analyzing these large data sets that we're collecting underwater.
Excellent. I have to ask.
Yeah.
So how is your student going below 30 meters, did you say 30 to 70 meters?
So
I have to
not
know.
by breaking the laws.
Okay.
But we have acquired a small ROV, a remotely operated vehicle.
Okay.
That's really like a PlayStation command that controls the asset, which is pretty much as on the small side. You have working class ROVs and small ROVs. We have a small one. And this allows us to investigate real time what happens down on the reef.
Okay.
This allows us to collect video images and images that are then our reference data set to start measuring and identifying. We're hoping to scale up and be able to also sample with a working class ROV and in collaboration with Seymour and different research cruises that we have lined up for the next couple of years. So the line of research is growing as we deploy more assets and gather more information.
Cool, so exciting. Thank you.
Yes, it is.
Thank you so
Thank
much,
you.
Francesca. We'll be sure to stop by Building 2 tomorrow, right?
Yes,
Open house
correct.
for Red Sea Center
Yeah.
is tomorrow.
Be there.
Be there if you can. Okay. Thank you. Thanks, Francesca.
Thank you, Caroline.
Good morning and welcome back to the auditorium. We're about to start this panel discussion about sustainability in university. I want to welcome on stage Dr. June Abrahano.
Good morning. Welcome back for this very interesting panel conversation that we're going to be having. We were told that as soon as the audience outnumbers the panel speakers, we can begin. So I am June Abrahano. I'm the Chief of Staff of President Tony Chan. And let me just put a little context to the conversation that we're about to have. Last July, The Economist released a video on what the Earth would look like if it was 3 degrees warmer. It is not a pretty sight. And what made it more horrifying is that there's 1 in 4 chance with the current policies that are in place that we will actually get there by the end of the century. To those who might not be impressed by this number, professor from Imperial College, Yuri Rouge, said that if there's a 1 in 4 chance of a plane is going to crash, would you like to board? So a 3-degree world is viewed by experts around the world as a disaster, such that Tony yesterday made a comment about one of our advisors in the climate and livability panel that we have here, initiative, I must say, that really the best way to deal with a 3-degree world is not to get there. So COP26, and I see that there are a few people here, including Anna, who were in Glasgow, basically showed some hopeful signs that there were some agreements that were reached, but in the end, the total commitments that were put on the table are not going to bring us close to the 1.5-degree target of the Paris Agreement. So as Tony also mentioned yesterday, after Glasgow, it looks like we are no longer on a path towards a disaster, but we are still in great danger. So the question is, are universities relevant to this discussion at all? And how can a normal university with its normal activities of research, education, innovation, and the normal campus operation, could we be making a dent on the global thermometer? Recall what we need to do that. Basically, what we need to do is to reduce the emission of carbon into the atmosphere. We need to capture carbon that is already there and reduce as much as we can other greenhouse gases that are important, like, for example, methane and nitrous oxide gases. If a university were to pledge to be net zero, would that make an impact on the levels of atmospheric CO2? Or are we just trying to make some kind of a symbolic gesture? But there's another reason why a conversation like this would be important to have in a university, beyond simply contributing to reducing the amount of CO2 that is in the atmosphere. Earlier this year, the United Nations Development Program released a survey. It's called the People's Survey. It's a survey of people's opinion, a total of 1.2 million of them, on what they think about climate change and what they think about the actions that we are taking to prevent the Earth from warming. I urge you to read it. It's good reading, and it's actually a wide-encompassing survey. But the reason that I'm bringing it up here is for 2 reasons. The first reason is that it actually concluded that the most interested in global warming and the people or the group of people that would like to take action are those that are well-educated and those that are younger. And it looks very appropriate that we are having this conversation here today because the universities, in fact, are the places where you find the people that are younger and well-educated. So as we move on to this conversation, there's quite a few input that people has made in this conversation. And I lost myself in the teleprompter, so I'm going to my notes. If we put the two reasons together that I have just cited, first, on how to convert the ideas that are promulgated in campus, researched, and innovated, how to convert that into decreasing the amount of CO2 that is in the atmosphere. And you put the second reason, which is the universities are home to this demographic that is very motivated, as Tony has pointed out yesterday. Many of our youth are beginning to take action because they see a world that is coming forth that is not very pretty, and at the same time, the window of action is closing. So if you put those two together, I have a quote from Thomas Friedman after he came out of the Glasgow meeting. He said that in order to solve the climate crisis, what we need are a few more Greta Thunbergs and a lot more Elon Musks. In other words, we need people who are motivated and people who are innovating in order to solve this problem. And again, there could be no better place to have this conversation as it is here. So to help the Elons and the Gretas out there, to provoke them into getting into a conversation, we have three panelists that have kindly joined us for this conversation. I will introduce the gentleman who is joining us from a distance. There he is, Davis Buchhardt. Davis is from HKUST. He joined HKUST in 2013 to prepare this comprehensive HKUST 2020 Sustainability Challenge, which might have started under Tony Chan if the timing is correct. Davis serves as the steward of the plan's implementation, and he concurrently serves on the advisory board of the Association for the Advancement of Sustainability in Higher Education. He teaches courses including sustainability management and sustainability thinking. Before joining HKUST, Davis was the director of the Office of Sustainability at Johns Hopkins University, and he likewise served as commissioner of the Baltimore Sustainability Commission appointed by the mayor. He has a master's degree in international affairs from Tufts University in Boston, and a master's in American literature from the University of North Carolina in Wilmington. Rose, well, feel free to clap if you want to. He can hear you. Thank you. Next, we have Rose R. Moore, who serves as the lead of the AUS Sustainability at the American University of Sharjah. Rose has led this group in leading all aspects of sustainability on campus, including community engagement, operational efficiencies, sustainability-focused research, and promoting sustainability. Before joining the American University of Sharjah, she served as a member of the Social Innovation Fund, an Obama initiative providing funding for social innovation across America, funding well over $1 billion of community programs. Additionally, Rose has worked with the Peace Corps and as a director of the programming and training in Fiji, and she also spent time in Burkina Faso in West Africa. She has a Master's of Community and Regional Planning from the University of Oregon and a Bachelor's of Arts in Natural Resource Management from the University of Texas. And finally, a familiar face and a familiar voice of sustainability on campus, our own head of sustainability office, Ana Margarita Costa. She leads the cross-campus working group charged with sustainability assessment and planning here at KAUST, including the design and implementation of sustainability vision and strategic plan. The promotion of sustainability across campus has been a major engagement, and we were expecting, and we see some paces of our sustainability students for sustainability that she also helped manage. Anna, as young as she looks, has well over 2 decades of experience in sustainability. She, of course, other than the time that she spent here at KAUST, she spent time at the Institute of Environment and Development, a not-for-profit group in Portugal. Anna holds a master's degree specializing in atmospheric pollution and a PhD in environmental sciences from the University of Aveiro in Portugal. So without further ado, let me get out of the way so they can begin their conversation. Thank you.
Thank you, June. I want to start this conversation, it's a very informal conversation, to say that the three of us met 2 years ago in United States, in Spokane, and the annual conference of ASHE, that stands for Association for Advancement of Sustainability in Higher Education. And it was really a nice group, and we decided to keep in touch. So we regularly meet to discuss how our universities are advancing our sustainability programs. So it's very good to have Davis and Rose. Well, Davis, we are missing you here. I hope next time you'll be joining us in person. I would like to start, just to kick out the conversation, to ask both of you, start by Rose, to explain us how the sustainability program is developing in your university.
Absolutely. So thank you so much for having me. This is wonderful to be able to get back together in person and to talk about sustainability at our different universities. So American University of Sharjah started our sustainability office back in 2009 when we were, prior to that, we were not responsible for our electric and water bills. And at that point, we started having, that started to become one of our responsibilities. And so that the major focus of our office in the beginning was to address energy usage on campus. And so that has been throughout time, that's been a large focus of the office. But in 2017, under a new chief operating officer, we expanded the office to engage the ASHE STARS accreditation process or rating process. And so we do a lot of different things. We work I work with professors. One of the big projects that we're doing is looking at integrating education for sustainable development into the curriculum and working with professors. We've created with UNESCO, we've created a boot camp that invites professors to bring a student into, to bring other faculty into a process that they go through a couple of months of learning about the SDGs, learning how to integrate those into their class, learning about transformational pedagogy to be able to integrate that into their classroom. So we go all the way from that spectrum, and then we also go into more of the operational sides. So one of our big missions, one of our big projects that we've started this term is we've started a climate action plan. And so we're really looking at our greenhouse gas emissions and looking at what we're doing for that and how we can start to address those. So those are kind of there's a number of other projects that we work with there, but those are some of the kind of the spectrum of the work that we're doing at American University of Sharjah for the office.
Yeah. Before I pass it to Davis, but you also engage with the students, because part of the conversations we have is a lot on the students level. Right?
Absolutely. They're core to our mission, and students are going to, they learn behavior change from their peers much more so than they do from me. So we engage students at all levels. We have what are called eco-reps, which are paid student workers that work for us that do events and activities, and they manage our social media, they manage our much of our communications, and they do a lot of the work like that because we've just found that peer-to-peer education, students are much more receptive to that than to listening to me or to faculty at that behavioral level.
And Davis, you have an amazing program in your university. Can you tell us a little bit more?
Yeah, thanks, Anna. I'm so glad to be here, even if I can't join you in person, but it's a real pleasure to join the two of you virtually on stage. And maybe at some point I'll be able to come and see your beautiful campus in person. Actually, getting to you is probably not so hard, but getting back into Hong Kong is a bit of a hassle with quarantine. So, but I'm pleased to be here for a couple of reasons. First of all, because we met at this conference and we really realized that even though we're spread out over great geographic areas, we have so much in common, and so I'm glad to be able to share the stage with you. And I'm also glad to come to President Tony Chan's university. You know, he was the president here at HKUST for quite a while, and we miss him, of course.
He's here with us.
Imprint on this campus, and
David is really here with us. At Professor Tony Chan is here saying hi, but you cannot see it, so he's here.
Oh, okay. Well, I wish I could see you. Anyway, greetings from Hong Kong. Greetings from HKUST. Hope you could come back for a visit at some point. So let me tell you a little bit about what we're doing. So I think that the key question for us, I mean, for practitioners in sustainability, what we're really looking at is what is going wrong today that we can't continue to do into the future. So we solve problems, and quite often the reason why we have some issues is because we don't often look at the outcomes in a multiple framework of looking at the systems and the multiple impacts. Of course, we're seeing that right now in this global pandemic. We're really trying to focus on one thing, which is the virus. But at the same time, we're consuming disposable masks, disposable PPEs, disposable hand sanitizers. What we find on the beaches now, when we have beach cleanups and volunteers will go out, they're finding masks and PPE and hand sanitizers. So we have to learn how to fix one problem without creating another problem. And of course, that's the world that we are in. So at the university, we put together our climate action plans. We're hoping to be net carbon zero by 2050, but the question is, how do we get there? We know we can incrementally chip our way at it, but we really need to be thinking about big step changes, because transformation really is the word of the hour. Because you can't change your light bulbs to net zero. You can't improve the chillers to net zero. You have to really kind of rethink and be willing to upset the apple cart just a little bit to be able to get there. So three things that we're really focusing on right now. Number one is rethinking about what's the role of the university. When I was in school, there would be a professor who would teach to the students. That was the single point of knowledge, and that person had everything you needed to know, including what to read, what articles were important, and what came out of his or her mouth was the most important things that you should pay attention to. And then, of course, you can bring that back. So much of that information is now available online and YouTube videos and others. It's not as important to be this single source of content as much as it is now to transition into experiential learning, project-based learning, trying to figure out how students can pilot and experiment on their own so that they learn through doing, which means that we're focusing on skill building. And what kind of skills? Future thinking skills, complex problem solving skills, life cycle analysis skills. All those things will transform across all careers because it's not a disciplinary approach, it's a mindset. So that's number one. The second one is really looking at our campus as a living lab, right? If we're going to try to get our students to try things more so they can build their skills, then we have to re-envision what the campus looks like, which means that you don't have traditional buildings anymore. Every building is a potential site for a new experiment for a student or for faculty. So most of our experimentation right now is happening with faculty and staff, as they have a prototype and they just need to test it out someplace. And we need to treat the university as a place where all of this kind of learning and experimenting happens outside of the laboratory so that people can see it and experience it, and they notice this is really what learning looks like, this is what it feels like. And then finally, the last thing, and this is the most difficult for the operational side, is we need to start operating the campus in a way that's consistent with what students are learning in the classroom. And if a student in the classroom is hearing what your moderator just said a few minutes ago about how do we stay below 3 degrees Celsius? How do we try to reduce our carbon? How do we do all of these things to reduce, become a zero waste? They can't walk out into the campus and see things like overflowing trash cans and lights that are left on and air conditioning systems that are too cold, because we're not acting in the way that we're trying to teach. And so that dissonance creates a problem that we really need to resolve. And so those are probably the 3 things that are at the top of our list right now.
Davis, just to go back a little bit on the program, you have this amazing program, the Living Lab program, but you also implemented we have discussed that funding scheme for sustainability projects. Can you just give it a bit of description of how does it work? How are the projects that are being funded?
Right, so we have a bit of a fund here that it's 50 million Hong Kong dollars, so it's about 7 million US dollars, spread out over several years that we can allocate to campus-based projects. Now, most of these are going to faculty and to researchers and some graduate students. Mainly because a researcher can work on a project for an extended period of time, whereas students have a limited time. But the idea is that we combine smart and sustainable, and both of those are essential, right? Because you could put in a garden, an organic garden. It's very sustainable. That's a wonderful thing to do. We should all do that, but it's not very smart. And then on the other hand, we could spend a lot of our time focusing on research that's very smart, very technical, very kind of data-driven, but the outcome is not improving the human condition. It's not making our lives better. It's not improving our health. It's not doing anything that would create a better world or create the conditions where we can live within the planetary boundaries. So you have to have both of those. You have to be smart and innovative and really thinking about how to use the technologies that are available. And then you also have to combine it with the sustainability mindset to make sure all that innovation is getting us to a point where we're all collectively better off. So smart and sustainable means that we give out certain grants to projects. We've had about 27 projects on campus now, ranging from behavioral nudges using artwork to try to influence people's behavior to become healthier, to using block certs to provide accreditation and diplomas electronically instead of through hard copies, to air conditioning, smarter air conditioning, ways of capturing energy from renewables and from solar and so forth. So it's really kind of goes across the lines. But what we're finding is that if we can do those projects on the campus, then the project teams are learning from the experience, and then everyone else can learn from what the project teams are doing. So it's kind of a and we also make sure that everyone understands that we're not looking for projects that will be perfect the first time. Nothing ever works perfectly the first time. In fact, that's usually you learn much more when you try something, it fails, and then you figure out why it fails, and then you tweak it, and then you try it again and again and again. And so we encourage people to say, even if it doesn't look right, even if it doesn't work as well as we think it is, that's still a learning opportunity. We should embrace that.
That is great, and we were talking about how this is important, because our campus actually look like small cities. So when we try these experiments, and then this opportunity to scale it up and have an opportunity to try then and use it as a test bed.
Absolutely. So as we've gone through this, one of the things that I bet a number of people here in the audience don't know is all the great work that is actually happening here on their campus. This is one of the challenges that all 3 of us have, is trying to communicate and trying to share all the great things that we're doing. So Anna, why don't you take a second and tell us what you're doing here that I'm sure might be information for some of the audience.
Yeah, thank you, Rose. So yes, one of the important part is communication. You're totally right. So I think we are missing this important piece. There's a lot of great things that's been happening in KAUST. We are now building up on this. We are hopefully build very soon a sustainability website that will work as a hub. And the most important is actually to bring to life all the information and projects, initiatives that every department at KAUST is driving on sustainability. We are in a process, we'll have very soon, a sustainability vision that will work as an umbrella
for the entire university. But I would say that the first part is actually to explain what is sustainability, because people are still confused. So sustainability is a very holistic concept, and how can we translate that in tangible things? So when we say it's a sustainability, and I think it's common to both our universities, as it's translated, it means that it is a cross-cutting area between our education efforts and research, the innovation component for sustainable development. Of course, we want to be a sustainable campus, to be a role model, and to engage with society and transfer this knowledge to society. So we are all doing a lot of this in KAUST, but we are failing communicating. Hopefully soon we will see a lot of this coming alive. And we are very proud of our teams in KAUST, and we are celebrating their efforts. We are make sure that we are going to highlight their efforts and energy in our website and to communicate them well. So this is one of the important part of the things we are doing right now. As being part of the Office of the President is very interesting, because our role will be actually to make sure that we are together on the same path. So pretty much what we find that people are having different initiatives in the campus, and because we are aware of them, we can connect them and somehow create this enlarged picture and do it better together. So it's been quite a rewarding experience to make sure that we are connecting the dots and helping everyone thrive. Could be, in the provost, because he's doing a lot of effort also on education for sustainable development. And there are new initiatives that will come up next year on the research aspect. And this week we are celebrating our research at KAUST and how much it connects with sustainability. We are seeing the Sustainable Development Goals in our campus, and we are connecting them. So advancing UN SDGs is actually a very important aspect of our work. And we are seeing this in communication through community life, and there are initiatives to our community, so trying to bring up alive these sustainable development goals. And the operations side, of course, reducing energy, managing our waste, and having commitments. So there will be a future sustainability plan coming next year, hopefully, and we'll need all the hands on deck, everyone's support to bring this alive.
Absolutely, it's such a challenge. I really loved the magazine and how you guys were mapping all of your work to, or much of the work in the magazine, to the SDGs, and being able to see that so that everyone can see that what they're doing is tied to the different things. It's such a valuable exercise.
So we started by KAUST Impact, and we have David Keys here, and actually this exercise of showing how KAUST is creating impact in the kingdom and how it's advancing the UN SDGs. And people might think this is something, small, but it's not. Because actually, when the Saudi government comes and communicates to United Nations, it goes through all stakeholders in the kingdom and asks, so how are you advancing the UN SDGs? And we'll say, here's our list of our efforts. So we are contributing towards this effort, a national effort. So it's pretty much important to have this happening. And now we have a new magazine from the research team that is also advocating for the UN SDGs. So we are very happy and proud of the teams. So Davis, how is your effort with the United Nations SDGs?
Well, the United Nations SDGs has really made some of this a little easier for us. And Anna, you were just talking about communication. Quite often, I think one of the challenges for us is that we do need to be translators, because there's certain big concepts that we're trying. It's not that they're too complicated. It's just that they're not exactly they just don't necessarily roll off the lips. So when you're talking about climate change and net carbon zero, and you say, well, why is net carbon zero so important? We breathe carbon dioxide, and then next thing you know, you're already in the weeds of what's anthropogenic carbon and non-anthropogenic carbon. And sometimes we just need some shortcuts to be able to talk about, what is really helpful and important. And I think the SDGs have really been able to kind of clarify in certain ways what sustainability means in a very practical and systematic way. And I think the one thing that the SDGs have done that's also quite helpful is that it really demonstrates that sustainability is not just environment. I mean, some people take sustainability, environmental, greening, all those, it's all kind of the same thing. Well, it's really not. And in fact, there's only, I think, maybe 4 or 5 of the SDGs that are environment related. and another 4 or 5 that are socially related. And of course, because everything is interrelated, you do find that if you can alleviate poverty, for example, there is also an environmental benefit. So I think that these SDGs give you the opportunity to have more complex conversations in ways that are a little bit easier to digest because it's been broken up into such nice pieces.
They're also very visual because they have beautiful colors and translates very well.
Absolutely. And there's a model that you'll find, the wedding cake model, that's just based right off of that, Davis, that is 3 layers of the SDGs, and the bottom one is the environment, the second one is social, and the next one is the economic. And it really just brings to life how without the environment and social, you have no economy. Without the environment, you have no social, you have no society. And so it's all, they're layered and it's foundational, and it's really just very eye-opening for students to kind of see that and see how it's all tied together and see exactly, as you said, how no poverty actually filters all the way down. So they're great tools to create that visual learning.
Yeah, so we could talk a little bit of our climate action plans, right? And Davis, you want to address a little bit how you're driving your climate action plan?
Yeah, I think, so actually this is a really great way to segue from the SDGs, because there's one more thing that the SDGs do. It is they set a goal in the future, right? So these SDGs, we're aiming for 2030. And in 2015, when they were kind of officially launched, 2030 seemed like a very, very long way away. And we realized that that time will come much, much faster than we think. And I think one of the things that's really difficult for us when we're talking about climate and climate plans is that just naturally, as human beings, we really don't think in terms of long-term planning. We're just not very good at it. We fix things quickly. We try to address the problems that are in front of us. We don't tend to think about things that might happen 10 years or 15 or even 30 years from now if we're talking about a 2050 model or 2050 target. And I think one of the things that we're finding, and Anna and you and Rose, I'm sure you're finding this as well, because we've talked about this a bit, is that when you start to put climate into a 2050 framework, it forces you to think about what does the world look like in 2050, right? Now, naturally, what we'll do is we will feel like, well, there's been a lot of change over the past 30 years, but the next 30 years probably look a lot like they are now, but maybe we'll have some more electric cars. But if there's anything that we've learned from the last 30 years is that, that things happen quickly and transformationally. I think 7 or 8 of the largest companies in the world right now were not even in existence 30 years from now, 30 years ago. If you think of Facebook and Google and so forth. So in the next 30 years, there's no reason to think that it won't be equally as transformational, if not even more. So what does the campus of the future look like in 2050? And how does that impact our plans? I think it really forces us to start thinking of questions or asking very hard questions like, will we still be teaching all of our classes in classrooms? Will we be doing a lot more remote learning? Will we be doing things where students are gathering the experiences and coming back to campus to share, but they're actually doing their work outside of the campus? If that's the case, what do we do with the buildings that we have? For lab research, we know that, for example, car companies used to, ram their cars into a barrier so they could test out how well they performed under crash tests. None of that happens anymore. That's all computer simulated. So how much of the research that we're doing right now in these very big, energy-intensive, heavy breather laboratories can actually be done through computer simulations? And speaking of computer simulations, how much of that computing actually has to take place on campus? If our campus is a very carbon-rich place, then would it make sense for us to start taking some of those data centers and other data, especially data-intensive kinds of applications and then move them to a place where there's a lot more and abundant renewable resources. So it really does kind of, rattle the cage a little bit to think about, do we really want to continue to operate our campus in the same way that we are today? It makes sense today, but we know that it's not possible to do that sustainably. So what are the things that really absolutely have to be here? What are the things that we could do without? And what are the things that maybe we just have to rethink?
Yeah,
and I think, Anna, you've been thinking about this a bit as well, in terms of, planning for the future and carbon, and how do we build that into our action plans and so forth.
Yeah, it's a very interesting and complex exercise. And actually, the exercise that we have, the complexity for a small place and like a small city, now we can imagine how we can try to scale it up for the world scale. And the challenge that we have, even on funding, a lot of the things that we know that we need to do. But actually, the part of planning is it's actually the step that we need to have, right, yeah. Rose? And you are doing right now that. We will for sure be doing that in the next, I would say, hopefully next months.
Yes, so we're working on developing our climate action plan right now. We have had workshops with all of our different facilities teams, and what we're actually doing, we've broken it into two parts. We're developing our technical climate action plan right now, and so that's much more the operations, the facilities side. We're working with them. They're creating recommendations. We're doing a greenhouse gas study, looking how we can cut our emissions and what we're doing as and trying to project that out into the future. As Davis said, it's been very hard for we can definitely envision the next 5-10 years, but beyond that, we're definitely a little bit challenged to see what those steps are going to be. So that's where we're really realizing that we need to push ourselves. But so we'll develop these recommendations and develop our technical plan, and that will be done in December. And then next spring, we're going to do something that we don't do a lot at AUS. We're going to do a lot of stakeholder engagement. And so we're really working. We are going to then part of this is telling the story of the last decade of what we've been doing with the Sustainability Office and in facilities. So we're working with our communications team and hiring a graphic designer and a videographer to be able to tell that story so people understand where we go. Because one of the things that you find that people say is their suggestions of what we should be doing are things that we've already done. Well, all the lights should be LED. Well, we've already done that. We're past that now. So really communicating where we are at that point, then communicating what the technical plan will be. But then we're going to have workshops with the faculty, with the staff, with the students, with our community members that aren't affiliated necessarily with the university, just the spouses and the dependents on campus. I don't know about here, but that's not something that we've done very much of. We're also going to talk to our external partners. We're going to talk to our neighbors, all of these things that haven't really happened in the past at AUS, and really trying to engage the larger community to see how they can work with us to be a part of this plan. So, we have a research park next to us. How can you integrate our goals of our plan? How can you help us with that research? We have some planned communities around us. How can you be a part of our plan? How can you integrate into this? What can you do? What can we research in your location? What can you do with us to make sure that this plan can move forward? Just to communicate that and bring it alive to so many more people than just our community, because we can do quite a bit technologically with the advancements, but a lot of the action for us to get to where we want to go with our climate action plan is going to involve a lot of behavior change, and that is going to, we need to have those different audiences bought in to the process so that they'll be a part of that behavior change, because if we just come at them and say, this is what we're doing now, they're not going to be, that process isn't going to move forward like we want to, so that's a big steps.
I totally agree. I think the question of helping people to understand that they have to have ownership of sustainability. It's often we hear from the departments, we are helping you. That's not the truth and should not be this way. We are always telling them, no, we are helping you. So bring alive your initiatives, take the ownership of sustainability, be proud of it. Be proud of what you are doing. We are going to celebrate with you. So that's what the stakeholders engagement, not inside the campus also, but outside. And we have also a very interesting technological park here that we look forward to work with everyone. So that's totally agree. And just to say on the climate action plan, plan front. KAUST is in the process of having a solar farm, hopefully soon. It will not solve our problems, but it will pave the way for a better future. But you are right on the question of the emissions inventory. To be able to manage our greenhouse gas emissions, we need to measure them. And so this is the first exercise, that we need to keep tracking of our emissions and try to address them. And we know that direct emissions in campus, we can identify them. We know the indirect emissions comes from the electricity consumption, which is big. And just look for the AC system that operates in the university. I'm sure that you have the same problem.
Absolutely.
I'm not sure, Davis, do you have the same problems with the AC systems because it consumes a lot of energy? How is this there?
Oh, you mean in a very hot and humid subtropical climate?
Yes.
Yeah, it's right at the top of the list. It's right at the top of the list. Well, and I guess it's the whole building approach is something that's just not. We're struggling with buildings that were designed 30 years ago when energy was cheap and you could just blast as much energy into the building as you needed to be able to make sure it was cold enough for everyone. And of course, now that's the opposite of what we want to be able to do. You only want to use as much energy or as much air conditioning as absolutely necessary and not one bit more. And so that's just a complete redesign. And it means that you think about things like windows and insulation and walls and ceilings and things that we just didn't think about. They just weren't at the top of the list 30 years ago when this campus was being designed.
You also have your story, right, Rose?
Yeah, but you also make such a good point, because so we recently did a remodel of a building on campus, and a lot of the climate action plan and what we're doing now is sending signals. And the UAE, just as Saudi Arabia, just pledged to go net zero. And these are sending signals to industry, to businesses, to the universities, to all of these things. So last year, we started a remodel, a retrofit of one of our buildings. And when they came back through the bidding process, one of the companies that we eventually ended up going with came back, and the electric load that they had for the building was extremely high. And our facilities department said, and the reviewers of the bid went back to them and said, no, we can't sustain that use of electricity. That's not where we want to go. And so we made them go back and we made them change the insulation levels, the windows, the glazing on the windows, a lot of the different aspects of their bid that then reduced the energy load by 2/3. And part of that was they don't want to come to you with that bid because that's a more expensive bid. And they're not on the lowest bid. If your contracts are lowest bid, they're not going to win the bid. So we are starting to incorporate into our procurement these kinds of things, saying we will not accept a bid if it doesn't have this level of insulation, if it doesn't have this level of window glazing and envelope protection and those kinds of things. So we really need, and so that's us sending signals to the contractors out there and the construction vendors that we work with that this is our normal way of business. And this is how we need to move things forward. And until we start making those kinds of decisions and really moving things forward in that way, it'll be business as usual. And so I think it's really important that we play a key role in making and being strategic in our sustainable decision making. And so I think that that's an area that we've all kind of talked about a bit. And Anna and Davis, why don't you give us some of the examples that we've had many conversations about.
Many conversations, setting the standards, leading by example, and actually, being part of that engine to make the change, right? So that's an important part of it. We addressed that. Yes, Davis. Yes.
I'm sorry. There's one other role that universities have too, and it's fairly unique in this. And I agree with everything that you just said, Rose and Anna. But there's one more thing that we can do, and if you look at the reason why designers and engineers would give you a design that's very conservative, it's because the conservative is time tested, and we know it works. And so as universities, one of the things that we can do is we can go in not just in the tendering process, but we can have conversations with the designers ahead of time. Because the thing that most consultants are worried about is if we say we want an innovative design and then they give us an innovative design and it doesn't work exactly right, we will blame them and we'll never hire them again, right? So how do you avoid that? Well, you avoid that by giving a very conservative design and just saying this is the best that we can do. So one of the things that we can do as universities is we can say, we'll share the risk. I know that we're putting a lot of pressure on you to do something that you haven't done before and to design a building in a way that we think will work, and we'll work on it together to see if we can get all these innovations, but we'll also share the risk. If it doesn't quite work exactly right, then we won't blame you because you're doing what we're asking you to do. And of course, if it does work right, then we'll both share the glory of having, one of the, most sustainable green buildings on the campus. But, there is a lot of other things that are part of the design process that aren't really technical or design oriented. They really are business decisions. And so we have to address those as well.
That's true. Well, we addressed one of the parts of this challenge of climate action and being carbon neutral, zero carbon, and how much this implies for institution, right? Because there's financial efforts. We looked for the pledges that a lot of the universities are doing right now, aligning with the governments, setting the example, and we are looking at, is this possible? Are we able to reach these targets? Are you confident, Rose, that when the moment you put a target, you will be able to reach, and the university will support that?
Well, I mean, today, if we were to have to implement this plan in 5 years, no, we could not reach net zero. AUS is a predominantly tuition-funded university. We are not a heavily endowed university, and it just doesn't make sense for us to spend our money on because you'd have to invest in offsets, and it just doesn't make sense for us to invest in offsets to hit carbon neutral in the short term when we should be investing any of that money into greening the campus. So right now, today, no, I don't think we can hit net zero. But I think that the world is being optimistic and thinking that technology is going to catch up with what we want to do. We're going to be able to sequester carbon, all of these kinds of things at scale to be able to hit net zero. But I think that I don't think it's realistic for me to say that today we could do it. But we have to be bold, and we have to try to get there and set those targets long term, but we have to be realistic on what we could do today and really heavily invest in what makes sense, but it doesn't make sense for us right now to invest in offsets.
And what about you, Davis? How is this? How is your target? You have a target, but the plan itself?
I think that it's actually a little bit of a blessing if you think about it the right way, because of course I think no university can really hit carbon neutrality without offsets. Yep. And it is a little frustrating if you see some universities around the world that say, we've achieved carbon neutrality, and they bought a lot of offsets. And that's great. I'm glad that they're doing that, but it also gives the impression that you can take your foot off the pedal, and we can't do that because there's way too much to do. In fact, if you decide not to buy offsets next year, then you're right back where you started. So it's not sustainable. It's a nice way to try to remove carbon if you can, but it's not a sustainable strategy. The sustainable strategy is to really try to put together some long-term plans that will help get you there. Yeah. But the real advantage of not kind of falling into the trap of saying we're just going to buy a bunch of offsets and alleviate our guilt is that it gives us time to do what we can do very well, which is we can influence the markets. So as universities, we have, as Anna, you just pointed out, we're small cities. We have restaurants and transportation and so forth. And each one of those represents a way for us to try to influence the market. So I can give you just an example. Globally speaking, every meal that you eat has a carbon footprint of somewhere around 3.5 kilograms to up to 10, even 11 kilograms of carbon, depending on where it comes from. We used to think that a lot of the climate change related aspects of food came from the food miles, from transportation, but it turns out that's actually not true. It's about 80% of it, of the the climate impacts are from growing, fertilizers, pieces of equipment, tractors, all the things that happen during the growing and production process. So if every meal is contributing at the low end 3.5 kilograms and at the high end, let's say 11 or 12 kilograms, that's a big range in between. And since we all have restaurants on our campus, this is what we consider a scope 3 emissions, right? We're not the farmers, but this is part of our supply chain. There's someone making decisions way down that supply chain, and that ends up in a meal on our plates that is being consumed by us and by our students. So we have a lot of influence over how that supply chain is undertaken, because we can, in our tendering process, we can try to ask our restaurants to source responsibly. We can ask them to take a look at what the climate footprint is for different dishes. We can even calculate the climate impact of all the dishes, and we could put that on the menu so everyone can even see that these types of dishes right up here have a very heavy carbon footprint, and these ones down here don't, and these ones in the middle. All of these things can help kind of indirectly influence the supply chain, either through our own actions or through the consumption of the people on our campus. So, and those are the things that take a little bit of time to really get going. You don't just do that, overnight. Or as Rose said, you can't just get there by 5 years from now. These are long-term plans.
Yeah.
This is the long game. This is what you're doing with the transportation sector. It's what you're doing with your air travel. It's what you're doing with your supply chains in terms of materials that come onto your campus and food and everything else. So let's take advantage of the fact that we do have a little bit of time and start building in those kinds of structures so that we're putting the kind of influence onto our supply chains that make a real difference.
That's a very good point. I just would like to stress the importance of the research and innovation that we are driving in our own universities. I'm pretty much relying, and I'm hopeful that KAUST, with the amount of great research on the carbon management, will be able to drive this research and as part of our climate action plan to reduce our carbon footprint. So our Circle Carbon initiative, it will be, I hope it will be one of the key points of our future climate action plan, is to actually bring alive of this research on our living lab approach.
Yep.
We are running out of time, and I would say that I would stay here. I don't know about the audience. I would stay here for there are so many things we could talk about. We didn't have time even to address the role of our students, and which is a very important part. And we will go very briefly because we want to open the Q&A for some to be able to answer some nice questions. So, Rose, very quickly on the student side, how you see the role of the students on pushing for changes in your university?
I'll just say a really quick story. We, in 2020, in the May of 2020, we did our first online open campus recruitment event. And so it was the first time that we were able to really clearly collect data on what virtual tables the students visited and stuff like that. And it was at that moment that the University of AUS opened their eyes to the power and importance of sustainability, because the sustainability virtual table got more visits than many of the colleges did, because this is what students are interested in. This is what really is driving them, and they want to know what's happening in this. So they're core to what we do. They are our messengers. They are our researchers. They do so much. So they're absolutely essential to everything that we do.
That's wonderful. Davis, what about your university?
Yeah, what's so funny is that I think we've even talked about this in the past, is that you have to stay on top of what the students are thinking. And even just, 5 or 10 years ago, students would take a look at what you do on the campus. And let's say you build a new building and it's a green certified building. Here it's called BEAM, but it could be LEED or whatever you have. And they would say, wow, that's impressive. I'm so glad that you're doing that. You're taking, you're really taking this seriously. Today, you build a new building and it's at the platinum level, and the students say, well, of course it's platinum. What, are you crazy? How could you do anything else? So their expectations are just through the roof right now. And they're not thinking about like, wow, let's give you a pat on the back for trying. They're thinking like, what have you done lately? And what are you doing for me? And the fact is, I think now more than ever, students are recognizing that they are heading out into this great unknown that has these tremendous headwinds coming right at them because of all the bad decisions that we've made. And not intentionally bad, of course, but they're unsustainable decisions. And they are in a very difficult position because they don't know how it's going to impact their jobs or their careers, their future, their ability to have a family. In Hong Kong, there's a lot of concern about even things like housing. And they're facing all this and they're thinking, wow, I'm going to have to go out into the job market and deal with this on top of whatever kind of job I get. But I think that in parallel, the one thing that I think is very inspiring is that students are also seeing the role of business as changing. It used to be there was this idea that you could have either or. You could have a good business be profitable, or you could take care of the environment. Well, they don't see it that way anymore. They don't see it that way at all. In fact, what they see is that there's people like Elon Musk who can make $1 billion by doing something that can improve our world and create a great new product. There are people who are doing all kinds of things in terms of renewable energy, and there's just jobs and jobs and jobs out there. This climate change can either be the biggest distraction or the most horrible problem that we'll have to deal with, or it could be the greatest opportunity for creation of value that has ever come along in the history of our economy. And I think they want to see it that way. They want to see this is the way that we go, that we solve the problems, we create great businesses, and we create the world that we really want to leave our children.
That's really great. And KAUST the same. We have a great, very active group of students. Rose, you've been with them. Yeah,
yes.
Yesterday, Davis. The next time we'll make sure that you meet with the students for sustainability. They are driving the way. Yeah, Nadia's making. Yeah, so we are going for the Q&A. So we don't have much time. Mary, yes.
Hi, I've got a question. Mary Matheson from procurement here at KAUST. David, you touched on the fact that you've got a budget for sustainability projects, and Rosie, you had talked about how bids come back in and they can be more expensive. So here at KAUST, what will we do when we have bright ideas? Is there going to be a fund available, and how easy is it going to be to access that?
That's a good question.
So, for me, this is. I thought this was like. Well, I think there's clearly there's indication that we need to create a platform to invest on sustainability. This is actually a very good question, Mary. I was like, oh, don't make me this question. So I hope there's, that in the future we need to make sure that this fund is available, this funding is available to invest in what we think is, and we believe is important, and sustainability is important. So, and when we come into this project and say, well, what is the return of investment? Oh, that's not good, because the return of investment is not cover this. This mindset needs to be changed. If you want to move forward sustainability, we need to invest money, and that's the reality. So we'll go through that journey here too, for sure. So hopefully soon.
Well, I could jump in here for just a second. I can't spend KAUST money, although I wish I could. But I could say this. I know anything that that we consider kind of a sustainable infrastructure is really just good business management. We shouldn't even call it sustainability. I mean, if you're replacing lighting, if you're replacing your infrastructure, if you're trying to make things more efficient, that's not a sustainability issue. That's just good management. Who could go into the boardroom and say, I have this great idea. We're going to continue doing things exactly the way that we've been doing them, even though we know that they're losing money and it costs us valuable resources that we could be using for other things. I mean, it's a loser of an argument. So that by itself doesn't need any justification. It just needs people to say, this is good management, we're going to do it, and build the value creation case for it. Where I think that universities could allocate some money is in looking at cutting edge, things that wouldn't necessarily get funded because they don't have a return. How do you know if a certain kind of a hydrogen fuel cell might work in a certain kind of situation and be a good backup power source for your laboratory? Well, you don't know that unless you just go ahead and try it. Or how do you know if there's certain types of blockchain that could help streamline some of your business, and your administrative processes? Well, there may not be a payback, and in fact, it might not even be something that provides a lot of value, except in the intellectual curiosity that you find out that, wow, this is really cutting edge, and we're doing something that we haven't tried before, and we're willing to put a little bit of funding into kind of this, operational innovation mental framework, right? Because we'll let the experts who are in the facilities, they'll just make good decisions and they can take care of themselves. But there's a whole range of things if we really think creatively and innovatively. It's nice to have just a little bit of seed funding to be able to try something that hasn't been done before and see if it works.
Absolutely.
Okay, so I think my question also related to what you just guys mentioned. My question regarding the ambitious goals for especially educational institutes, for example, universities or healthcare facilities or something like that, where would they have ambitious goals in terms of emission neutrality? We have heard the president yesterday mentioned here at KAUST mentioned that they're aiming to reach neutrality way before 2060, which is the NDC of Saudi Arabia. My question is, we would like even to look a little bit for deeper, especially for institutes where it's non-profit and making money is not the paramount or the pillar of their objective. So I am heading the National Center for Renewable Energy at King Abdulaziz Center for Science and Technology, and also I aimed at my center to reach carbon neutrality, but I started to think of it a little bit out of the box. For example, what if my engineers, for example, design some kind of photovoltaic projects for citizens in Saudi Arabia, and it's free, and that values of whatever that cost, I will just take it as a carbon credit for my center to reach that. And that's not very tangible toward treating the sustainability and the emission of the organization itself, but would it be, for example, feasible for such institutions, non-profit institutions, to consider these solutions? I mean, non-tangible solution, for example, giving educational services as a credit, as a carbon credit, for example, or healthcare, a hospital that would give a day in a month, for example, for free treatment or something like that, just as a carbon credit or something like that. Thank you so much.
Rosie, you want to address this?
I'm not sure that I totally, I'm not sure I 100% know. I do know, so we just recently talked to one of our, when we were doing our greenhouse gas, the bid, we talked to one of the bidders, one of the vendors, and they did talk about different organizations and the registration process to be able to, for your services to be able to be a carbon offset or to be a carbon credit. So it's a registration process. So you would have to look into that registration process and see if what you're doing fits that model and that mold, and then they kind of subscribe to your services, and then when they get companies that want to buy the credits, they have a list of projects that we were able to go through and pick what projects that we wanted to go, and each credit had a different value. Some of them were $2 to $5 a credit, and some of them were up to $20 a credit. There was a stove project, an efficient stove project, and that was in the 2 to 5 range, and then some sustainable agricultural projects were in the $20 US range. So if you are able to become part of that list, then perhaps that is something that you could use your services and get carbon credits for that.
Yeah. But there are some dangers on the offsetting. Davis, do you want to address this?
Well, right. So the offsetting is a little bit tricky. I appreciate the question, though, because it really gets at something that is overlooked, which is what are the other things that we could do that could contribute to a positive carbon-free economy? And I think one of the examples was, could you volunteer your time to help people in a hospital and things like that? And I think that could, there could be ways that there are things that you do that actually can help to reduce carbon dioxide in very unconventional ways. And I think we should be able to capture that. So for example, I remember in Project Drawdown, that's a group that's looking at different ways of trying to reduce carbon. And I think one of the most powerful ways of reducing carbon in the developing world is providing more educational resources for young girls as they're growing up. And the idea is that, you know, without education, they don't have much to look forward to. They get married at a much earlier age. They have many more kids. You know, you could see kind of the cycle of poverty kind of building up and creating a carbon impact because of that. And so, and that has nothing to do with renewable energy. It has nothing to do with, you know, with emissions, but it does have an impact. And so I do think that there could be ways that you could be looking at non-traditional ways of contributing to a zero carbon world. But with that said, the thing that makes it tricky though is that offsets right now are kind of all treated in a very similar way. If it can remove a ton of carbon from the atmosphere, then that's all we're kind of looking for. But of course, something that removes a ton of carbon, but only removes it for a year or two, really should be treated differently than another kind of technology that can remove a ton of carbon from the atmosphere and remove it for, let's say, 100 years, right? And we need to be able to price them accordingly. We also need to be thinking about things that avoid carbon. So if you have a coal plant and you sequester the carbon, you're not really removing it, you're just decreasing the overall amount that you're emitting, which is different than, let's say, some kind of a soil, you know, or farm restoration project, which could actually be putting carbon from the atmosphere back into the earth and trapping it there. That's actually removing it. So there's a number of different pieces that are involved to it, but I think the two things are how much carbon over time, and secondly, are you avoiding carbon or actually removing carbon?
Well, next question.
Yeah, okay, hello. Thank you for the really, you know, many inspiring thoughts. You know, I have one comment. Sustainability for me is not really an option, you know, only like kind of to say, oh, that gives me business opportunity. But for an institution like KAUST, it's really an existential question. And it is an existential question because a 3-degree increase in temperature will come with a sea level rise, right? And we are at the lovely shore of the Red Sea here. And instead of using our diesel buses to go to work in the morning, we will use paddle boards or kayaks to come to work. Our supercomputer would be flooded, the facilities, all our nice air conditioning units will also be flooded. So it would take care of a lot of problems that we have in terms of reaching sustainability, but it would render the university that we hope to grow for 100 years or 200 years, like the institution that we're aspiring to be a part of, it would just make it unsustainable. We would disappear. So sustainability in action, that is living it here on campus and as a red thread through most or all of our research, is an existential must. And I think we as university need to live up to this and have the plans and the actions together to reach sustainability in a very short time distance, because 2100, that's 80 years from now. That's nothing.
Thank you, Volker. Just a small comment on that. Definitely, you know, we need to have an action plan. Not only mitigating our own emissions and setting the example, but actually being ready. You know, as you said, probably we need to have an adaptation plan for the university. What will happen if you go on a path of 3 degrees, what will be the energy consumption of our buildings? So we need to adapt ourselves and think about the future, not only in terms of mitigation, but in terms of adaptation of our own campus. Rose?
Absolutely, and I think one of the things that was most eye-opening for us when we started doing the workshops for our climate action plan with our facilities and our operations staff was many of them thought that they had no role in climate action and changing this because they were thinking very much of their personal life, that they could carpool to work, they could commute or they could remotely work a couple of days, they could change their diet, but overall that was not going to have a huge impact. And when we started to explain to them, in your role at the university with your responsibilities, you can have a huge impact. All of a sudden they started to get excited that I can make a change, that this is really in my hands. And so we're really, that excitement was very inspiring to see from the staff, that not only were they now believed that they could make an impact, they were excited that they were going to be responsible for making some of this impact. So I agree that we need to do it, but to see that inspiration of the staff and to see that motivation was really wonderful.
Davis, you want to add something?
Yeah, I love the way that because both of you now have talked about how finding the right way for people to be involved can also really create the conditions for people to see that they're part of the solution, and that's really the key. And Anna, you had mentioned that a few minutes ago, and that Rosie just mentioned it again through your stakeholder engagement. It just reminded me that a couple of days ago was Thanksgiving, in America, and I'm not able to go back to see my family, but here with my family, we do talk about what we're thankful for, and and at some point I said, I'm really just thankful for the fact that I get up every single day, and my job is to try to make this world a better place. What a great job, what a great job. What a thrill to be on this earth and be able to work with lots of people and try to make this world a better place. And I think that, but really my job is to try to, as Rose said, engage everyone else to feel like that's their job too. And so everybody has a role to play. And if you're in IT or if you're in the software department or purchasing, if you're also thinking about how do we become more sustainable, how do we prevent, the beautiful KAUST campus from turning into a kayak range, like you just said, what do we all have to do? And we all have a role to play. Some of us are very good at numbers. Some of us are better at equipment. Some of us are good at writing and communicating. But all of that can be contributing to a really positive direction. And of course, our universities, this is what a university is supposed to be. Our universities, generally speaking, in our mission statement, we talk about making the world better and improving the lives of others. And so, making sure that everybody, kind of feels that inspiration that, yeah, if I do my job really well and I think about, what a sustainable university would look like, then I do have a role to play, and I'm very proud of that. It makes me very happy to know that.
And we have a big plus here. We have faculty. We have a center of knowledge. So Volker, you are most welcome to come and contribute to this exercise. We need you and all the faculty. Last question. I know that we are over time. Yes.
So I have a question regarding the involvement of the students. So we are talking here about the importance of students being involved in sustainability action in the university, and we see a lot of activities that are considered extracurricular, and I want to delve even deeper and making the students part of the solutions that are proposed. So for instance, if we have students that have studies where they study life cycle assessment and how these can be incorporated into real projects in the operation side of the university, where when we go to contractors and we say we want to create a plan to mitigate disposable used items or alternatives for this, where actually the student knowledge can say we can create a report as part of a master student's thesis or a part of a PhD thesis of a student, where really the project of the student is the assessment and how we can better the university. And therefore, when the student goes out, he has a real case scenario on his curriculum to then translate on a corporate side or a governmental side. So is this being done in your institutions, and what are your thoughts on this?
So one of the things that we've done recently is we've taken all of our energy data for the last 16 years, our water data for the last 16 years, paper usage, our recycling, our commuter data. We've taken all of this data that we've gotten, and we don't have as much data as we'd like, but we've taken all of the data that we do have, and we've put it in public folders on our Google Drive. And those data sets are available, and we are encouraging professors and students to use that data to do life cycle assessments, to do different research using those data. And we do a data visualization class uses our data for their research projects, trying to incorporate those real data sets into the classroom. One of the reasons is because they're real data sets, they have flaws in them. They're not all right. And so that's a much better way to actually teach a student how to use data, because you're never going to get a perfect data set. And so we've been doing that, and that's been successful. And so students can use it for anything, and it's just open and out there and available. So we're really trying to encourage people to use our data, to look at it, to come back to us. And if they have a better way to do something based on our data, come give us the argument. Come talk to us about what we can do and how we can change things.
Davis.
Well, I love the question. I think it's so spot on, and we're really focusing on this as well. In fact, I'm in the process of putting together a proposal to create what we're calling the Life Cycle Hub, and it'll do just like what you said. It will really create self-learning modules and training workshops to really get students, and not stop at the students, for staff as well, and for contractors to understand how to do life cycle, because they don't. And we put it into the contracts for every new building or every major renovation. And of course, nobody will admit that they don't know how to do it. But then when you start to ask them, they say, oh, we don't have time. We don't have time. So there's a gap there. And I think life cycle, not just life cycle costing, life cycle analysis, life cycle thinking, I think it's a really broad area of kind of this circular systems approach. That, if you can really get that, then you get sustainability. I think it's as simple as that. And I feel very, very strongly about that. And so we really are trying, just to answer your question, we don't have that in place right now. We have about 3 or 4 departments in our engineering school that have included the demonstration of life cycle analysis as part of the criteria for their final year project. So at some point within the first 4 years as an undergraduate, you're going to have to learn either through a class or through a workshop or through some online modules, or you could learn it on your own through a YouTube video, but you're going to have to learn how to apply those principles of life cycle analysis. And then you're going to have to show that you can demonstrate it, and that's how you get your grade at the end of your capstone project. But we'd love to be able to expand that to all students. Basically, if you graduate here with a degree from HKUST, that should mean you know what life cycle thinking is, and you should be able to apply it. And no matter what your major, what your degree is, you should be taking that skill set with you.
Yeah, that I totally agree. We do have a course here taught by a faculty, but it's not definitely comprehensive to all the students. That definitely is a key point. Also on accessing data from our facilities, a very important point. Actually allow the students to use our own data from the campus. It's something that we're working with facilities management and engaging with different faculty. We are running out.
We are well over time. Thank you all for staying.
So we need to finish this session, and thank you everyone for being here and to make these wonderful questions and being half an hour almost after the time. Davis, thank you so much. We want you back. We want you here in the campus. I hope, I don't know, next year or when things are opening for you in Hong Kong. It was a pleasure, Rose, great pleasure. And we will continue our own conversations, the three of us, to brainstorm how we are moving our sustainability agendas and supporting each other.
Yes, hopefully we can report back soon on where we are with our climate action plans.
Thank you, everyone.
Thank you so much.
Thanks, everyone.
Thank you very much. Very interesting talk, a very interesting question. Just a few reminders. There is lunch in Building 19, Level 3, and in the library. And the next talk here is going to be at 1 p.m. I hope to see you here. Thank you.
KAUST Research Week is a new opportunity for us to showcase what we do in our research at KAUST. We are engaging a lot more with our colleagues within the Kingdom. We have many partnerships, we have many projects that involve direct collaborations, and this is a great opportunity to bring people to KAUST. So we have a very wide range of activities. We have an amazing lineup of guest speakers for our keynote talks. Our KAUST faculty are also talking about very timely research topics. We cover a very broad spectrum, so we cover the 5 themes that KAUST is developing. So we cover the environment, we cover energy, we cover water, we cover food and health, we cover the digital realm. Getting out there, meeting people, getting into the labs, talking to the young people who are doing science, there's nothing better.
Welcome to day 2, everybody, of KAUST Research Open Week. Today we are focusing on the digital domain. I'm here at the booths again, and I hope to walk you through what KAUST is doing to provide a more sustainable future for the Kingdom and for the world. Come walk with me. I'm here at booth 26. It's talking about extracting lithium from seawater, in particular the Red Sea. And I'm joined by?
I'm Zhenli.
I'm Zhong Xiaoli.
From Xiping Lai's group in KAUST.
Yes, I'm from Xiping Lai's KAUST, and he comes from the Hong Kong City University.
Yeah, I'm a visiting student here.
This is excellent. Yeah. So tell us a little bit about what you're doing here at the booth, Zhenli.
I'm extracting the lithium from the seawater using our membrane. We prepare a lithium selective membrane like this, and it's a kind of critical with the special lattice, and the lattice can only allow the inserting of lithium and rejecting the inserting of other ions, so that if we applied the voltage between the membrane, that only lithium can pass through the membrane, and the other ions like sodium, potassium cannot pass through. It can be blocked by the membrane.
Excellent. So basically, kind of the secret recipe here is the membrane that will be used to allow the lithium to pass through, but nothing else. Yeah. And that's what you have developed in Xiping Lai's lab. But we also have a solar light here, which comes from, I think, your side, right?
Yeah. And during the lithium extraction, and they need the energy, right? So normally people use the electric from the industry and burn something fossil fuel, and it's totally environmental friendly. So from this opinion, we get some silicon solar cell, and they just need to sunlight on it, and they will produce enough energy to drive this reaction and drive this lithium from the seawater side to the concentration side, and this is our work too.
Amazing. So we've got the membrane, which is doing basically allowing the lithium to extract, the solar cells, which is giving power to this entire thing and allowing it to happen. So Zhenli, tell me, why do we even want to extract lithium from the Red Sea?
Because as the development of many electric equipment, for example, the electric vehicles and our cell phones and our laptops, and we need a lot of lithium battery. That means the lithium demand is rapidly increased in these years. So we need to extract this kind of valuable resource from seawater.
Yeah, what you're doing is absolutely excellent. It's very sustainable because you're using the solar lights and the solar cells. You're extracting from right outside our back garden in the backyard, which is the Red Sea. So this is fantastic. And you're extracting lithium, which is needed as it's basically to power, right, for batteries and for battery cells. So thank you both for joining me here today, and thank you for being at this booth.
You're welcome. Thank you.
Are at booth 5. I'm looking at the title. It's called Cryogenic Carbon Capture. So carbon being a very common word these days, especially when it comes to climate change. Good morning, guys. Could you introduce yourselves?
Hi, Nadia. My name is Christopher Wagstaff. I'm a PhD student here at KAUST.
And I'm Anne Antunes, also a PhD student here at KAUST in the CCRC.
With Professor Bill Roberts. Could you guys tell us a little bit about what's going on at this booth?
Of course. So this is a kind of new process for carbon dioxide capture, and we've pinpointed it because it has some real cool advantages over other processes in the field. So this is very much thermodynamics based. We're working with the company SES, an American company, and we've been testing this for quite some time now. We have a lot of hours of
running,
like
troubleshooting.
Yeah. in Kingdom, and we're going to separate ways. I'm gonna say why. Oh, this sounded really bad.
It sounds amazing. No. So it sounds like you guys are capturing carbon at the source, right?
like carbon dioxide intensive sources. So cement plants, power plants, all the big emission sources. And it's really cool because we can basically be integrated in their process without changing anything. So we capture the flue gas that's like rich in CO2, we cool it down a lot, and then this is where the magic happens in the spray tower. So we basically sprinkle a very, very cold liquid, like below minus 120 degrees, and we induce desublimation of the CO2, which means basically the CO2 will freeze, will solidify instantly in the liquid droplets and fall down to the bottom of this spray tower in a kind of slurry. And then we separate this slurry by squeezing it in a screw press. We separate the liquid from the solid, and we end up with kind of solid CO2, like dry ice, which is quite fun to see.
You can see it right there on the screen.
Exactly. And we recirculate this very cold liquid to not lose all of the energy we used in cooling it, and also the rest of the gas that's not the CO2 and was cooled down will go through a heat exchanger and basically cool down the flue gas that's coming in the beginning. And this technology is really interesting because we can end up with a very pure CO2 at the end, like industry-grade CO2 that you can I don't know, use in food industry, eventually sequester in the ground. There's a lot of options. And it's really important for the circular carbon economy. Like the kingdom is really, really focusing in it.
What you're doing is very, very important for the kingdom and for the world as well, right? It's very hard to capture CO2. And you guys are doing that. And not only are you doing that, but you're also capturing pollutants at the source as well. Mm-hmm. And everything is powered via solar and wind. So it's sustainable.
Powering it by solar and wind is definitely an option.
Yeah.
So it can be used kind of as an energy storage system. So you can kind of pre-chill some of your refrigerant ahead of time. And so that's the way it would be integrated with solar and wind.
Excellent.
It only needs electricity. So if you have better, let's say, cleaner sources of electricity, then it's better for the whole.
Why not use it? Yeah.
And it also has several advantages over amines, for example, that are the other main technology in CO2 capture. We use way less energy for the same capture. We don't have to get more absorbents in the process because there's no use of them. And
you don't have to use steam. Usually steam is integrated into the power plant process, but this can be used with wind and solar, where there is no extra steam lying around.
Excellent. What you're doing is very important, and it sounds like it's state of the art. So thank you so much for your time today.
Yeah, thank you, Nadia.
We are at booth number 8. This booth focuses on energy, really exciting stuff, crude to chemicals, and I'm here with
Alberto Rodriguez Gomez. I'm a research scientist in the KAUST Catalysis Center and part of the crude to chemical team in the KAUST, which is a project funded by Saudi Aramco and which represents a breakthrough for the oil refining technology.
Absolutely, it's a breakthrough indeed.
Hello, my name is Tiana Shenkhorova. Currently, I'm a PhD student at KAUST Catalysis Center, and my work in this big collaboration between Saudi Aramco and KAUST is mostly dedicated to the development of catalyst for one-step conversion of crude oil to chemicals.
Awesome. Can you guys tell us what is going on at this booth?
So I will tell some introduction because. So as you may know, the demand for all diesel and gasoline is expected to decline in the next year. So the idea is to use this the most abundant feedstock in the kingdom, which is Arabian Light, to produce other stuff different to the fuels. So what we propose here is a reactor. What we propose is a new reactor concept. Called multi-zone fluidized bed technology. able to process different refining steps in one single reactor vessel and to produce some high-value chemicals like olefins and also aromatics, which are the building blocks to produce some very valuable materials like polymers, plastic, polyethylene, polypropylene, etc., etc.
So we are not going beyond oil. What we're doing is we're taking oil and we're turning it into something else. And you have a one step from crude into chemical that you have developed here.
Yeah, so the most important part here is that normally in the refinery you need several steps to do the whole process, and generally this is focused on the production of fuels. So in this case we are proposing something like a very new technology to take the crude oil from the ground, convert it directly in these precursors for other stuff different to fuels, like the precursors for the plastic and polymers. So this is the most important.
Excellent. Tell us a little bit more about the catalyst, which is very important.
So this all new changes in reactor configuration also bring a lot of challenges for catalyst formulation. So, and we need to have multifunctional catalyst. Why I'm saying multifunctional is because catalyst should be able not only maximize light olefins production, but also impurities removal will be a must. So in that case, we developed our very beautiful fluidized FCC catalyst for one-step conversion of crude oil to chemicals. And also we introduced a couple of new changes in order to improve our heat management in the reactor. So in order to prove the concept, we achieved, okay, can you remove this? At the present, we achieved 35% of light olefins production at lab scale level. So in order to prove the concept and reliability of the system, we have moved to the benchmark.
Yeah, as you say, we already proved the concept at the lab scale, and we moved to a demonstration unit, which is currently working at KAUST. We are operating at this moment. So the idea is that this is we are very optimistic that this technology will go to the industry. So Aramco is already getting a lot of feedback, and I think in the future is very promising. They will implement it in the next generation of refineries.
This is indeed very promising. Well done, guys. Congratulations.
Thank you.
Thank you. Thank you.
Okay, good. I am at booth number 3 with Professor Matteo Parsani. Matteo, how are you?
Good, thank you.
Good. Can you tell us a little bit about what's going on in this booth? I see an airplane, a 3D printed airplane, and I see part of Shaheen, I think?
Yes, it's a blade of Shaheen, and this is an airplane. It's called NASA Common Research Model. It's a model that was released a few years ago by NASA for a call of running a simulation around it and try to understand the aerodynamics and develop a next generation of computational capability to design future airplane that they will appear maybe in 10-15 years from now. Airplanes that are greener, so they pollute less, and are also quieter, because one of the big problems of aviation, many people don't know, it's noise pollution that can create health issue to human, animal, and it's a big problem, especially near the city. And also for a city of the future like NEOM, where we will have flying car, flying taxi, drones to deliver Amazon package, all these things. So it's going to be a big concern. So we are trying to work on this algorithm, implement them in a high-performance solver, and run simulation like this one that you see here, and test our solver, which is going to form the backbone of future computational capability for NASA, for KAUST, for anyone that needs these tools.
Amazing. So you're using our supercomputer here at KAUST Shaheen to develop a technology, simulation of these planes and the aerodynamics around them. And you are actually providing the future for aviation right here in KAUST. You are. You're providing more greener, quieter aviation.
Yes. That's what we are trying to do. This is something that started already 5 years ago, or maybe a few years before that, when I was at NASA as a scientist there. Then when I came here, I continued to work on this. And the big issue here is that, currently there are about 4.5 billion people traveling yearly around the world with airplane. And by 2037, there will be 8.2 billion. So we are doubling it. So the emission of the airplane, they are substantial and they are at a high altitude, so they are even more stronger compared to the same emission at the sea level. So we need to make airplane more efficient, so consume less fuel, reduce the emission, and yes, this is happening here at KAUST. And I'm proud to say that we have some tools that in the NASA 2030 vision, because we have KSA 2030 vision, but there is also a NASA 2030 vision that was released in 2014. They said that we should have this capability around 2027, 2028. And at the beginning of 2021, we have them here at KAUST. So that's why we can do this type of simulation. And with Shaheen, which is the big toys for us, it's something that it allows us to do research. It enables us to do research. Without it, it wouldn't be possible to do what we are doing in the lab.
I'm so proud right now to be part of KAUST and to hear all this. This is amazing. Planes aren't going to go away. We're still going to get on them. And if you're providing the future for aviation, I'm happy it's in your hands. Thanks, Matteo.
Thank you, Nadia.
I'm at booth number 18. Looking at the title, it says Gas Sensors for Pollutants. Could you introduce yourself?
Yes, hi. I'm Hanna Mhanna. I'm a PhD student in Professor Amir Farouk's lab in the Clean Combustion Research Center here at KAUST. And we've done a gas sensor for pollutants.
Tell us a little bit about this gas sensor for pollutants, how it works, maybe a little bit high level, and what exactly is going on here. I see a lot of wonderful equipment.
So the sensor is based on lasers. It actually sends a laser signal, and then depending on the wavelength of this laser and on the species that we want to measure, there will be some interaction between the species and the laser, which results in some absorbance of the laser. And then depending on that absorbance, we will be able to distinguish or to measure actually how much we have from the species that we want. And here we are doing it for BTEC species, which are benzene, toluene, ethylbenzene, and xylenes.
So these are pollutants?
Yes, they are all from the benzene family, very harmful to the health, especially if you work on site, for example, for an oil and gas company, then you are exposed to some amounts of these species daily for a couple of years, right? Then studies have shown that this might cause very big problems, like they might cause cancer or severe lung problems. And the problem with the existing sensors actually is that they are either simple, which can be taken to the site, but then they suffer a lot when it comes to selectivity between these species, because these species have very similar molecular structure, which causes them to behave almost the same to the laser. Then it will be very hard to distinguish between them, and then the sensor might mislead you between benzene and toluene, for example.
So this laser sensor is actually very selective.
Correct. So we aim at having two things here, selectivity and sensitivity. So these characteristics are found in gas chromatographs, for example, which are lab equipment, right? They cannot be taken to the site, sorry. So the selectivity, we achieved it through machine learning, actually. We have trained our sensor on some deep neural networks models that made us able to distinguish between these very similar structures. And then when it comes to sensitivity, here is our measurement cell where it will contain the medium or the mixture that we are measuring. We can just open the valve and then air will enter. And usually we will have windows here and here just for the laser to be transmitted through the cell so that we collect it. But what we have done here is we replaced these windows by highly reflective mirrors so that when the laser enters, it keeps bouncing back and forth inside the cell, causing the laser to travel a much longer distance than what it was supposed to travel. So for example, the physical length of this one is 50 centimeters, while its equivalent length is 1.4 kilometers. So as if the laser is traveling 1.4 kilometers before being collected, and this makes it able to sense very low amounts of these pollutants. So like this one can measure down to 1 parts per billion of pollutants.
Amazing. There seems to be a lot of stuff going on here, like the electrical engineering, there's machine learning, you're working with lasers. So tell me, where would you put one of these sensors? Like where would, in application, where would it be?
Yes, so this laser sensor was actually made for Saudi Aramco. because they care about the amounts of these pollutants on site, because there are now too many regulations on countries and on big companies specifically. They cannot emit as much as they want, and they also care for the health of their people, right? So it was funded by Saudi Aramco to make this sensor for them, to just to use it on site, to monitor the amounts. And it also has another application, which is detecting of leaks, right? Like if you have a pipeline.
Which is very important.
Yes. So if you have a pipeline containing some gases and then a leak happens, what people usually do is they collect the air sample, they take it to the lab, they analyze it to know. But if there is a leak, then it will be too late, right? Then this sensor can feel the leaks. Actually, you can just put it in a car and walk through the site, or put it in a drone. It can be transformed into a small prototype. So here is a prototype for another sensor, for an ammonia sensor that we have done. But this has less components and can be done in a smaller scale, you know. And then it can be put in a drone, just moved around in the site, and then it knows the amounts that we are targeting.
Amazing work. Mahana, thank you so much. Thank you. I am at booth number 7. There's some funky looking fluids going on here. Hi, can you introduce yourself?
Hi, my name is John Gerges. I am Dr. Laurison's lab manager.
G'day. I'm Gordon Wellman, a postdoc in the Sustainable and Synthetic Biotechnology Lab.
Awesome. Okay, so tell me what is going on here. I see a lot of green.
Great. So actually in our lab, we like to say that we're turning carbon dioxide into interesting chemicals. You can think of the interesting chemicals we want to produce as pharmaceuticals, perfumes, biofuels, that sort of thing. And the way we do that is actually with algae. Because algae can use ambient light and ambient carbon dioxide to grow and produce their biochemistry, we like to kind of hijack that mechanism and produce the high-value chemicals we're interested in. So one thing we do is we do a little bit of bioprospecting. So we go out into the Red Sea, find native species that already exist, and we try to grow them in the lab. Native Red Sea species are really good because they tend to be high salinity tolerant, high temperature resistant, that sort of thing. This really allows us to grow the algae without desalinating the water, saving a step. It also allows us to plan for far into the future where someone might try to grow the algae at industrial or environmental scales for their projects.
That is actually happening at the moment, isn't it? There are like large-scale algae farms going on.
Yes, in I think Portugal and California and in Arizona, there's a few of those. I think there's a couple actually planned here in Saudi Arabia, and there's a lot of talk, especially in a room like this, with that sort of project. But I don't know if anything concrete, I can give you a deadline just yet. Yeah, and Gordon will talk to you about scale-up and extraction.
Yes, so after we've identified some interesting species, we want to engineer them to produce more of those valuable products. So in this middle experiment, we have some culture growing from our lab where we'll be adding a small layer of oil on top, and as the cells produce the compound, it flows up into the oil, and then we can extract the oil and remove the chemicals that we want.
Amazing. And I think this process as well is very good for the circular carbon economy because you are reusing CO2, right? And then you're making products like, okay, let me think, if I remember correctly, tires, like car tires, perfumes. Give me some more.
Biofuels, so Kyle has previously produced bisabolene, which is one chemical step away from diesel. So we are that close to producing something that is quite popular out of algae, for example.
With the Formula One this weekend, you might need to go talk to McLaren.
Yeah, we absolutely should.
Excellent job, guys. Thank you so much.
Thank you.
So hi, we are at booth number 2. I see a massive sink in front of me. This is exciting. Please introduce yourself.
Hello, I am Abdulwahab Filimban, a PhD student in the Information System Lab here at KAUST in Professor Tarzan Nafouri Group.
Excellent. Abdul Wahab, can you tell us what's going on with this sink and this tap?
Okay, this is a smart tap, a replacement for infrared taps. It have a better response compared to infrared taps, so it works smoothly compared to the infrared taps. Okay, now it's running. You can see that it's way smoother. And not only that, it also detects the exact movement you are doing. So in the use case of wudu, which is a Muslim's ritual of performing ablution, we do different actions, and there's a different need of water for different actions. So for someone who collects water, we can dispense less water less water flow compared to someone who's washing his hands. So this makes our tap smarter. It makes the response smoother, nicer user experience. As well, we save water.
Excellent. So currently there are sensors already in taps, but I think this is taking it to the next level. You're bringing AI in to bring in this algorithm that's going to show how people will, how much water people actually need when they're making wudu, right?
Exactly. So the current existing solutions have some limitations. We spotted those limitations, like the delay in turning it on, the delay in turning it off, and we are trying to solve those issues using AI in a next generation technology tab. So by that we can have a smarter tab, as I mentioned, and solve those limitations.
Amazing. I don't know how many times I've gone into a bathroom, you know, and you like try and get the sensor on, it doesn't go on. The minute you walk away, the tap starts going. The one thing I wanted to say to you about your smart tap, which is very smart and very amazing and definitely state of the art, is that I want you to try and utilize more females doing wudu. So you can make sure that the AI is capable to learn the mannerisms of a man and a female and a child making wudu.
Exactly. Currently, we collected a small data set to test our algorithms, and we collected around 300 videos of people doing wudu in different ways. But there are many different ways people do wudu in. And there are like diverse people who do it. Children, women, even men themselves, they do it in different ways. So we need to collect that diversity in our data set and scale it up in order to improve our model and make it work in a generalizable way to everywhere.
I'm looking forward. I'm looking forward to the future where you're making the world a more sustainable place by, with conserving water and making the way people make wudu smarter. Thank you so much, Abdul Wahab.
Thank you very much. Thank you.
Good afternoon and welcome back to the auditorium. The afternoon session is about to start, and please let me welcome on stage Professor Donald Bradley, Vice President for Research.
Could I ask the people at the back to come further forward so you can be more part of what's happening? I think if that would be possible. So my name's Donald Bradley. I'm the Vice President for Research at KAUST. It's my great pleasure to introduce our second keynote speaker of the day, Sir Peter Knight. Sir Peter is an emeritus professor and senior research investigator at Imperial College and is renowned for his research on quantum optics and quantum technology. He's also served the UK in global science through many leadership roles. He was the first president of the Optical Society of America to hail from outside of North America. He's a past president of the Institute of Physics and was chair of the UK Defence Scientific Advisory Council. Currently, he's the editor of Contemporary Physics, chair of the UK National Quantum Technology Programme Strategic Advisory Board, chair of the Quantum Metrology Institute at the UK National Physical Laboratory, and a UK government science advisor. Peter's research and organisational prowess has been recognised through being knighted for his work in optical physics, being elected to the Fellowship of the Royal Society, being awarded the Thomas Young and Glazebrook Medals of the Institute of Physics, the Ives and Walther Medals of the Optical Society of America, the Faraday Medal of the Institution of Engineering and Technology, and the Royal Medal of the Royal Society. So Peter will talk to us today on the topic of quantum science as a transformative technology. Please join me in welcoming Sir Peter.
Thank you, Donald, for those very kind words, and greetings from a very cold and snowy England. Right, so I'm going to tell you something about what's going on around the world in terms of exploiting some of the odder features of quantum physics in order to generate new technologies. And what I've done is to pull together what's going on right around the world, but with a bit more of an emphasis on what we've been doing in the UK. All right, so let's see if this slide... Yep, that works. Whoops, that worked a bit too quickly. Okay, so here we go. If you look at the way that information technology has progressed in terms of ability to do computation, for example, if we look right at the very beginning in this slide right at the top, a fully programmable electronic computer, ENIAC, in 1947. Then to, for example, the Pentium 4 chips. What we see on this graph, this is due to Roger Keyes from IBM, is the number of atoms that were involved in actually manufacturing a gate, basically, a thing that will be a switch in the logic elements. And Roger's graph of this, a kind of Moore's law shrinkage of making things smaller and smaller. Roger was predicting that by 2017, we're hitting a kind of wall where it looks like we're very close to one atom. Of course, there was progress in information technology. Moore's law persisted a bit longer than that. But if we look at the progress towards getting things to atomic scale, we immediately have to think about what happens in the world of quantum physics. So here we've got a portrait gallery of some of the founders of quantum physics, from Max Planck on the left-hand side, right through to Schrödinger on the right-hand side, and pulling in all the key individuals, Einstein, Bohr, Heisenberg, Born, Paul Dirac, and so on. And a lot of what they were focusing on is the way that we could use the superposition principle of coherence. And that's precisely what we're going to be looking at during this talk. Okay, so the quantum world is really highly counterintuitive. Obviously, if we look right at the very beginning, quantization led to discrete energy levels. The idea that one would get transitions between these, and that's what led to basically a lot of what we take for granted in modern technology, lasers, semiconductors, and so on. Another feature is the wave nature of matter, that all objects will actually have both a particle characteristic or a wave characteristic. And as things become colder and cooler, for example, you might well see this wave nature exhibit itself. The next part of it is superposition, a highly counterintuitive thing where you can put systems into a superposition of both here and there at the same time. So if you imagine a classical bit, which could be in a state 0 or a state 1, in quantum physics, you could put it in 0 and 1 simultaneously in superposition. And when you make a measurement, you get one or the other as you get this collapse onto one of the measurement outcomes. And the final ingredient for this is entanglement, the idea that there's a connectivity between separated quantum systems, and a measurement on one immediately affects the wave function, the state of the other. So there's the progress: quantization, wave nature of matter, superposition, and entanglement. And what we're going to see is, as we go down that ladder of things, the way we can exploit things in new technologies. Okay, so let's think about these things with Schrodinger's machines. And I'm going to make a little plug here for something. On the left-hand side, we see Schrodinger. And Schrodinger talked about one of the key mysteries of quantum physics, the idea that one has the idea of these entangled states. Okay. Now, if you did this, could you make a quantum machine? All right. Can you make one? And that's what I'm going to describe, that journey. And there's a connectivity here. On the right-hand side, this picture is my colleague at Imperial College, Terry Rudolph, actually my successor in the end in my chair at Imperial. And what Terry's doing is actually realizing one of these Schrodinger machines. And it's a kind of family constraint in a sense, because Terry Rudolph is Schrodinger's grandson. So what we're going to see is this journey, almost like a family journey in this particular example. So most people, when we talk about quantum technologies, think we're going to be talking entirely about quantum computing, and we're not quite that. What we're going to be looking at is the way that we can take quantum systems, bits, for example, put them in superposition, and look at ways in which you can exploit that. And within that funnel of things, from the immediate right through to the intermediate development to a long-term development, you can see quantum computing is a distant journey. It's really tough. But en route to that journey, there are a number of things involving, for example, atomic clocks, quantum communication systems, quantum sensing systems, which will evolve in that journey where there is a technological advantage from exploiting these. And in this funnel, which we identified when we started the UK program, lots of things that we knew would have an immediate benefit without losing sight of that long-term journey. Okay. So what have we done in the UK? At the end of 2013, a group of us managed to persuade the UK government that this wonderful advance in quantum science that we've seen would enable us to start thinking about new technologies. And what we were able to do is to persuade the then Chancellor Exchequer to actually invest completely new money. At the time, it was 270 million to initiate this. And what we focused on were these topics here on this slide: compact atomic clocks, for time stamping, for GPS resilience, and I'm going to talk about that, quantum metrology and sensing, quantum secure communications, quantum simulation, of course, and quantum computing. And what we ended up with is basically forming 4 hubs, headquarters for the coordination of this activity, but involving over 30 universities working collectively together with a common goal. We brought in government labs and over 100 companies were engaged. The company engagement was really facilitated by something called the Challenge Fund, where we actually committed very substantial resource to industry-led projects which were enabling this technology to actually be realized. And you see in this pie chart a whole raft of breakdowns of what we're doing in terms of computing, in terms of the components that underpin everything, the supply chain, if you like, communication, sensing, and so on. Right, so let's talk about qubits and registers, for example. I already mentioned that if you have a classical bit, it could be state 0 and 1. In quantum science, you could certainly realize 0 and 1. It could be spin up or spin down. But you can actually do stuff where you could put them in this superposition of 0 and 1 simultaneously. So if I imagine a really simple 3-bit register, there are 8 potential states, 0, 0, 0, right through to 1, 1, 1. And of course, in quantum physics, if you can put a bit into a superposition, you can put the register into superpositions as well. All of these 8 possibilities simultaneously. And it's that massive parallelism that gives you the ability to do things which you couldn't previously do. Now, I've stolen this slide from John Martinez, who led the Google effort at the time in quantum computing. So I've got this quantum bit I can put in a state 0 and state 1, and I can put it in a superposition. But if we're going to do it with that one, what about an array of them? Okay, so here's 2 of them, and there are those 4 states. Okay, but now if you look at what happens if I have n of these things, it generates enormous, incredibly rapid acceleration in the number of states you've got accessible. So if you have 50 of these things in superposition, that already gives you the state space which is exceeding a supercomputer. If you have 300 in superposition under control, there are more states than there are in the visible universe. In other words, it's bigger than anything you could actually manufacture classically. Right, so that's the vision. What's the reality going to be like? Well, let's talk about this oddity of quantum physics. And what we need to do is to make sure that really jumped a bit. Let's see. Right, imagine a situation where we're going to take quantum particles of light, photons, and a beam splitter, and a detector that looks at the reflected photon, a detector that looks at the transmitted photon. So which way? And of course, photons are indivisible. It'll either go that way or that way. Okay, so which one clicks is going to be probabilistic. Okay, so there we go. Inject a single photon, and because it's probabilistic, the beam splitter acts as a kind of classical coin flip, randomly sending each photon one way or the other. A 50-50 beam splitter gives you a 50-50 split of that kind. Okay, well, is that all that happens? Is it just probability? Einstein's God playing dice? Well, who knows? Let's look. Here's my source. Here's my beam splitter. Now what I'm going to do is recombine those 2 paths with another beam splitter. Now, of course, if we take this idea that a beam splitter is just a 50-50 probabilistic splitter, what one would expect, again, at these 2 detectors at the top, is 50-50. That's not what happens. Properly aligned, all of the photons arrive at the top. Or properly aligned in a different way, all arrive at the side. So adding probabilities is wrong. We see in quantum, quanta interfere, and it's that interference that we want to be able to exploit. Right, so it's all very well with photons interfering, but what about atoms and atomic waves? Okay, so if I take some atoms and I cool them right down, and you can cool them down by laser cooling, It's a bit like slowing down a bus by throwing snowballs at it. Eventually, it will slow down. Okay, so we'll do laser cooling. And eventually what happens is that as they cool down, their wave characteristics become more observable. And eventually what happens is those wave characteristics dominate and you end up with a matter wave. And just like a light wave, matter waves interfere. If they interfere, we can build interferometers with them. We can build structures that guide these atoms, and they can be used, therefore, as an interferometer to sense rotation, gravity gradients, and so much more. And we're going to be exploiting exactly that in some of our new technologies. Right, so one of our focus in the UK program, and similarly around the world, quantum sensors, quantum timing, quantum imaging. New time standards enable us to actually work on the ability to proceed, even if you can't see the GPS constellation of satellites. You can build a navigator that way. You can build accelerometers, gyros, gravimetry. You can do so much more. You can, and I'm going to describe some of these things in this list, including the ability to see without being seen. This poor person here, which looks like they're being tortured, that's a brain imaging helmet. And I should explain exactly how that is transforming brain imaging for surgery. Right. So, gravity sensing. These matter waves, these atomic cold atoms in an interferometer, have the ability to sense gravitational field changes. If you can do that, you can do a great deal in terms of infrastructure productivity. You can look at a whole raft of things where the whole surveying side of things and the inspection of what's there is actually extraordinarily difficult in terms of conventional surveying. But these atomic sensors can detect what's under your feet. You can see the invisible. You can do stuff down in pipelines, for example. You can do a lot more on situational awareness. Is there a tunnel below that you didn't know about? So, I mentioned this helmet that person had on is monitoring brain electromagnetic imagery. This technique is called MEG, magnetoencephalography. And what we have is the ability to build an array of very small atomic magnetometers in a helmet that will monitor the electromagnetic activity within the brain. It's extremely high sensitivity. You get good spatial resolution, and you can adapt it to fit any head size, and that includes children. Children have a habit of running around when you're trying to do brain imaging. This is the sort of thing that really will transform the ability to do these brain scans. And in fact, you can use this to aid surgery. And the University of Nottingham that lead this work have got a spin out. They've manufactured these things. And that MEG helmet that we showed you is already being used in hospital for MEG-guided epilepsy surgery. So incredibly rapid adoption from the first signs of a new technological opportunity, a capability, into being deployed in healthcare. I mentioned GPS, and of course we all rely on GPS. It does so much. Traditionally, people regard it as very much generating the way that your sat-nav works, and that's true. That basically there's a constellation of atomic clocks. These atomic clocks that your system can see, that gives you the ability to actually work out exactly where you are. That's not all it does. It provides timing accuracy around the world. And a great deal of the world's economy depends on seeing the GPS constellation in order to do stuff which synchronizes activity, from fintech right through to the ability just to get gas from a filling station. Right. So the problem about GPS is that it's extraordinarily vulnerable. The signal from a satellite, by the time it gets to your receiver, is tiny. It's easily spoofable and jammable. So we need to find a way of generating a resilience so that we've got a backup system. And some of the new quantum technologies involving new clocks will enable us to do that. So not just new clocks, but also the ability to navigate without any GPS at all. So what do you need if you want to navigate without seeing the satellite constellation? Well, you better have a clock. Secondly, you really need to know where you are, your starting point. You need a map and so on. And then you need the ability to measure rotations and either velocity or acceleration. So we have a consortium in the UK that's developing this. Now, there are other consortia in the United States and in France developing this. This one that I quite like is a collaboration between Imperial College and a company, M Squared, building exactly one of these test navigators without having GPS. Okay. What about imaging? Well, of course, if you think about laser ranging, for example, that's ubiquitous. Any construction site uses laser ranging. Basically, the time for a laser pulse to actually be emitted, scattered from an object, come back to you to be detected, gives you the distance. But we can do something new now. We can make light, quanta of light, in pairs. One of them triggers your timing, the other one is sent out and comes back. So if you've got ranging with timing, you can do something else. Okay, I'll give you some examples. More surprising one, the ability to see around corners, for example. Right, so here's the engine that we have. Okay, the engine that's used by essentially everybody in this field is called parametric down conversion. A high energy ultraviolet photon or a blue photon is entering from the top left. There's in the center, in the optical mount, there's a crystal, and that down converts into a pair of photons. They're twins, highly correlated in an entangled sense. So what can we do with these? Okay, so first thing you can do, and this is always a surprise to people when we describe it, is you can use a very curious thing called ghost imaging. So my ultraviolet light comes in from the left. There's my nonlinear crystal, and then we get a red photon. It could be the infrared, for example. Infrared is really hard to image. Cameras tend not to like infrared. There's my object that I want to image. But what I'm going to do is these photons are twins. What happens to one, the measurement effect on one affects the other. And we'll have a storage line and then a camera. Camera is looking at the blue photon. Visible photons, dead easy to actually measure. Light comes in, there's the object. Okay, over here we've got a bucket detector. The bucket detector gives you the timing information to the camera to say, we just detected a red photon, you better know that there's a blue one coming. If you don't detect one over here, and you detect one over here, that tells you something. And by doing this, you can actually build up an image in this camera of an object that light never saw. That's why it's called ghost imaging. It's rather surprising. And it's simply because these are born highly correlated, and we're using that correlated information to drive this imaging. It really does work. Surprising, but true. Okay. So how do you use this to see around corners? You have a source of light. Okay, it sends out these photons go out, scatter a spherical wave. There's an object. The object re-radiates spherical waves, and you can see around the corner. And in the UK program, we built cameras that can detect humans, for example, around a corner, about 50 meters standoff distance. And if you use machine learning on this as well, you can identify from behind a wall with a pretty good accuracy. So you can see there's lots and lots of reasons why that's going to be of value. Right. Now, what about information moving? Codes, basically, where you actually secure your information. And basically, this is the business of ciphers. In 1918, the Vernum cipher was devised by Vernum and Moborg, and basically it's a one-time pad. What you do is you encode your plain text into binary and use a rule, some sort of algorithmic rule. Okay, and then you combine it together, and the recipient is the only other person sharing the key, the rule, if you like, and can recover the plain text. And what Claude Shannon proved in the 1940s is that the one-time pad is provably secure. It's actually the only cipher system that's provably secure, but a lot of provisos. Keep the key secret, same length as the message, truly random, whatever random means in this space, and you never reuse the key. So how do you establish the safe shared key? Because an eavesdropper can grab it. So this business of secure codes is very much part of the new generation of quantum technologies. So what can we do in quantum science? Well, firstly, you can't make a measurement on a quantum state without disturbing it. That gives you the ability, therefore, to detect unwelcome eavesdroppers. Secondly, you can't measure all the properties of a single photon, extract all the information from it, and then transmit an exact copy of the photon. That's sometimes called the no cloning theorem. Okay, that means that you can't really do a man-in-the-middle attack, measure the photon, and then transmit a copy of it. Those two combined means that you can build ways of transferring information where you can certainly know if anybody, an eavesdropper, is trying to extract the information. And you can either disregard keys when Eve's listening, or you can use entanglement, where you can actually see a piece of the key being destroyed because there's an eavesdropper. And these are the two key protocols. BB84 after Bennett and Brassard. The entangled one is the Eckert protocol. And they also provide you with various countermeasures for eavesdropping, but also deliver weaknesses that you need to actually investigate. So quantum security use a shared random number to develop a one-time pad, for example. Now, classical physics isn't random, so you could use quantum, which has this provable provision of entropy. And then you've also got this problem of authentication. How does Bob know that Alice is Alice, and how does Alice know that Bob is Bob in terms of the traditional senders? So these are the key things we need to identify. Authentication. Okay. So I borrowed this slide from the Optical Society, where this is Alice and Bob, and they're sharing pairs of quanta. This is basically the Eckert protocol. And any eavesdropper that comes along is going to disrupt this entangled sharing, so that by measuring on one of these things, you're really disturbing the system. Alice and Bob will be able to detect it immediately. Okay, so what can we do, therefore, in terms of producing a cryptographic toolbox which is quantum safe? Well, you can use quantum random number generators. Products in this sense are already available on the market from research groups that have bounced out of universities into startups building quantum random number generators. Another way of doing this is to provide what's called a quantum resistant algorithm, and I better describe later on why quantum gives you the ability to do something different, and I will. And there's quantum key distribution. These are the various parts of the toolbox. Okay, so why do we need this toolbox? Okay, and what would we use it in? So if I go back to some of the really early stages, the first use of established communication networking was done in a collaboration between the group at Malvern, led by John Rarity at the time, and the group at British Telecom, led by Paul Townsend at the time, where they were able to do this quantum secure communication on established fibers around the network around Ipswich, where British Telecom have their research headquarters. That was a pioneering work, and it's been used by a whole raft of people since then. But the Townsend and Rarity protocol was actually the first demonstration of this kind on a large-scale network. Okay, so you can build long distance ones, and here's one that we've established in the UK between the British Telecom labs out in Suffolk through the various parts of the installed standard telecoms network to Cambridge University. That network with trusted nodes, which actually, you've got a limit on how much you can send photons down fibers without getting undue losses. So you've got boosters, things. These are called trusted nodes. Off it goes to here. Okay, and you always can detect the presence of eavesdroppers because the bit error rate increases in a detectable way. Right. One of the most important advances in this area was led by China in two different directions. Firstly, building an enormously long network, across China with 32 trusted nodes, 1,240-mile optical fiber route. So that was a huge development of the fiber communication system. And also, really impressively, building a satellite link where you can do a single hop, not down miles and miles and miles of fiber, but one hop to a satellite down to here between Beijing and Vienna. So that was done. That was the Messier satellite, and it was launched and worked in 2017. Now, if you do this, you've got to be really careful that you actually operate the hardware appropriately. Human factors, side channel attacks, and so on could render this useless unless you've got real confidence in your design engineering. Okay. Now, what is this business about a quantum attack, though? Okay, there are some things that are quite decidedly easy, and there are things that are decidedly difficult in mathematics. For example, in this middle of this complexity diagram, P, these are polynomial problems. Fairly easy to do, easy to check. Multiplication is an example. And then there are ones that are harder and harder in these complexity classes. Okay? So problems in P, the polynomial ones, they're solvable, they might take effort. These bits in NP, you might get a solution. It's going to be tough to get that solution, but you can check it using polynomial resources. An example of that is factoring. Factoring is really hard. Okay, it's NP. But checking you've got the factors right is easy, it's multiplication. And then there are horrible things out here that are exponentially hard everywhere. Okay, so what can we do? So if hard's always hard, no matter what, there's a thing called the Church-Turing thesis. Okay, this is Church and Turing. And they tell us that all reasonable models can be efficiently simulated by what's called a probabilistic Turing machine. If it's hard for a probabilistic Turing machine, it must be hard for any other. So it doesn't matter whether you're using a really clunky, old-fashioned, restricted ability computer versus a supercomputer. What's hard's hard. And that used to be a golden rule of computer science. Okay, a computational problem like factoring is intrinsically difficult, independently of how hard we try to find an efficient algorithm. Okay, and then quantum mechanics changes all of that. How does it change it? Well, Feynman, back in 1982, pointed out that quantum systems are very hard to simulate on a classical machine. State space just grows exponentially, and therefore one should use a quantum machine to simulate quantum things. David Deutsch, in 1985, gave you the first algorithm to show that you can do things that a quantum machine could find fairly easy. A toy model. But it was Peter Shaw, then working at AT&T and Bell Labs, who pointed out that you can now use this parallelism of quantum mechanics to do something really dramatically different. What was considered to be hard, factoring, becomes easy with a quantum computer. It's called a quantum Fourier transform. In other words, this central tenet of information theory that hard's always hard is now completely disrupted. Okay. All right, so there's the Feynman idea. I've already spoken of that. I'll skip that, therefore. Okay, quantum. Okay, too many builds on this one. So quantum computing, quantum simulation, is a model that certainly violates this strong Church-Turing thesis. What does that imply for us? If you can build a quantum computer, what can you do? Right. Well, one thing you can do is generate what I've been calling a crypto apocalypse. All of our information security and e-commerce are based on the use of NP problems that are not in P. In other words, it must be hard, not in P, so that security is unbreakable. And there are assumptions about your algorithmic capability. But what a quantum algorithm does is it breaks this Church-Turing thesis about hard always being hard. Okay, if you can do that, then you can start to break a great deal of what we do in terms of resilience of the information security based on hardness. Now, quantum computers of substance might be a decade away, but it's going to take us a while to do all of these things. So the lessons that we've learned, algorithms and complexity classes can change. And security assumptions of what's hard and what's possible, you better be convinced about their validity. Okay, so to illustrate this well, my colleague Michele Mosca in Waterloo in Canada has come up with a simple expression of this. How long does your information require? How long is it required to be secure? Let's call it X. How long is it going to take to retool our infrastructure to be quantum safe or resistant to a quantum attack? Let's call that Y. How long till a large-scale quantum computer is built? Let's call that Z. And Mosca's theorem is that if X plus Y is greater than Z, you better start worrying because you've got this overlap period where your information is not going to be secure. And that's been the trigger, a driver of so much. So a lot of what we do, we secure our information using a protocol called RSA. RSA depends on this inability to factor. So RSA 200 is this big number on the top left, and there are its factors. Finding those factors is extraordinarily hard on a classical machine. It could take a very long time. If you worry about it, you increase your key size, your RSA number. Could take the age of a universe. But as soon as you have a quantum machine using Shor's algorithm, then it's polynomial time, not exponential time, and you can crack these things in minutes. Okay, so there's an example. There's a large number, and that's its factors. Okay, that's how difficult it is, but on a quantum machine, it's not difficult at all. Okay, so if I build a quantum machine, what's it going to look like? Okay, just to remind you, that's the first ever transistor. Pretty clunky. The progress from that to chips was a hell of a journey. Right, so computation is a physical process. Okay, hardware's physical. What's a quantum computer look like? I can't resist this quote. Okay, this comes from Popular Mechanics. Okay, so quantum computer might weigh no more than 1.5 tons. Sorry, that's a classical computer. That was in 1948. What a quantum computer does at the moment is that it certainly weighs 1.5 tons. And I'll show you some examples. So Schrödinger's engine is going to use this ability to actually put things into position of two places at once, two different places. And the number of states that you can access grows exponentially. It's just 2 to the n. It's like a massively parallel machine. Now, there are lots and lots of algorithms that exploit this. They're listed on this thing called the Quantum Algorithm Zoo. Okay, a lot of the things in the algorithm zoo are only of interest to computer scientists, but there's some really useful ones, variational eigensolvers, that are going to be useful, for example, in quantum chemistry. Right, so let's have a look about this. This towards generating a quantum advantage. Sometimes this was, in the past, that was called the quantum supremacy challenge. And we're all trying to avoid this supremacy word now. Okay, so here's the Shor algorithm, where you get this change from an exponential resource size in terms of the ability to do things as a function of the number of bits. So a big advantage. There's another algorithm due to law of Grover, which is a database search where you see basically a quadratic speed up. And there are things called quantum annealers, and you can buy one of those from D-Wave in Canada, which will do interesting annealing and optimization. Okay, so depending on your algorithm, your advantage depends on the number of bits that you've got, how well connected they are, and they're all very susceptible to noise. Right, so if I go back to 1996, when people started to look at early implementations, there was an enormous chasm between what experimentalists could generate, 10% errors typically, compared with what theorists were demanding in terms of a threshold to do stuff. So how long is it going to take to close that 10 to the 4 gap? Nobody really knew, but a lot of people guessed. Some people said a few years. That was me, basically, for example. Some said many decades, and pessimists said never, it's going to be impossible. So how long did it actually take? Well, 20 years. Theorists found better and better, more practical ways of protecting the qubits and using them. The experimenters massively improved the levels of control possible. So that gap is now closed. Okay, so we can begin to do a few useful things with quantum machines. What are the candidates? 2 leading candidates: trapped atomic ions manipulated either by electromagnetic fields or by light, and superconducting circuits at cryogenic temperature. Okay, and basically these are the 2 leading candidates, and there are others as well. Okay, large investments coming in, centers of excellence in this in Oxford, and there are companies like IonQ. IonQ is Chris Monroe's spin-out, which is now raised over $1 billion in fundraising. Honeywell, another example of this, with a large fundraising. Superconducting ones, basically led by IBM, Google. Rigetti, which is a spin-out, Chad Rigetti led when he left IBM, Oxford Quantum Circuits. They're the 2 vehicles for making a quantum computer. So let's have a look at this. Okay, here's a chip. Actually, it's an artist's impression of a chip called the Sycamore chip, which Google built. Okay, and it had 54 qubits. That, in principle, will give you 10. Well, you can see 2 to the 64. A huge state space. In fact, they only used 53 qubits because they had extremely good control and diagnostic systems on their chip. They had 1 noisy bit, they could turn it off. Okay, compare it with the largest machine that was then available, IBM Summit supercomputer. Okay, you can see the state space comparability. Right. So there's the result. They call it quantum supremacy, which we try to call it quantum advantage now. It was doing a random number generator algorithm. It took 200 seconds. Google reckoned that it would take 10,000 years to produce it as a similar result on the Summit supercomputer. IBM, who built the Summit supercomputer, said, no, we can optimize it to do it in 2.5 days. I don't think that really is much of a criticism. Firstly, they didn't do it. And secondly, this is 200 seconds versus 2.5 days. All right, so where are we now? Okay. We've got this mountain we have to climb to do lots and lots of calculations without the thing falling over through noise. Okay, so what we have in this complicated graph is a logarithm of the number of quantum bits we've got. Okay, and here's the error rate. Okay, so here's horribly noisy ones, here's pretty good ones. Okay, so where are we? And there's lots of little data points down here which really tell us that we're in the foothills of this mountain. If you've got really noisy qubits, increasing the number of qubits doesn't give you any advantage at all. Basically, the calculation stops because of noise. If you improve the qubits better, if you make them better and better, you can start to climb up this mountain. So as soon as you get to a reasonable number in here, you can start to think about correcting errors. Okay, it's quantum error correction, which has a really large overhead on this one. So these data points were provided by my colleague David Lucas in Oxford, but the graph is from Andrew Steen, also in Oxford. Okay, so if I blow that bit up, you can see where we are. We're right down in the foothills. So here's the Google chips over here. They are really noisy, okay? The ion trap ones are less noisy, okay, but there are fewer qubits. So what are we going to do? If we got this middle range where we got 50 to 100 qubits, what can we do? Right over here, we want millions of qubits to do things with error correction, but they're a bit more distant. Okay, so are we any prospect of actually making things better? Well, there are. In fact, there are two quantum versions of Moore's law, both acting together. Hardware is getting better and better. Okay, and this is on a log scale. Hardware is getting better and better. Superconducting and trapped ions, both getting better and better. The demands from the algorithm designers are getting less and less demanding, also on a log scale. So you've got this double log advantage in the ability to make good qubits and to be less demanding on how you use them. And that gives you some optimism that we can do things. So where are we now? As I said, trapped ion, superconducting. Okay, so there's a chip design. And in fact, this is the Chinese chip design, which actually did better than the Google chip in terms of doing this, but basically a 10 to the 3 enhancement over the Google result. Okay, these things are called noisy intermediate scale quantum machines, hundreds of physical qubits. There's no error correction really, but can you do things in terms of very early quantum simulation? The answer is yes, you can. Okay, so fabrication of these kinds of things, both for superconducting and in trapped ions. The UK is involved in each of these things. The US and China is the lead on superconducting. The US, the UK, and China are the lead on trapped ions. Okay, and whatever these things are going to be able to generate, they'll be running them together with high performance classical computation. And by combining them with machine learning, you can do a whole raft of optimization, things involving quantum chemistry and so on. So that's a rather busy slide. I'm going to skip it. In fact, it's too busy. Okay, so something I'm rather fond of, which is building a modular structure. What happens if we start to scale these things up is life gets a bit crowded. So building modules that can talk to each other. And quite a long time ago, I worked on some of these ideas where you could have a qubit over here and a qubit over here. And by doing a beam splitter operation, you can remotely entangle these things, even though they might be in different labs, for example. And that's certainly been done. The Oxford group have got high fidelity entanglement of ions via a fiber link in 2 different places. And you can imagine now scaling this up with a whole load of quantum modules talking to each other via these kinds of beam splitter attacks, sometimes called Bell state measurement, remote entangling. So scaling is not easy. You can imagine the modular structure. And that's a lot of people are looking at these modular structures, or you can build something that's massive and monolithic, and that's the approach that the Sussex group in the UK, led by Winnie Hensinger, is dealing with. Or you can do something completely different, which is to use photonic beam splitter arrays on an optical chip. And the experimenters at Bristol and the theoreticians at Imperial came together to form a company called PsiQuantum. This is Terry Rudolph and Jeremy O'Brien and others. And PsiQuantum is now valued as a startup at over 3 billion. IonQ, which is the Chris Monroe spin out in Maryland, raised a couple of billion in an IPO. Okay, so here's how we're spending our money in the UK. So basically, that initial 270 million I mentioned has grown now to about £1 billion. The biggest single part of it is collaboration now with industry. Okay, that's that big slab, the orange color bit. We have these hubs working on with doctoral training system, building the skill base, the National Quantum Computing Center, which we've established, the Quantum Metrology Institute at NPL, and so on. So we've got about £1 billion. We've got collaborative work, for example, with Singapore on a satellite experiment, and also with Australia and with Canada. One of the things that I was quite proud of is the fact that we actually managed to pull in a great deal of strength right across the nation. I mentioned the 4 hubs, plus the National Quantum Computing Center. And what we've been able to do is to involve universities right across the nation, bringing in a collective effort, which means that we can really develop stuff. Now, if we go back to 2015, working with The Economist magazine, we looked at the spend worldwide, okay, in the non-classified part of what was going on. A big push in the United States and so on. The European total investment was also very substantial. Okay, how's that changed now in the 6 years? Okay, well, it's fairly easy to understand what's happened. The United States have actually increased their expenditure through the National Quantum Initiative, but China is really accelerating their activity in this space. Okay, so led by a very able team with leadership led by Jianwei Pan, they're building a major investment, a 10 billion investment, in fact, in Hefei. So this is the Hefei headquarters, with goals to look at quantum metrology and also quantum computing. Right, so this is my final slide. I hope I've demonstrated the spectrum of activities where quantum coherence can be exploited in sensors, in imaging, in timing, but also in computation. I think it is transformative. There's a huge amount of activity around the world in this space. Accelerating push in terms of quantum computing it's enormously exciting. Some of the brightest young people really are engaged in this now. Now, it's worth bearing in mind that you can't really do everything yourself. Trying to compete on every front with every nation is impossible. So how do you focus things? How do we engage with each other on this one? These are things that we're developing. But I hope I've given you a sense of how really exciting this is and how counterintuitive the quantum world is, but really does affect new capabilities in technology. Thank you for listening.
Thank you very much, Peter. We have time for a few questions. Do we have some questions from the audience? Anybody? Please.
Thank you. Thank you for the very wonderful talk. I really learned a lot. I only wish this was at night, and then I could go home and say, I saw the night at night at night. Yes. Okay, so my understanding is quantum computing is going to change the way we live and change the way we do a lot of things. In our lifetimes, we've already seen the internet change the way we live, we work, and we play. And in hindsight, we see perhaps humanity was not as well prepared for the advent of the internet because the tools and the power in our hands also caused us to spread hate and, spread fiction instead of fact and violence. With the advent of quantum computing, what things do you think we should focus on right now in, for example, psychology, sociology, philosophy, and learn more about so we can be prepared and we can blunt out the rough edges, if I may, of quantum computing that may arise?
Donald, I wonder if you could that was very bad connectivity for me. Could you summarize that for me?
Yes, so I think the question basically was, there are many developments in technology that then lead to unintended consequences in terms of social interactions, in terms of development of society. And I think the question really was, are there any problems potentially with the adoption of quantum technologies and quantum computing that we should be thinking about today so that we can address those ahead of them arriving?
Right. That's a really excellent question. And yes, I think a great deal of work is underway involving the general public and people from other disciplines in understanding what the ethical natures of all of it, what impact will it have on things? So in terms of privacy, for example, if there's an ability to do so much more in terms of surveillance, do we worry about this? What should we worry about? The biggest single thing, of course, is that we've got used to the fact that we can trade and do e-commerce and rely on secure communications using RSA. And as I tried to demonstrate, RSA is extremely vulnerable to a quantum attack. And that means all the things that we've got used to in terms of secure e-commerce and information technology, all the things we've got used to when we use HTTPS, that confidence will go, and it will go quite soon. So the ethical constraints there are considerable, that finding a way of defending your privacy in that sense is important. And that's why there's a great deal of work underway, not just on quantum communication security, but also in quantum safe encryption. I mentioned also the ability to do things like the single photon imaging, which also give you the ability to do a great deal on surveillance. So there's a lot of dialogue on it. What we've tried to do in the UK, and others around the world have been dealing with this, is to start thinking about ethical principles, of trying to hear from the public what could happen in this space. We've learned a lot in the past when things went wrong, for example, in the worries about genetic modification of foods. So involving the public at a very early stage and hearing them, not just telling them, but hearing them, has become quite important. So all of these things, in terms of, if you like, citizen access to some of this, has become quite important. I'd like to see a lot more of it.
So there was a related question in another talk earlier today, Peter, which Eran Tean gave from the National University of Singapore. And the question was basically about whether the developments of quantum technology and quantum computing were sucking too much resource out of trying to address other challenges that we're faced with, and whether in the end the direction in which we're heading is a sustainable direction of travel.
Yeah, that's actually a good question. We've become a kind of popular, I hope it's not a fad, but it's certainly something that the governments have suddenly become fixated on, along with artificial intelligence, machine learning, and engineers, synthetic biology. These are the kind of things around the world that people are focusing on. The reality is, of course, the proportion we actually spend on research as a component part of the world economy is really pretty small. So looking at ways in which we can do more in one field, not necessarily at the expense of all the others, is something that we need to think through. And making sure that we're not captured by enthusiasts who propel one field at the expense of others is important. But let me maintain, we don't spend, if we spend 2% of our GDP on R&D, that's a pretty good outcome. So as long as we can be confident that we can persuade folks that spending on science is important, it shouldn't necessarily be at the expense of others. When we started the UK program, it was brand new money. It was not money taken from others, and that was important for us.
Thank you. other questions from the audience? Ravi.
Thank you, Sir Peter, for a very interesting talk. My question is that quantum computers at the end of the day are still analog devices in some sense. Computing on those is like similar to running really an experiment. And at one point you showed a slide about the noise levels. My understanding is that with the number of qubits going up, the noise level is also going up. And it is extremely difficult to control that noise, and many people are very pessimistic about that. But you showed that maybe a factor of 10 or 100 reduction in noise would, on your log plot, would really get us to a new plateau. I mean, is that really realistic?
The conquest of noise by error correction is really quite important. And if you look at the connectivity of the qubits, in order to do this, it depends on the platform. So that with some platforms, for example, trapped ions, in order to suppress errors through quantum error correction, you need a number of physical qubits to build a logical qubit, and that overhead could be probably 20 physical qubits making a logical qubit. If you take much noisier qubits, for example, the superconducting ones, then the overhead is much larger. You know, the error correction protocols for that are going to require a great number of physical qubits to make this. So that's where the hunt is, to do error correction. And there have been some really good advances in building error-corrected qubits recently. And I think what we need to be able to do is to show that once we've error-corrected this, then you can cycle things, you don't make repeated errors and so on. And that's where we have that prospect to climb up that mountain. I think that what we will be in this noisy intermediate scale regime for at least the next 5 years. But there are things we can do already in terms of optimization, in quantum chemistry, in looking, for example, at nitrogen fixation. All of these things, people are proposing advances already using these noisy devices. The large scale stuff is going to require the conquest of error correction. And I think that's where we've got at least a 10-year journey. But there are things you can do on the way to it, and people are already doing it. And that's why we're seeing this massive investment that's coming into this sort of field, because people can see that even at this intermediate scale, you can do stuff.
Any other questions from the audience? Just maybe one final question, Peter. You talked about cold atoms, you talked about superconductors, you talked about photonics. You didn't say anything about solid state approaches. What's your thinking there?
That's basically my own background, Donald. And there are all sorts of promising techniques. For example, spin-based qubits, which have been the focus very much of the University of New South Wales and allies activity in Australia, led by Michelle Simmons, looks very promising in terms of ability to actually build basic lattices of qubits. Getting them to entangle each other is difficult. Some of the quantum dot and systems are looking promising too. The area where you can use, for example, nitrogen vacancy diamond to do this, so you have teleportation, photonic links to things involving solid-state systems, is also looking promising. So it's too early to say this is going to be the winner. What I've tried to do is tell you where most resources have actually gone in, and that's superconducting and ions. But the others should not be neglected at all. In terms of the solid-state side of it, the challenge is simply to try to demonstrate at least 2 qubit gates, which don't have a great deal of noise in them. But that work is underway. And I've got I've got some friends who are really confident that these solid state systems that are compatible with CMOS really are the way to go eventually.
Thank you. If there are no more questions, may I please just ask everybody to join me in thanking Sir Peter. Thank you. Thanks very much.
Well, thank you very much.
Thank you very much for joining this talk in person or online. I just want to remind you that there's going to be faculty talks at 4 p.m. and another keynote talk at 6 p.m. Thank you.
So here we are at Science on the Spine, and we have created these experiments to be on the spine, so children from the KAUST schools and from schools in Kadima and Thule can come and do live experiments on the spine. Over here we have the MATE ROV competition. What's happening here is they're building robots, they're putting them in the pools and making sure that they work. And then if you follow me here to the library, you'll be able to see that our postgrads are reaching out to our younger students and doing live experiments on the spine. We are on Science on the Spine, and I'm joined by Mohammed Shahab, who's going to talk us through some robotics experiments, hopefully. Mohammed, tell us what you're going to do for the school children here today.
Yeah, okay. My name is Mohammed Shahab. We are from the Robotics and Intelligent Systems and Control Lab. Here I'm accompanied by PhD students Ubada Wali and Nawaf Al-Utabi and Kuwait Teleganov, who is managing the lab. So what we are going to be presenting today is two demos, robotic demos. The first one is going to be a combination of modular drones. So that's the first demo that we're going to present. And the other demo is related to the robotic arm. So both of these two demos show the potential of these two robotic applications. The first one related to how we can have modular robots and bigger structures that we can fly, either to lift off more payloads or to make some more complex maneuvers. The other one is the other robotic arm demonstration is related to the combination of robotic arms and the vision, the image processing of the computer on how to pick up stuff on its own automatically, and we'll be showing also how the computer will recognize the colors and the shapes of what to pick up depending on the color of the cube. And that, I think, will be good for the kids here to show and appreciate these kind of technologies and the concept behind them. Yeah.
Amazing, thank you. So when we talk about kind of robots, we're talking about a bit of engineering, and also, you know, today is the day for digital. We're focusing on digital today. So there's got to be some kind of like AI in there. There's got to be some sort of digital kind of element to it.
Yeah, and all of these devices that you see here, either the drones or the robotic arm, behind them in the background are the computer or the brain that it's actually controlling these and actually observe the environment and try to understand it and then try to decide what to do in the next step. And that's also always happening in the background, and these will be the researchers and the developers who are really programming it to tell the computer or the brains what to do according to what we want out of it. So yeah, that's definitely what's happening inside the computer or the brain that behind these robotic arms. They are not passive devices. There are something that's actually controlling them. So definitely, yeah.
What you're doing is amazing, and thank you for reaching out to the school children, and thank you for being part of KAUST Research Open Week. Audience online, and I'm joined now by Dr. Daniel Acevedo Feliz, the director of the Core Labs. Daniel, welcome.
Thank you.
Would you like to introduce yourself a little bit?
Sure. Yeah. My name is Daniel Acevedo. I'm the interim director for Core Labs and Research Infrastructure here at KAUST.
Brilliant. And we have a lot of Core Labs at KAUST.
Yes.
How many?
We have 12 different facilities.
Okay, excellent.
That support the whole faculty, the students, and also our partners from outside and from all over the country. So we're very proud of that.
Brilliant. Tell us a little bit about what the Core Labs do.
So we are here basically as research support. We are stewards of fantastic facilities that we were provided by the university, and our experts, which are scientists with a lot of different expertise, most of them with advanced degrees, PhDs.
From all over the world.
From all over the world,
yeah.
Indeed. We are here to really oversee the facilities, but also collaborate with our scientists. So yeah. Sometimes our staff have years of experience running the instruments, and we bring that along to the faculty and the users that have projects, and excellent. We combine efforts to really advance science.
So you're providing services in-house to our own faculty, our own KAUST faculty, and also nationally, kingdom-wide as well.
Absolutely, yes.
I think you have some nice examples from the Core Labs on how you support the kingdom and also you know, the university. We even have one of our booths that we interviewed yesterday for the AmbuBag. It was amazing.
Yep.
Maybe you could give us a few more examples of how the Core Lab supports specifically.
Absolutely.
Thinking one maybe like a glass blowing story or
yeah. We have in the glass blowing shop. That's part of our prototyping and product development Core Lab.
Yeah.
That's really a unique facility in the region, not just nationwide.
Yeah.
This is a dying art.
And a beautiful art.
Scientific glass blowing.
Yeah.
So we have partnered with technical universities, technical colleges in Saudi.
Well done.
To bring young Saudis, after they complete their degree, they will do an apprenticeship, basically. So they will learn and follow our glass blowing experts, which we have here. And they complete it's a 5-year program.
Wow.
They will be here for 5 years to really start from the beginning, and at the end, these guys have a guaranteed job. I mean, this is absolutely highly demanded worldwide. Very few places in the world provide this training.
Amazing.
And we're very proud of that, with providing that training for young Saudis that want to follow this career.
Absolutely. And how many glass blowers do we actually have in the Core Labs?
We have one master glass blower.
Yes.
From the UK, and we have also another staff member that is also now at the master level, really.
Right.
And that supports our glass blowing operation.
So 2 people.
Yes.
2 individuals taking care of a 5-year program. That's
absolutely.
amazing.
Yeah.
That's
and
amazing.
we have right now the cohort is 2 young Saudis from this technical college, and they are learning. They are starting from scratch, breaking a lot of glass.
Yeah.
That's okay.
Yeah.
You want to start doing that. But at the end, they're already producing and interacting with our researchers when they have projects that are demanding and how to solve problems. So they're already getting into the difficult part of the fun part also of the job, when they come with really complicated things that they're not off the shelf.
Yeah.
These are projects that require a dedicated design. And these guys are already getting into that. So that's fantastic to see.
So for our listeners, if you don't know, Daniel is one of 3 research directors here at KAUST. So Daniel, if I may ask you, how is the Core Labs enabling KAUST research?
So for us, it's all about providing this added value that our scientists bring. You could think of these facilities, and we could go all the way to just operating the facilities, making sure that the equipment is up and running, and the scientists don't need to do it. But we really bring more. Yeah. Our scientists are very proud of squeezing the last bit of information out of this equipment, working with the technology companies to really advance. We get advance notice on technology, so we bring the latest technology to campus. We provide that information to the faculty and our deans and the different divisions to say, this is where the field is going in terms of technology. If we combine that with their strategic plans in research, then that really is synergistic to really bring the university forward much more. So we're really proud of adding that extra, that just technical staff would be a missed opportunity really for the university. We are really pushing.
So knowledge sharing, building partnerships, training the next generation, and providing the service for the scientists in-house and also our in-kingdom and international users. Thank you, Daniel, for joining me today.
Hey, thank you for your time.
Thank you.
Thank you.
KAUST Research Week is a new opportunity for us to showcase what we do in our research at KAUST. We are engaging a lot more with our colleagues within the Kingdom. We have many partnerships, we have many projects that involve direct collaborations, and this is a great opportunity to bring people to KAUST. So we have a very wide range of activities. We have an amazing lineup of guest speakers for our keynote talks. Our KAUST faculty are also talking about very timely research topics. We cover a very broad spectrum, so we cover the 5 themes that KAUST is developing. So we cover the environment, we cover energy, we cover water, we cover food and health, we cover the digital realm. Getting out there, meeting people, getting into the labs, talking to the young people who are doing science, there's nothing better.
So here we are at Science on the Spine. We have created these experiments to be on the spine, so children from the KAUST schools and from schools in Kadima and Thule can come and do live experiments on the spine. Over here we have the Mate ROV competition. What's happening here is they're building robots, they're putting them in the pools and making sure that they work. And then if you follow me here to the library, you'll be able to see that our postgrads are reaching out to our younger students and doing live experiments on the spine. We are on Science on the Spine and I'm joined by Mohammed Shahab, who's going to talk us through some robotics experiments, hopefully. Mohammed, tell us what you're going to do for the school children here today.
Yeah, okay. My name is Mohammed Shahab. We are from the Robotics and Intelligent Systems and Control Lab. Here I'm accompanied by PhD students Ubada Wali and Nawaf Al-Utabi and Kuwait Teleganov, who is managing the lab. So what we are going to be presenting today is 2 demos, robotic demos. The first one is going to be a combination of modular drones. So that's the first demo that we're going to present. And the other demo is related to the robotic arm. So both of these 2 demos show the potential of these 2 robotic applications. The first one related to how we can have modular robots and bigger structures that we can fly, either to lift off more payloads or to make some more complex maneuvers. The other one is the other robotic arm demonstration is related to the combination of robotic arms and the vision, the image processing of the computer and how to pick up stuff on its own automatically, and we'll be showing also how the computer will recognize the colors and the shapes of what to pick up depending on the color of the cube. And that, I think, will be good for the kids here to show and appreciate these kind of technologies and the concept behind them. Yeah.
Amazing, thank you. So when we talk about kind of robots, we're talking about a bit of engineering, and also, you know, today is the day for digital. We're focusing on digital today. So there's got to be some kind of like AI in there. There's got to be some sort of digital kind of element to it.
Yeah, and all of these devices that you see here, either the drones or the robotic arm, behind them in the background are the computer or the brain that it's actually controlling these and actually observe the environment and try to understand it and then try to decide what to do in the next step. And that's also always happening in the background, and these will be the researchers and the developers who are really programming it to tell the computer or the brains what to do according to what we want out of it. So yeah, that's definitely what's happening inside the computer or the brain that behind these robotic arms. They are not passive devices. There are something that's actually controlling them. So definitely, yeah.
What you're doing is amazing, and thank you for reaching out to the school children, and thank you for being part of KAUST Research Open Week.
But I shall look at it, right?
Me. Hi, welcome back, everyone. I'm here now with Jorge Gascon, Professor of Chemical Engineering. Welcome, Jorge.
Thank you very much.
You're also the director of the KAUST Catalysis Center, correct?
Yep.
Okay, great. I have a feeling you could actually talk with us for a few hours about how your work relates to sustainability. Mm-hmm. But maybe if you want to select one or two of the key areas, your key focus at the moment, for example, just tell us a little bit about that.
Okay, so indeed I could talk for 2 hours. I will keep it much shorter. Catalysis is sustainability, right? Everything that allows you to make things faster, more efficiently, and with less waste, I believe is very much linked to sustainability. This is what we do at the Catalysis Center. We are improving industrial processes to make them waste-free and much more energy efficient. But we are not only doing that, we are also trying to change a paradigm which is thinking of carbon dioxide as a problem and rather turn that into an important feedstock to make durable carbon materials. And that's something that we are trying to facilitate through catalysis.
Okay. So there's many facets, really, where
Absolutely.
catalysis can improve processes or make them less wasteful and more sustainable. Mm-hmm. How can we use carbon as a feedstock, for example? Can you tell us a little bit about that?
Well, look, it's all a matter of how you look at the molecule. Right? Let's imagine oil, right? Oil has been and is still a feedstock for many important products, right? What we normally do with oil is we have super long chains of hydrocarbons, right? So carbon, 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 hydrogen, hydrogen, etc., very long chains that we cut to the size in which they can be used, be it as fuels, be it as materials, as precursors for polymers, etc., etc. Now with carbon dioxide, we are starting with a molecule that has only one carbon, and the trick here is to put back those carbons together, right? To make synthetic oil, if you want to do it. That's something that can be done with carbon dioxide, such a way that it is permanently recycled in a completely closed cycle, rather than extracting, consuming, and disposing.
Okay, so these fuels that you would make, synthetic fuels, they would burn cleaner and be more sustainable?
Well, by definition, they are going to be made out of carbon dioxide that has been sequestered, right? So that we can work with that carbon dioxide in a closed cycle rather than in an open cycle.
Okay.
So certainly, yes. But we are not only looking at carbon-based synthetic fuels, we are also looking at other fuels, and especially at ways in which we can use hydrogen in a more efficient way. Right? Ammonia is one of the molecules at which we are looking because we believe it has a very important potential as hydrogen storage and transport material. So we are looking at ways in which ammonia can be transformed back to nitrogen and hydrogen, releasing only nitrogen, which is absolutely harmless for the atmosphere, and again, releasing that hydrogen that can be used to generate energy for transportation, etc., etc. Again, those are things that need to be enabled by catalysis.
Okay, it's fascinating. And you have a nice part in a piece in our new research magazine, KAUST Insight, from the Office of the Vice President for Research. And you have also some very interesting collaborations with Aramco. Do you want to say anything about that?
Well, that's also part of making consumption of oil more sustainable, right? So we are trying to change the way refineries operate. At this moment, most of the product out of refineries are fuels. A small portion are precursors for polymerization that are used for the synthesis of materials. We are trying to change that balance, right? So, and basically devote most of the oil barrel to make durable carbon materials rather than to make fuels. That should bring sustainability to the oil industry, which is important. And of course, we are doing it while looking at potential impacts in terms of carbon dioxide emissions and so on, because our idea is that oil is a fantastic feedstock for so many things, and if we use it responsibly and smartly, it's here to stay.
Wow, okay. I thought we were going to run out.
No, I don't think so, especially if we use it for certain applications, then we will have oil for many more years. The problem is when we burn it, right?
Okay, right. So just a different way of thinking about
absolutely.
Oil.
It's making more out of less.
That sounds good. A different way of thinking about things, and certainly it sounds sustainable.
That's why we are at KAUST, right?
Yeah, that's why we're at KAUST. Jorge, do you have any demonstrations happening here from your group on the spine? Or you're having also an open day, I imagine the Catalysis Center will be, is that Wednesday?
Yes,
Wednesday.
Exactly.
Okay.
So
what should we not miss?
So we have indeed a nice demonstration with a fantastic team of people here in Building 19 on our oil to chemicals technology. You should certainly not miss it. It's if you want to know more about this topic about I talk about last, we have everyday science at the spine from the Catalysis Center. Most of the groups from the Catalysis Center have demonstrations there, and we have our open doors on Wednesday afternoon, and obviously everybody in the community is more than welcome.
Great, sounds good. Thank you, Jorge. Thanks for sharing your time with us and telling us just a small piece of all of the research you do that relates to sustainability.
My pleasure. Thanks a lot.
Thank you. Hello, welcome back. I'm here now with Manus Ward, the Director of Research Partnership and Planning in the Office of the Vice President for Research. Welcome, Manus.
It's great to be here. Thank you very much, Carolyn.
Thank you for sharing your time with us. I'd love to know, could you share with us, what does the Office of Research Partnership and Planning do as it relates to sustainability? But you can give us a broad scope first, if you like.
So I'll give you a broad scope. We have 4, I suppose, big functions. One of the big functions that we just took over during the summer was that of research funding. So as a university, we want to offer sort of bespoke programs in order to deliver on key different, I suppose, key different deliverables for the university, as well as align ourselves better with the kingdom, as well as programs that are very much directed towards translation, impact, and commercialization. So with those programs, as a university, we've always, and this often happens with funding agencies, we often get stuck in the implementation model where we focus an awful lot on the funding and maybe not as much on the monitoring and evaluation, because those are important parts in terms of working with our strategy and developing our strategy. So I'm sure most people know Nadia now because of Crow, anybody that's involved in Crow in any way. So Nadia's team, outside of what they're doing in terms of setting up this week for the KAUST Research Open Week, one of their main activities is in relation to research evaluation, research monitoring. So we are now currently doing a full review of all our 12 centres. It's a timely process, and through that, as a university, we get a lot of good insight and good feedback in terms of the centres. There's a lot of constructive feedback to help the centres develop. The other 2 big components is research translation. So Sami Dardona on my team is building a team of research engineers, and we are now at a stage where we've brought that team up nearly to full capacity. So they will be actively working with the research community, working on projects, helping develop their technologies and scale their technologies out.
What's a research engineer?
A research engineer, so the people that we've targeted are people that have specific skill sets. So there's chemical engineers, there's design engineers, there's software engineers. So they've got specific design sets that are, and most of the individuals that we have are coming from an industry background.
Okay.
So with those, what we want to do is have these guys actually work. They know what the industry standards and what industry needs, and in terms of helping develop the technologies in order to move the technologies up the research translation chain. The other group, and I always joke about this, is the partnerships. Mm-hmm. So with the research partnerships, we have a small team. Realistically, I should be dividing my efforts 25% across each of the different teams. Research partnerships takes up 120% of my time.
Okay.
So that gives you a sort of indication of where we are, and it's, from my perspective, and it's been one of the things, if people have seen me over the last couple of days, I've been zooming here and zooming there. So we have a lot of our national partners have been with us this week. So I've spent a lot of time with them, having side meetings, just understanding where we are in terms of developing different partnerships, different agreements. So it's been a really fun couple of days in that regard, because whatever chances that we can get, sometimes we're a bit isolated here, being outside Jeddah and on the Red Coast, or on the coast of the Red Sea. So whatever opportunities I can get to engage with my partners, I think it's hugely important. Plus, they get to see KAUST at its finest, which it has been over this last couple of days.
Exactly. Who are some of the key partners that are here this week?
So today's conversations, we were talking with the Royal Commission for Al-Lula, and we're really looking to develop a program of activities out with them. Another big partner that we have is MIWA. So we just signed a strategic partnership agreement with MIWA last week, and we had a follow-on discussion with two of the key people that have been driving that on the MIWA side. So that is it's a joint venture, 60 million SAR over the next 5 years. So, and this evening I am going for dinner with is a representative from the Ministry of Investment. We're looking, myself and him and Jiahang Li are going to have a discussion around the semiconductor space and where KAUST can add value in that space. Yesterday we met with the Ministry of Energy, so had a really good discussion with them, and that was done with the former president of Iceland, President Grimsman, who's here over this for the course of the week. So there's lots of interesting conversations. You know, some projects are in development, but some new beginnings as well, which is really exciting.
That's great. That was my next question. Where are we headed?
No, so it's like, you know, for me, one of the big things about KAUST is, you know, it's, in order for us to deliver, we're a relatively small university, and for us to deliver, we need to have big partners. You know, I think my goal, you know, people talk about impact. You know, I think one of the biggest impacts that I would like my team to have is making KAUST more relevant. And the only way that we can be more relevant is to be actively engaged with our partners, in particular in the Kingdom, in terms of providing solutions for them, you know, advancing you know, the setup of the Giga projects, advancing the missions of the ministries, you know, working very closely with our partners such as Saudi Aramco. Again, you know, they have a number of people here, and it's you know, and I always like to link in and have a conversation with them.
It sounds like lots of the partners actually touch on sustainability, the energy, MIWA.
Yeah, and I think this is, it's one of these areas where you know, where I think most of our partners see that, you know, we can't continue to do things the way that we have done things. So in order for, you know, those projects, in order for them to have the sustainability that they want, they have to do things differently, you know. So they have to look at their energy sources differently, they have to look at water differently, they have to look at, you know, how, you know, they consume things, energy storage. So there's a whole sort of kind of mesh of things coming together. So the conversations on sustainability are, I think, they're very apt because, you know, I think, you know, already, you know, and this is why there's such a big conversation in the semiconductor space, because people are already anticipating significant shortages in that area, basically because we're starting to run out of some of the key materials and some of the raw materials. Lithium-ion batteries, which is one of the biggest storage mechanisms. Now, lithium is becoming a source of contention because, you know, there's only a limited availability of lithium. So if we're looking at, you know, developing worldwide fleets of electric cars that have lithium-ion batteries, where's the lithium going to come from?
Right.
You know, so there's I think globally people are starting to see that you can't continue to take and take and take and not have a way of sort of kind of recycling things back into the system. So I think, you know, the whole goal for, in my view, from sustainability now is looking at, you know, if we do something, you know, if you buy something, you actually think about, you know, what was involved in making that, you know, and how is that actually going to be recycled back into the system, or how could it be used in another sort of productive way? And I think for too many years, we've just got into the cycle of sort of using and discarding without really thinking. So I think it's just, I think people need to have just a different way of thinking now moving forward in terms of how we look at the products we buy. You know, I love my travel, but you know, do we really need to travel as much? And you know, whilst you might be going to the country and helping boost that economy, but at what cost is that to the environment? So that's always a difficult one for us here at KAUST.
It is a little more holistic view and some consumer accountability, I guess.
Yeah.
So let's finish off with one last question. What are you most looking forward to about the week?
You know, people are talking about McLaren coming in the Formula One. For me, when we started this off, you know, I really just wanted, my big KPI was getting the research community out and active and talking to each other. You know, so I've just come from the visual computing open house, and there's over 200 people down there. It was actually pretty amazing. The sessions with the students at lunchtime, you know, there's been such a great buzz around those. You know, I know the attraction of free food is always a great way to
helps, yeah.
It does. So, but it's and that to me is the biggest KPI. You know, and I'm about my youngest daughter. She was up on the spine doing science on the spine. You know, and just getting that young community excited about their research and out and talking and discussing science, and that to me, that's my big deliverable for the week.
That sounds great. Yep, they're our future, right?
Yep, they're our future.
Thank you, Manis, for chatting with me today, and enjoy the rest of the week.
Thank you very much.
Thank you.
Okay, take care.
You too.
Bye.
Bye.
Welcome to day 2, everybody, of KAUST Research Open Week. Today we are focusing on the digital domain. I'm here at the booths again, and I hope to walk you through what KAUST is doing to provide a more sustainable future for the kingdom and for the world. Come walk with me. I'm here at booth 26. It's talking about extracting lithium from seawater, in particular the Red Sea. And I'm joined by...
I'm Zenny.
I'm Zhong Xiaoli.
from Xiping Lai's group in KAUST.
Yes, I'm from Xiping Lai's KAUST, and he comes from the Hong Kong City University.
Yeah, I'm a visiting student here.
This is excellent. Yeah. So tell us a little bit about what you're doing here at the booth, Zhenli.
I'm extracting the lithium from the seawater using our membrane. We prepare a lithium selective membrane like this, and it's a kind of critical with the special lattice, and the lattice can only allow the inserting of lithium and rejecting the inserting of other ions, so that if we applied the voltage between the membrane, that only lithium can pass through the membrane, and the other ions like sodium, potassium cannot pass through. It can be blocked by the membrane.
Excellent. So basically, kind of the secret recipe here is the membrane that will be used to allow the lithium to pass through, but nothing else. Yeah. And that's what you have developed in Xiping Lai's lab. But we also have a solar light here, which comes from, I think, your side, right?
Yeah. And during the lithium extraction, and they need the energy, right? So normally people use the electric from the industry and burn something fossil fuel, and it's totally environmental friendly. So from this opinion, we get some silicon solar cell, and they just need to sunlight on it, and they will produce enough energy to drive this reaction and drive this lithium from the seawater side to the concentration side, and this is our work too.
Amazing. So we've got the membrane, which is doing basically allowing the lithium to extract, the solar cells, which is giving power to this entire thing and allowing it to happen. So Zhenli, tell me, why do we even want to extract lithium from the Red Sea?
Because as the development of many electric equipment, for example, the electric vehicles and our cell phones and our laptops, and we need a lot of lithium battery. That means the lithium demand is rapidly increased in these years. So we need to extract this kind of valuable resource from seawater.
Yeah, what you're doing is absolutely excellent. It's very sustainable because you're using the solar lights and the solar cells. You're extracting from right outside our back garden in the backyard, which is the Red Sea. So this is fantastic. And you're extracting lithium, which is needed as it's basically to power, right, for batteries and for battery cells. So thank you both for joining me here today, and thank you for being at this booth.
You're welcome.
Normal professor said that they don't know yet if I will have an actual department of aviation. But you can say mechanical engineering.
Hi, welcome back. I'm here with Thibaut Ghiberti, who is a professor of mechanical engineering. Welcome, Thibaut.
Thank you. Thank you for the invitation.
Thank you for joining us. We'd love to hear a little bit about your research, and then maybe you can tell us how it aligns with sustainability.
All right, sure. So I work with reactive flows, which is a fancy way of saying flames.
Oh, thank you.
So that's the kind of flows you need to produce power, like electricity or heat or propulsion. And so basically the way I contribute to sustainability in that field is that we're trying to get away from the typical fuels we've been burning to produce this power, this electricity, and this mobility, which are hydrocarbons, which are culprits in producing a lot of CO2. And so my research is really trying to continue producing a lot of energy because we need the energy in a more sustainable way by emitting less CO2.
Okay, so it's not alternative fuels, it's being more efficient about the burning of the common fuel we use.
No, so yeah, thank you. That's a very nice question. So there are many different ways of being more sustainable, and the first way was trying to be more efficient, trying to burn less fuel to get the same amount of energy.
Okay.
But it's not enough because even if you have a very good efficiency, you'll still emit some CO2 if you're burning hydrocarbons. So most of what I do and most of what we do at the Clean Combustion Research Center now is actually trying to go to new fuels that do not have the C atom, do not have carbon in it, so that when you burn it, then you don't get CO2.
Okay.
And so two very good examples of such fuels are hydrogen, H2, and ammonia, NH3.
Okay.
When you burn that, you get basically H2O and not CO2.
Okay, so not so harmful to the atmosphere.
Yes.
Or not harmful at all, I guess.
Well, for sure you easily get rid of the CO2, but CO2 is not the only potentially harmful emission from flames, from combustion. You have other pollutants, including nitric oxides, NO, N2O, NO2, and this can come from the air itself. So when you're burning air, you have nitrogen in the air, and so if you're not careful, even burning these new fuels, H2, hydrogen or ammonia, you may produce this harmful species. And so that's one of the challenges we're facing as we try to promote this new carbon-free fuels, is that there are other emissions that we need to be mindful of.
Okay. And then can they also be captured, or is it more simply about avoiding it?
Right, so yes, you're right. So instead of using carbon-free fuel, you could also use what we call carbon-neutral fuels, where there's still some carbon in it, but you can do basically a carbon cycle where the carbon you emit as you burn the fuel, you actually capture it and you reintegrate it in the fuel. So you're looping the carbon so that basically you're neutral, you're not doing a net emission to the atmosphere. And so methanol or ethanol could be fuels of this nature, yes.
Does that mean that you wouldn't have to refill the tank? It would just continue to...
No,
okay.
No, because the CO2 is not the only product of combustion. You have also H2O, and so some of the energy is released to the atmosphere anyway. So you need to get this CO2 that you captured, then go get some water somewhere, and then use electricity to recombine it into a fuel which you can use in your car or in your gas turbine.
The future of fuels, so exciting. It's going to be interesting to see how we're powering our vehicles and phones in the future.
Yes.
What's your main focus going forward in your research?
So my main focus right now is on gas turbines, which is basically a unit to produce electricity, and we are trying to see how we can send pure ammonia in these turbines, which have been developed with hydrocarbons in mind, and still have good stability and good performance, so burning ammonia.
Okay. Where do we get the ammonia from?
So the ammonia is a hydrogen carrier. So actually you produce hydrogen using electrolysis, so electricity that comes from renewable, and you basically from water, you get this hydrogen, and then hydrogen, you combine it with some nitrogen you get from the air to create ammonia. And you want this ammonia because it's liquid at low pressure compared to hydrogen, so it's much easier to store and transport than hydrogen.
Okay.
So you produce ammonia from electricity and water.
Wow.
And air.
Cool. Okay. Wow, that's really exciting. And so what are you looking forward to this week? You're part of the Clean Combustion Research Center.
Yes.
And you will have an open house Wednesday,
yes,
correct?
Wednesday between 2 and 4, we are organizing tours of our facilities in Building 5 and in Building 7.
Okay. Yes. What if of the folks who can physically attend, what can they look forward to seeing at this open house? Do you have any examples of what we could see? Will we see your flames, for example?
So I know we've been preparing some virtual tours.
Okay.
So I don't know as of right now where they will be displayed, but we have a very nice movies of the different experiments we have in the lab, and that I need to do.
Lab safety. To some extent, I guess we can't all pile into the lab to...
Sure, and there are some experiments where nobody can be really around when they're running because of the scale.
Okay.
But we have nice images for that, yeah.
On the upside, that means that our virtual audience will also be able to attend the open house, I imagine? Or some sections of the...
So I don't know if it's going to be in parallel, but there will be some access to these videos, I think, but I just don't know right now.
Okay.
Through which channels.
Okay, we'll find out. We'll try to be there for the open house.
Yeah.
Thank you, Thibaut.
Thank you.
Thank you. See you at the open house.
Thank you.
KAUST Research Week is a new opportunity for us to showcase what we do in our research at KAUST. We are engaging a lot more with our colleagues within the Kingdom. We have many partnerships, we have many projects that involve direct collaborations, and this is a great opportunity to bring people to KAUST. So we have a very wide range of activities. We have an amazing lineup of guest speakers for our keynote talks. Our KAUST faculty are also talking about very timely research topics. We cover a very broad spectrum, so we cover the 5 themes that KAUST is developing. So we cover the environment, we cover energy, we cover water, we cover food and health, we cover the digital realm. Getting out there, meeting people, getting into the labs, talking to the young people who are doing science, there's nothing better. My name is Donald Bradley and I'm the Vice President for Research at KAUST. KAUST Insight is a new publication. It tells the story behind the discoveries that come out of our research. We're interested to show the social side of science, how new ideas in science sometimes come from chance encounters. We want KAUST Insight to be a publication that helps people to understand where our science is going. That is influenced by many factors, by the needs of Saudi Arabia, by the Vision 2030, also by our own strategies, the things that we think are important for KAUST to be part of and to be working on. Some key directions include work that is being done to address climate change, and in particular the work that we're doing within the circular carbon economy. We have a circular carbon initiative that is focused on finding ways to reduce the amount of carbon dioxide that is produced, to remove it, to recycle it and to reuse it. Another key component of our science going forward is to work on the Red Sea. The Red Sea is a very exciting opportunity for research. It's critical to the future of the kingdom in terms of the development that's taking place through the Giga projects. And it's a fascinating environment in which many different areas of science come together. Another critical area is how society is changing. The gender balance in science, and we want to be part of that journey. We want to show how diversity is important to taking science forward. We want to show how women in science are contributing and how they are taking leadership in driving forward many of the ideas that we have for development in KAUST. You will find that all of these topics are featured within KAUST Insight, and we will be looking to develop these stories as the publication goes forward over time. There are many new areas that are coming forward in science in terms of the digital transformation, in terms of the energy transformation. There are lots of different directions in which our science will be progressing, and we look very much forward to being able to expose those areas to our readership of KAUST Insight.
Welcome to day 2, everybody, of KAUST Research Open Week. Today we are focusing on the digital domain. I'm here at the booths again, and I hope to walk you through what KAUST is doing to provide a more sustainable future for the kingdom and for the world. Come walk with me. I'm here at booth 26. It's talking about extracting lithium from seawater, in particular the Red Sea. And I'm joined by...
I'm Zhenli.
I'm Zhongxiao Li.
From Xiping Lai's group in KAUST.
Yes, I'm from Xiping Lai's KAUST, and he comes from the Hong Kong City University.
Yeah, I'm a visiting student here.
This is excellent. Yeah. So tell us a little bit about what you're doing here at the booth, Zhenli.
I'm extracting the lithium from the seawater using our membrane. We prepare a lithium selective membrane like this, and it's a kind of critical with the special lattice, and the lattice can only allow the inserting of lithium and rejecting the inserting of other ions, so that if we applied the voltage between the membrane, that only lithium can pass through the membrane, and the other ions like sodium, potassium cannot pass through. It can be blocked by the membrane.
Excellent. So basically, kind of the secret recipe here is the membrane that will be used to allow the lithium to pass through, but nothing else. Yeah. And that's what you have developed in Xiping Lai's lab. But we also have a solar light here, which comes from, I think, your side, right?
Yeah. And you know, during the lithium extraction, and they need the energy, right? So normally people use the electric from the industry and burn something fossil fuel, and it's totally, environmental friendly. So from this opinion, we get some silicon solar solar cell, and they just need to sunlight and sunlight on it, and they will produce enough energy to drive this reaction and drive this lithium from the seawater side to the concentration side, and this is our work too.
Amazing. So we've got the membrane, which is doing basically allowing the lithium to extract, the solar cells, which is giving power to this entire thing and allowing it to happen. So Zhenli, tell me, why do we even want to extract lithium from the Red Sea?
Because as the development of many electric equipment, for example, the electric vehicles and our cell phones and our laptops, and we need a lot of lithium battery. That means the lithium demand is rapidly increased in these years. So we need to extract this kind of valuable resource from seawater.
Yeah, what you're doing is absolutely excellent. It's very sustainable because you're using the solar lights and the solar cells. You're extracting from right outside our back garden, the backyard, which is the Red Sea. So this is fantastic. And you're extracting lithium, which is needed as basically to power, right, for batteries and for battery cells. So thank you both for joining me here today, and thank you for being at this booth.
You're welcome. Thank you.
Are at booth 5. I'm looking at the title. It's called Cryogenic Carbon Capture. So carbon being a very common word these days, especially when it comes to climate change. Good morning, guys. Could you introduce yourselves?
Hi, Nadia. My name is Christopher Wagstaff. I'm a PhD student here at KAUST.
And I'm Anne Antunes, also a PhD student here at KAUST in the CCRC.
With Professor Bill Roberts. Could you guys tell us a little bit about what's going on at this booth?
Of course. So this is a kind of new process for carbon dioxide capture, and we've pinpointed it because it has some real cool advantages over other processes in the field. So this is very much thermodynamics based. We're working with the company SES, an American company, and we've been testing this for quite some time now. We have a lot of hours of running like
troubleshooting.
Yeah. in Kingdom, and we're like going to separate ways. I'm gonna say why. This sounded really bad.
It sounds amazing. No. So it sounds like you guys are capturing carbon at the source, right?
In carbon dioxide intensive sources. So cement plants, power plants, all the big emission sources. And it's really cool because we can basically be integrated in their process without changing anything. So we capture the flue gas that's rich in CO2. We cool it down a lot, and then this is where the magic happens in the spray tower. So we basically sprinkle a very, very cold liquid, below minus 120 degrees, and we induce desublimation of the CO2, which means basically the CO2 will freeze, will solidify instantly in the liquid droplets and fall down to the bottom of this spray tower in a kind of slurry. And then we separate this slurry by squeezing it in a screw press. We separate the liquid from the solid, and we end up with kind of solid CO2, like dry ice, which is quite fun to see.
You can see it right there on the screen.
Exactly. And we recirculate this very cold liquid to not lose all of the energy we used in cooling it, and also the rest of the gas that's not the CO2 and was cooled down will go through a heat exchanger and basically cool down the flue gas that's coming in the beginning. And this technology is really interesting because we can end up with a very pure CO2 at the end, like industry-grade CO2 that you can I don't know, use in food industry, eventually sequester in the ground. There's a lot of options. And it's really important for the circular carbon economy. Like the kingdom is really, really focusing in it.
What you're doing is very, very important for the kingdom and for the world as well, right? It's very hard to capture CO2. And you guys are doing that. And not only are you doing that, but you're also capturing pollutants at the source as well. And everything is powered via solar and wind. So it's sustainable.
Yeah, powering it by solar and wind is definitely an option.
Yeah.
So it can be used kind of as a energy storage system. So you can kind of like pre-chill some of your refrigerant ahead of time. And so that's the way it would be integrated with solar and wind.
Excellent.
It only needs electricity. So if you have like better, let's say, cleaner sources of electricity, then it's better for the whole.
Why not use it? Yeah.
And like it also has several advantages over amines, for example, that are the other main technology in CO2 capture. Like we use way less energy for the same capture. We don't have to get more absorbance in the process because there's no use of them. And
you don't have to use steam. Usually steam is integrated into the power plant process, but this can be used with wind and solar, where there is no extra steam lying around.
Excellent. What you're doing is very important, and it sounds like it's state of the art. So thank you so much for your time today.
Yeah, thank you, Nadia.
Hello, welcome back. I'm here now with Shaika Inal. She's a professor of bioengineering. Welcome, Shaika.
Thank you. Hi, Carolyn.
Hi. Thanks for taking the time to chat with us today about your research during Research Open Week.
I'm very excited about it.
Great. I saw you were just having a look through our new research magazine, KAUST Insight, and your piece within the story that we did about COVID.
Yeah.
Maybe you could start by telling us a little bit about that project.
Sure, of course. So actually, we did present some pieces from this project. Last week, there was a Smart Health Initiative opening event. So this is some work that we did under R3T team. This is Rapid Response Team that the president has called once the pandemic started in 2020, as we all know when it was. So what we did within this project is basically making electronic sensors for the virus. I teamed up with a protein engineering team led by Professor Stefan Arold. He's a professor of bioscience at my division. So Stefan's team builds very interesting and well-controlled protein layers. And these proteins are able to specifically target the virus itself. And I myself, as I will explain to you in a bit, make electronic devices, micron-scale chips. And if you put these proteins on top of these chips in a very controlled fashion, you can actually make electronic sensors for the virus. And that's where we spent almost about a year. We published our results in a Nature journal, and currently getting some funding from the Innovation and Economic Cluster to commercialize these sensors and build some prototypes so that the clinicians in the hospitals in the kingdom can use them for rapid testing of the coronavirus.
Okay, great. Please tell us about your research about these microelectronics. Are so fascinating.
Sure,
and this field of bioengineering also.
So my research is in the field of bioelectronics, and my lab is called organic bioelectronics. So as the name suggests, in the lab we deal with organic electronic materials. These are carbon-based semiconductors. I'm sure you heard this week about semiconductors. So the type of the semiconducting materials that I deal with are organic based. So these are simply, you can think about them as conducting plastics.
Okay.
And they do have quite interesting properties for interfacing with living systems. So I do a lot of fundamental studies of how charges are transported in the films of these organic semiconductors. And then when we find interesting candidates or efficient candidates, we go ahead and make micro-scale chips that integrate these polymers. And due to these interesting properties, transport properties, we are able to make sensors and actuators for biological systems. So these devices either detect very small or very weak biological signals from living cells. Normally you can't really hear them, what they're doing, but once you bring those sensors close by, you can detect various things from the tissue. Or if you want to intervene with what they are doing, for example, to cure certain diseases, you can use electrical signals. But again, for that type of communication between the living systems and the electronics, you need really, you need materials that have the properties from these two worlds. And organic semiconductors have properties from these two worlds. They're, soft as the living systems, like the tissue, but at the same time conducting like inorganic metals and such. So my lab is really trying to bring the worlds of biology and electronics together so that we can establish communication between these two worlds.
Well, doesn't seem like a likely pairing.
Well, yeah, we have a lot of challenges.
I imagine.
But again, I think materials, they hold the key. And we love working with materials, and that's also one of the strengths of KAUST. We have quite a wide variety of materials that we can work with. So we have internal collaborations. So although I'm a fan of organic materials, I also work a little bit with, for instance, 2D materials. These have also interesting properties to explore.
Okay. So you told us a little bit about this collaboration with Stefan, and hoping to move this to market as well at some point in the near future.
Yeah.
Do you see any other of the initiatives from your lab related to this type of work, this type of sort of quick to the call sort of what's the current emergency and sort of tuning to those?
Right. So anything that we do in the lab has a path for translation, because we are working, although we do a lot of fundamental research, our final goal or whatever we have in the back of our minds when we are in the lab discovering things is always for an application, and that application is in healthcare. And because humans, are born with problems and they will keep on having problems, we hope to generate solutions that can solve those issues. So today, the devices that I make are for coronavirus. Maybe in the next pandemic, unfortunately, we will have it. We will then have some devices ready for the next diseases, or any disease that currently the detection relies on very long procedures or hospitals with expensive instrumentation and trained personnel. So the idea is to be able to bring sensors to the homes of the users so that, for instance, people in rural areas or those in underdeveloped countries have access to some sort of healthcare.
That's great. That reminds me actually of our new issue of KAUST Discovery, which is about super connecting the connected and connecting the underconnected. So also check out the latest
beautiful
issue
topic.
of KAUST Discovery. Yeah. So that sounds like you're doing a similar thing with health, basically, in healthcare.
Yes, trying to bring basically healthcare to those that may need it, but at the same time we try to develop technologies that are at the forefront. Things that you cannot maybe think right now, or they are not used as treatment of diseases, but maybe in 10, 20, 50 years from now on, those technologies will be more mainstream.
Available to all.
Hopefully, yes.
And you have you and your lab, you have a booth here, correct?
Yes, that's correct.
Okay.
We are demonstrating some of our devices in the Future Semiconductors booth, which I think we share with 4 other PIs at KAUST. So we are just showcasing some of our organic electronic devices in that booth.
Okay, so maybe some fruitful collaborations on the horizon there with those colleagues.
There's actually one device there that we use in collaboration with Antonio Adamo's lab, who's a stem cell biologist. Antonio has stem cells that do not like to grow fast. So we try to use electrical stimulation by use of these devices to make those cells grow into their best.
Wow.
For instance, Antonio wants to take those skin cells and make them turn into a different type of tissue, which can then be implanted in the body where it is needed. But for those, you also need certain electrical cues, and that's what we try to molecularly induce with the devices.
Fascinating. That's great. And also this week, you will be involved in a Women in Science talk, is that right?
Yes, and I'm very excited about it. Looking forward to it. It's on Thursday, in 3 days from now on. There will be 2 speakers from KAUST, and we have an external speaker who's coming from Oxford. She's also a keynote speaker. And we are going to talk about, the goods and the bads about being a woman in science.
Okay, sounds good. One not to miss.
Exactly, yes. I invite everyone to attend the event.
Sounds good. And then also you are affiliated with the CBRC, the Computational Bioscience Research Center?
Correct, yes.
And you have an open house on Thursday?
On Thursday afternoon, yes, we are opening the doors of our lab to everyone who wants to know more about organic electronic devices.
Great, okay. Sounds good. We'll be there, Shaika.
Fantastic. I look forward to hosting you.
Thank you. See you then.
See you. Bye-bye.
Bye.
Yeah.
Hello, beautiful people. Come down to the front. Come on, get out of those seats at the back. Come on, Julie, get down. You need to be here. You need to see what the professors are talking about. This is KAUST professors. Give them the respect. Come down to the front. Thank you. Shukran.
Good afternoon, and welcome back here, and welcome back also to the audience, which is live following us. We're going to start today's session of the faculty talks. I am Sara Durini, and I'm a scientific editor in the research communication team in the Office of the Vice President for Research. The first speaker is Mohamed El Hosseini, Assistant Professor of Computer Science at KAUST. Before joining KAUST, he was a visiting faculty member at Stanford University and at Baidu Research. And before that, he was postdoc at Facebook AI Research. He received his PhD in 2016 from Rutgers University, where he was part of the Art and AI Lab. Professor El Hosseini's primary research interests lie in computer vision, especially in efficient multimodal learning with limited data in zero-few-shot learning and vision and language. He is also interested in effective AI, especially to understand and generate novel visual content, such as art and fashion, for example. Please join me to welcome on stage Professor Mohamed El Hosseini.
Thanks, Sarah, for the nice introduction. All right. Today I'm going to talk about something that I feel very passionate about, imaginative and effective AI. And the connection that I want to introduce with you today is how it actually can relate to building sustainable future, which is a reflection that I have thought about recently. So before I start, I'd like also to thank my team who's behind a lot of the work that I'm going to present today, and also collaborators that I'm going to mention as I proceed. So the machine learning and AI has powered a lot of actually our life in the recent years. And in the technical level, a lot of people may agree on categorizing that into three categories: supervised learning, semi-supervised learning, and unsupervised learning. Let's simplify that in the sense of having a machine learning system that does some simple task. And this task is categorizing, let's say, cats and dogs. So we have a bunch of photos. Some of them are cats and others are dogs. And when just to classify if an image belongs to a cat or is an image of a cat or a dog, a supervised approach assumes that we have all the labels. For every single image, I know that this is a cat or this is a dog. And this works pretty actually well. But this is not usually so realistic. So we might have only a few images that are labeled, and this represents a second direction, which is semi-supervised learning, where we have only some of these labels of cats and dogs, and we hope to leverage the unlabeled data to be able to do this task very well. Unsupervised learning is where you have access to only the data, and we don't have even a single label that tells me this is a cat or a dog. So you want to make the model itself discover the categories and hopefully name them as well. So what I'm going to talk to you about is some reflection that relates to another paradigm that could be complementary to those. And this paradigm is what we might call imaginative learning. And today I'm going to show you how it can connect to solving some of the real problems and in helping us to see. So for example, understanding an image of a bird that I have never seen before, or an animal that I have never seen before, producing art, fashion, and how this can be an excellent tool to accelerate the rate of progress of producing creative products like art and fashion, and maybe revolutionize the interior design industry, like producing a new design of a chair or something. Drive, how do we build imagination is a key element of human intelligence, and at the heart of it is to extend beyond things that we haven't seen. And this is actually, I think, the main thing that I feel beautiful and makes me think about it every single day. Imagine to drive, how do we enable or how do you build self-driving cars that can imagine itself in some situation so that it avoids, if that prediction or that trajectory of a car is so dangerous, I want at the training time to hallucinate trajectories or prediction of the car so that if it hits the road boundary, I hit it in the learning time, not in real life, which could be fatal. The fourth part is imagination to feel, and this means that how can we have models that can feel and maybe communicate with us with some affection. This might connect to some, for example, sustaining mental health. So for example, one of the key things that we seek help for in mental health problem is to speak someone that makes us feel good, right? And what I'm trying to share with you today is that we can build systems that can communicate with affection to us, and maybe this will help in case accessing some person who can makes us feel well is not easy to find. So I'm gonna go through a set of steps, and I hope to make some progress convincing you guys that this is a useful modeling direction. So imagination to see. So let's say a lot of people might not know what this bird barketo is, but if I describe to every single one of you that this is a bird and it has an orange beak and the plumage of this bird is dark above and white below, you can start to imagine how this bird may look like even if you haven't seen this before. And this imagination will help you identify which bird I'm talking about even if you haven't seen that before, right? So you can easily say that this is the bird I'm talking about. And this human learning ability inspired several researchers, and I'm one of them, to build machine learning systems that have a similar imaginative ability. In concrete, so we can have a system that takes as an input that description of Parquet-Euclid that we just mentioned and feed that to an imaginative model, but this is a neural network that can hallucinate generation of a bird or an animal that we have never seen before. And think about it, if we have more than 10,000 bird species in our planet, and the data sets that we have access to are only a few hundred, right? So we cannot actually have data. For most of these categories, we don't have much data. So, but imagine if we have a model, an imaginer, that can hallucinate these unseen birds from just a bunch of words, from a language description. One thing we can do is that we can hallucinate generations for each one of those, and we will have imaginary data, fake data for each one of those, and this will help us identify those unseen bird species and tell them apart, hopefully from seen ones. In fact, we built a state-of-the-art model a few years ago called generative zero-shot learning. Zero-shot means here that we don't have examples, zero images of unseen classes. So this is where zero is coming from. And at that time, you can see that there's a big bump before models that explicitly formulate this problem as an imaginative task with a generator that tries to hallucinate or imagine appearances of classes that has never been seen before. Why this is helpful, like in real life? We often may encounter a situation where I've seen a bird, and this bird may fly away, and we have no longer access to it. And in other situation, we actually have to fly away. Otherwise, we could be a meal to this hungry bear, right? In both situations, we care both about the bird and the bear from biodiversity perspective. We want to recognize the appearance of this bird, and we know at the fine-grained level what category of bird that is, and report size of them, because this can help reporting size of those creatures and maybe help decision makers to take some actions to protect species that could be in danger. All right, so imagine that Adam actually is the name of my son. So I've seen a bird that just flied away, and he can just say, I just saw a bird and that has an orange beak. And maybe the robot that loves environment here, which is represented by the picture on the left, can ask more and more questions until we make sure what kind of bird we really mean, and we give us an answer that we're happy with and identify that bird, right, through a conversational setting. And hence, if we make sure that kid can report sight of this creation, and this might actually make the reporting of those sites is something that everybody can do, right? So this is something, and I have actually talked in the United Nations Convention of Biodiversity in 2018 about that, and I have seen a lot of interest in from decision makers that this is something where AI can be an additional arm and it may help a lot more than there's still some progress to make this happen, but what I have sensed from that there is room to contribute. So imagination to create is about, I think, the way it relates to sustainability is sustaining the beauty we see in the world, accelerating the rate of producing creative products like art, fashion, accelerating in the interior design and stuff like that. I'm going to explore with you or share with you today the art and fashion, but this might extend to also other industry that we can think of are important. So imagination to create is, I think, in this, to start discuss this, I want to introduce the creative adversarial networks. It's a method that we developed a few years back, and it's in a nutshell or in a sentence, it takes existing art styles, let's say High Renaissance, abstract art, Cubism, etc., and it tries to come up with a new art style that have never been seen before. And we hope that this art style is something that could be interesting. It's based psychologically, it's based on a principle in psychology called the principle of least effort by Colin Martindale, who's a Canadian psychologist, and that was studied in the scope of human creativity, where the x-axis here is novelty of an artwork produced at that time by human, and the y-axis is hedonic value, means likability. So this shows that if something is not so novel, people may not like it, but as novelty increases, people start to like the work more and more, but not for too long. If the work is too novel to understand, that will make it hard to relate or hard to appreciate, right? So the point is how to build a machine learning model that can generate content that is in that sweet spot, all right? So GAN, we took the state-of-the-art model GANs, and at that time, we can feed it images of artworks, but the point is that it is trained with imitation. It is not trained to produce something new. It is not encouraged to create something novel that is different. So it will end up producing something like the Mona Lisa again. It's a beautiful painting, but it's not creative anymore. So we needed to do something to encourage or excite that model to think creatively about the content that we want to generate. So we came up with this, what we did is that we said, hey, we have 20 art styles, and abstract art, Cubism, Impressionism, High Renaissance, etc., and we want to start from those, and we want to generate something new. And to do that, what we did is something simple. We have a discriminator that tries to tell if this is a piece of art or not, and at the same time, it can predict if this piece belong with confidence to any of the existing art styles. And it tries to teach the generator so that if it produces the Mona Lisa, if the generator produces the Mona Lisa, it gives us a penalty. Hey, this is something similar. This is 100% High Renaissance. I don't want that. And we formulated that by an entropy loss. So if the image is easy to classify to any of the existing art style, then we found it's not creative. But if they produce an image that is hard to classify to any of the existing artworks, then we give the model a reward. And by training or enforcing the model to have this sense of creativity, it was able to produce novel content.
I like it. It's really cool. So who painted it? A machine.
It's actually the first work of art made by AI to be sold at Sotheby's. Sorry, I'm late, Dana. I got caught up.
So this is a piece of art that was generated by the GAN model. In fact, you can see also a bunch of high-quality artworks that were produced on the right. The work has been exhibited in, for example, the Frankfurt Book Fair, featured in MIT Technology Review, New Scientist magazine, and others. Again, that major media attention. And this scene is from HBO Silicon Valley TV series, I think episode season 5, episode 3. So if you want, and this work is generated by our method. So we took this further to think how this can help fashion, for example, and we partnered with one of the big fashion company in Paris. You might guess what it is, but I might not be able to share that for now. So we managed to. This is something. It is something similar, but the creative space we are exploring here is the shape. So the model was capable of producing these pants with extended arm sleeves. It's not an existing shape in the fashion dataset. The dataset have pants only, pants and T-shirts, and the model somehow turns out came up with this combination of pants with sleeves. So, and that when we discussed this with fashion designer, he found that this can be a useful tool to inspire new generation. It's not, it won't be, it's not in a high resolution that it can be directly printed on fabric, but it shows some promise that this technology can be used to accelerate fashion design industry, especially in the early stages. So going back actually to the birds problem, we actually realized that this wounded curve, like, is something that can relate to also understanding bird species and improving it further. And the way you can relate to it is, let's say you have a bird species like parakeet auklet. You have seen that during training. And there is another bird that looks very similar to it called crested auklet. And you want to tell this apart. Both of them have orange beak. Both of them have dark plumage, plumage that is dark above and white below. But you can see the crested auklet in the middle has a crested feather that comes from the top of its head. But remember, this unseen species has never been seen during training. How the model, from just a language description, be able to tell this apart? We are thinking about it we thought about it in this way. If we have an unseen class, if you want to generate a visual appearance of an unseen class, we want to make it distinguishable from seen classes on the far left. But in the meantime, we don't want that separation to be pushed too far that we cannot transfer what we have seen from seen classes to unseen classes. For example, we know what an orange beak is from parakeet auklet, which is a seen class. We know a plumage, what plumage means from a seen class. So you want to make them relatable, but we don't want to push generation too far to produce totally unrealistic or nonsense generations. So having that is something that we can mention, we can define as the wounded curve for understanding unseen classes. So we similarly, what we did is that we tried to hallucinate language description of unseen birds, plug this into a generator, produce a visual hallucination of hallucinated unseen classes, so that it is hard to classify to any of the seen classes. So I want I'm hallucinating an unseen class. I want the visual generation of those not to belong to any of the seen classes. And when we measure the influence of that kind of creativity-inspired loss, it enabled the model to double its accuracy on telling apart parakeet auklet from crested auklet, which is two classes. One of them is seen and another one is unseen. And by just adding this, the accuracy jumped from like 13 to 0.27 with this area under the curve metric, which is a popular metric to measure the separability of this. So going through this loop, I'm just trying to convince you that this is an exciting direction. It can be helpful to accelerate our understanding of birds, animals in the context of Imagine to See. It may accelerate fashion, art industry, interior design industries, by thinking about it in a similar way. But one interesting thing is that the same kind of loss function can help us have safer self-driving cars. Motion forecasting is a well-defined problem in machine learning, and it's about giving like a driving situation, and I have a car, and I want to predict where the car should go in the next 3 to 6 seconds. So the way I want to, this is a paper that we published at ICLAIR, which is a major conference in machine learning. And the way that I want to share with you today is that we propose something called hallucinative intent and classified intent. Imaginative intent versus seen driving intent. What is a driving intent? It's a latent variable that represents our intent about going some steps in the future to go right or turn left. So for example, turn right is an intent, and then the actual prediction is XY coordinates where I want to actually go, right? So we said that the classified intent is where the training data is guiding us. So the training data lives in the classified or seen intent spectrum. The hallucinative intent is the intent that we want to hallucinate so that it deviates, it's different from the scene driving intents, and hence it will have an augmentation behavior. So it tries to basically predict some intents, some direction, so that it's safe. And this is what we use GAN loss for that, real fake, safe, unsafe loss. And we want that to be different from where the training data lives. And when we hit a car boundary, so let's say when we hit a road boundary, we correct that so that these deviated signals helps the car be safer at this time, and in a way that starting from a baseline without this loss, the road boundary violation, the number of times that the prediction hits the road boundary, got reduced from 19% to 9.22%, which is more than 50% reduction. In another metric like the final displacement error, to the error of predicting the car at the final position, got reduced from 6.7 to 4.9, which is more than 27% reduction by just adding these types of loss. The third direction that I want to share with you today is the art and culture theme that we also are developing in our group, which is about building AI that loves art, and in a way that makes it effectively talk about art, so that we give in an image like this, we can say that the base color of this palette and this watercolor painting is very relaxing. I can imagine myself sitting by the water listening to the birds. In the meantime, I want to also go in the other direction, where I mentioned to the AI that loves art, to use dark color to make it seem as if the ships are going to an anonymous place, and it generates something that you see on the right. And this image that you actually see is a machine-generated art. So I'm going to cover the first part. The first part is called, we collected a huge data set called Artemis, Effective Language of Visual Art. This is a partnership project between KAUST, Stanford, and École Polytechnique. And in this work was published in CVPR. I'm grateful for this wonderful collaboration, of course. And this work was appeared in CVPR 2021 for oral presentation. And there are some, I would say, I'm personally like inspired by Lisa Parrott, who have a very wonderful book about how emotions are made. And it just tries to relate how we feel about things. So if you look at this image, it's just a bunch of blobs, but if you see what it really is, it's a snake, and this makes you feel, identify that this is a snake and it could hurt you. That this might make me feel scared, that this is scared about this painting. So here comes the question that what we can call an art, and it's very hard to define, but one thing I can say is it's something that conveys a strong meaning. And for example, this is a piece of art that I find that this looks like a friend is stretching the wings of her other friend, and this is a message of support. This must feel like there's another famous painting by Kafka who was depicted in a very simple painting, who's holding a toy and giving it to a young kid. And it's a very simple painting, but the story behind it is very interesting, because he met a girl and she lost her toy, and he told her not to worry, don't cry. She was crying, and he asked her hey, the toy is not, you didn't lose the toy, you just went for an adventure, and it will write to you. And then after that, he started a series of letters, making a whole adventure, like chapters, about the story of that toy until the girl has grown up. So this is a very significant painting, and the story is what made this powerful. So we collected a data set that you can tell the difference between it and the former data sets, which is about objective language. So if you, let's say, you choose a topic like birds, in existing data sets, you will see, for example, a small bird. In the bottom part is not our data set, it's one of the seminal works, but in objective, not affective language on images. So a small bird that is on top of a page. On the top, you can see that this is a picture of the bird that gives me hope, and others. So you can see that the difference is to speak with affection, and this relates to how we collected the data. This is the interface of that we use for data collection. We give give participants a piece of art. This is from WikiArt dataset, have more than 80,000 paintings. And we ask people, how do you feel about this painting? And they choose how they feel. And we have 8 emotions: amusement, awe, contentment, excitement, anger, disgust, fear, sadness, and nothing else, like something else. And by that, we then, after they choose this emotion, that we ask them to write a description about why they feel that way. And that's how we collect it. And this is why it's more effective. And this is a distribution of different emotions, like the data for each emotion category. And we have some preliminary results that we showed in the paper that shows that we can have machines that can talk effectively about artwork. So we then circled back and we built a new model called Imaginative Walks to produce better artworks with what we call imaginative walks. It's more like, let's say, these centers, C1, C2, C3 are different art styles. So we built a random walk method that you can think about it intuitively, that we have a walker that starts from every scene class and go for a walk around the center, and go for a walk on a collection of creatively generated images that we want to be creative. And after the model go for a walk, I want it to land in a feature representation that is not relatable to any of the scene classes. So this is a high-level idea. There is some technical details to implement that, but you can think about this, hey, I want to go for a walk from static movement centers through the creatively generated images, and I don't want to be able to go back. I don't want to go to any of those homes. All right. So we managed to generate this. You can see the difference between the quality of this 2021 algorithm versus the older version of CANS. And the interesting thing is that most of these generated paintings constructed actual emotional experiences for people that I think more than 90% of those constructed some emotions like awe, like amusement, like excitement, etc. And our Pacific model generated paintings that are much more likable than the baselines, like with the imaginative walk method. We can also relate that to one-dot curve that you talked about, and the model tends to produce paintings that are in that sweet spot, that are likable and are far from the training data. And it helps both ways. It helps in art generation and also help it in understanding unseen birds. So it's the same thing. We also recently built a model to effectively create art in a sense that you can tell it use dark color to make it seem that if the ships are going to an anonymous place, and this is one of the generated example. These are some technical details, but we built the model in a way that it can extend outside of the training boundaries, that it can generate something like this in the middle, and the model can try to complete from what is outside that red box. So it have a stretching possibility, and this technically was not explored before. So we just did this work in the past couple of months. These are some examples. So an Italian city. So the model on the generation on the far right is the one that's generated by our method. An Italian city showcased beautifully with pastel colors from the vantage point of the garden carpet. So you can see that maybe our generation makes some sense. And interesting to look at all these little details that people are doing. So you can see the state-of-the-art methods, some of our KAUST state-of-the-art method and our method. And this is of course the one that the use of dark colors to make it seem as if the ships are going to an anonymous place. One thing I want to share that we are also like extending this to make it multicultural. So we are currently have an effort to build a model that this data set was collected only on English data. So we're collecting now, extending it for more languages. So this is an ongoing effort. So if you're interested, please, we of course happy to collaborate. So the goal for that is basically people from different culture might feel differently about different things. For example, dragon is probably something very exciting in China, and it relates to festive events, but maybe it's not the case in the UK. So we want to understand this, how different culture feel about different feel differently about visual content, and that's the hope we want to understand in this project. And I think that's one thing I want to also share, that there's a connection between this and mental health, because we're trying to make steps towards having systems that you can have, where you can have a visual conversation, an effective conversation about the visual content. And this might, for example, make, let's say, blind people experience art, because you can have a system that you can give it a piece of art and it can start to talk about it, and maybe the blind person can ask questions about what's going there in this artwork, and that's it. That's it. Thank you so much for your attention.
Thank you very much. Thank you for the interesting talk. If there is any question from the audience, that's time. Well, then I have a curiosity more than a question. I was just like, while you were talking, I was really curious to understand what motivated you to connect something like AI and something which is so emotional like art and also fashion for me, for example. So yeah.
I'm quite passionate about how do we leverage imaginative intelligence to machines. I feel that this is something that is far less explored. So we have code models that can classify, I would say, not just cats and dogs, between thousands of visual categories, but it has a fixed vocabulary. It cannot imagine beyond the learned vocabulary. And I see this as a key element of intelligence that I think it's important, because we need machines that help us report sight of a new animal species. We don't have technology that can do that. And I do think that the only way to do that is to have machines that can understand that this is something novel, and it can tell it apart from what has been seen. And this has, I do think that this has an impact in many fields. Like I was trying to mention, that unseen birds, unseen animals, this is a biodiversity perspective. Accelerating fashion industry, having models that can explore better the creative space and be better creative assistants to fashion and design. The goal is not to replace artists, designers, or the goal is to augment and accelerate their the production of quality products. Self-driving cars, I feel also there is an impact, because no matter how we collect data, there is some situation that have not been seen. So if we have a system that is trained on, let's say, US data, it might not generalize to India or Saudi Arabia, and the opposite also is true. Feeling is something that also is I think we're in the middle of understanding it as well. So I don't have all the answers, I would say, but I just feel that there's something we can. There's so much to learn there, and I'm passionate about that.
So maybe we can learn about unseen feelings.
Unseen, right.
Okay, thank you very much. Thank you again.
Thanks.
Oh, sorry, I didn't see you.
I just have one
There's
question.
A question.
I like the idea that AI can be involved in the fashion industry, and the fashion industry at the moment is quite unsustainable. And as the theme of KAUST Research Open Week is sustainability, do you see AI having a role in making the fashion industry more sustainable?
I think so, because if we produce something that we want to make something that is new and maybe more environment friendly, so we can try to teach the model to be more environment friendly. Another thing for sustainability, also that can be related to that, is also like interior design. So thinking about this in a 3D space, we want to build new chairs, and we're interested to have materials on it, and maybe these types of materials, the choice of them, some choices of them can be more sustainable than others. In car, I was saying self-driving car is also interesting, because machines can make optimal routes, so we can have better, if there's carbon emission, we can have machines, yeah, thank you. We can have machines that are more efficient in terms of cost, in terms of fuel cost, fuel and carbon emission. This can help us have more sustainable environment.
Thank you.
Thank you.
No more questions then? Thank you again, Mohammed.
Thank you.
And now it's time for the second speaker of this session, Paolo Esteves Verissimo. Professor Esteves Verissimo is Professor of Computer Science and Director of the Resilient Computer and Cybersecurity Center here at KAUST. He is also a research fellow at the University of Luxembourg, where he was also professor and FNR per chair before coming here to KAUST. He is author of over 200 peer-reviewed publications and co-author of 5 books. He is currently interested in resilient computer in areas such as SDN-based infrastructures, autonomous vehicles, distributed control systems, digital health and genomics, and blockchain and cryptocurrencies. Professor, the stage is yours.
Thank you very much for the kind introduction, and I'm thrilled that we have, this very interested audience. I loved, Mohammed's talk, and I hope I'll keep you still interested in what I'm about to say. The title is probably an interesting one, right? The day Facebook went down. Go back thinking how you felt, like, what? No, this cannot be happening, right? Facebook doesn't go down. Let me try, WhatsApp. Oh, WhatsApp is also down. And then, of course, you kept trying, and I'm going to explain. I'm director of this recent center. It's about to be a year old, RC3, Resilient Computing and Cybersecurity Center. Cybersecurity is in the hype of the fashion, we know that. Cybersecurity, AI, in the hype, curve. And actually, if you want to know more about, we are slowly starting. We are already 7 professors, and some, research scientists, postdocs, students. We want more. So check that in the URL of our site. So when I started, thinking how would this RC3 thing look like, I studied, of course, KAUST and the country and all that. And I think that what we want to do is create capacity of research that is, of top level, because that's the only way we will appear, and we want, of course, to make KAUST very, very reputed in this area. But if we do that, we attract very good people, we train them, and then they can percolate, in the region, in the country, and so on and so forth. There's a word that, people have been using a lot, which is digital sovereignty. Let me tell you that it's much more difficult than it looks. I had the honor and the privilege to be involved in this kind of work, consulting in the European Commission. I've been connected to it. I was in Portugal and then in Luxembourg. And given the extremely interdependent and interconnected world, this is something that you only achieve if you have the right technologies in what we call the cyberspace. And so that's the dream here. Let's see how we will look back at the dream in some years from now. The scientific points that we are, because we cannot do everything. And so also it depended on the look that we had on KAUST, the country. And we want to be very, very good and create results on what are called cyber physical systems. It's the systems, as I use in the talk, that instead of doing crash, they do bang, they can explode on you. So the systems that are connected to the real world. And the IoT, Internet of Things, are again, and of course, it's your microwave oven, which, if it's connected to the internet, could be hacked in a way that it could also explode. So, it's very challenging. For those of us who like, besides mathematics, we like physics. And so, of course, the classic internet and cloud and web compound is very important, and we want also to be there. Now, 2 semi-orthogonal aspects that we want to be concentrated on are what people call trusted components, because there's a lot, for example, here in the area, in the country, etc., related with control. And control is done through this, boards. And actually, in order for them to work well, despite accidents or attacks, they need to have parts of the system that we call trusted, trustworthy. And of course, everything that computes serves data, and data privacy and integrity are aspects that interest us. And this is pretty much what we're going to tackle in the RC3. Now, if we do that, I think that then we will create value for the university, for the country, for the region. We're certainly going to train people, some of which will stay around, and they will contribute to the transformation, and that's what we expect. Now, let's go back to the title of my presentation. And actually, on the 4th of October, recently, 1551, one of the most important operators on the internet, Cloudflare, and in this layer that stands between information providers, content providers, and content users, us, Cloudflare, detected, oh, something is very wrong with Facebook. And so they were, I guess, the first to come up with a very interesting account that I read with a lot of curiosity. And then later Facebook, VP of infrastructure, came up with an account that we know that Facebook has been under some fire. The account was very sincere, but there was no other way out because other people had already mentioned what had happened. So DNS is the domain name server. So I'll go very quickly. This is not going to be a technical talk, so I'll try to make you understand, some of the acronyms. The domain name server is the phone book of the internet. So, if you want to find someone and, you know the name, but you don't know the phone number, so you will go to the phone book, right? This number, so that's the phone book. And nothing works today if you really cannot get to the address, the IP, the Internet Protocol address. It doesn't work because you cannot possibly log all these addresses, especially also because a lot of us will have varying addresses because we have non-commercial accounts. All right, so suddenly the phone book stopped. Imagine, oh, let me check, where is the phone book? The phone book said, I'm sorry, I don't want to work today. And so this created a very, a moment of instability. And of course, concerning, they stopped working for Facebook, for Facebook. And so if they stop working, you imagine that Facebook and WhatsApp and Instagram, they disappear from the internet, nowhere to be found. And the causes were interesting because it was a configuration change. Someone changed something, and then the thing stopped working internally, right? Okay, internally, we all have problems. We all have problems in our houses, right? But we try for the problems not to go out. But sadly, the fault cascaded, this word that we in dependability use. Actually, let me do a parenthesis. You heard me mention several times this word dependability. So to tell you that, although security became very, very fashionable, it's just because things are happening wrongly very, very much. Dependability is at least as old as security, and it tries to make systems go well despite accidents, not attacks. Accidents, crashes, a disk that broke, a performance crisis in the data center, a partition of a network and all that. Without dependability, dear friends, you would not travel planes. If you were like me, I travel a lot during my whole life, the chance of dying before 60 from a train trip would be very high. Your nuclear power stations would explode, and so on and so forth. That's dependability. Things work on that side. And this will make sense further in my talk. So a fault cascaded, as we say, in dependability. And of course, I work in dependability and in security. I'm a hybrid, right? And so the fault cascaded, went out. And it went out to where? To this very, very sensitive protocol called BGP, Broad Gateway Protocol. What is it? Well, the internet, maybe some of you know, is a set of virtual countries. And thank God, because it's very decentralized. Virtual countries, some of them, not corresponding, of course, to countries, and they're called ASs, autonomous systems. And for example, .pt, .sa, .us, .com, and then some domains are not countries, .com, .io, etc. And they are pretty much, independent, so Facebook, you see, yeah? And then they will talk to each other through this protocol. And you know what? They announce how to get there. And, the fault cascaded because, the BGP thing stopped announcing where Facebook was. It's like you wanted to go drive to Bahrain and suddenly get there. What is the bridge? What is the road? There's no road. No road, Bahrain disappeared. It's that, made simple. And so the fault went external. That was when we discovered, they simply disappeared. All right, so the interesting thing is that it didn't stop there, because had it stopped there, you would say, oh, okay, so let's get back. No, it went out of the control. because, and this is so funny, the humans and the apps had their own way of handling things. And so what happened, you can imagine, you were like, where is Facebook? And so let me reinitialize the computer. Let me try again. Let me, even the apps have mechanisms that you don't see that keep retrying. And so you see, everybody in the world, be it humans and apps, started, where are you, where are you, where are you? And this overloaded stupidly, look at that, I mean, this overloaded, so the queries jumped up. And this, you know, really, this was kind of the end, you know. At that time, things, you know, practically stopped. Now, the Facebook team explained very candidly, thanks. But this was amazing for me, because Facebook said, yes, you know, we you know, during a routine maintenance job, we issue a command which is used to assess the availability. You do a configuration and you issue a command to assess that everything is available, and the command rendered the infrastructure unavailable. That's very interesting. And of course, if you work in dependability, you say, what? Yes. And then they have an auditing. It's typical that you have an auditing program, a monitoring program that follows what's happening so that, hey, don't go there. But that program had a bug. And so that program did not understand that something was going wrong. And that, you know, also from the dependability viewpoint is, no, you don't do these things. That's dependability is for avoiding these kind of things. And then, of course, then they did the right thing, which is manually try to go there. I don't know if you know how the world is. These data centers that you hear about, most of them had no one there. They're in the middle of nowhere. They're unmanned or unwomaned, you know. Yeah, I invented the word. And so they discovered that we have to go there. Why? Because we cannot access the data centers remotely, because that's how you do it. So there's nobody there, and you are in the middle of a city, big city, and you are accessing all these things. And so the interesting thing is that if you realize again, the DNS, you know, broke the internal tools that we were using to investigate outages. And this is also amazing. So they had a monitoring system for investigating outages that would go out when an outage would occur, which is, you understand, right? That's probably not the best way of thinking about it in dependability terms. And then, of course, they really, really understood we have really to go there. And then when they got there, they had serious trouble going in. Why? Because there were so many hard measures to really prevent, you know, attacks, you know, prevent people from entering there. And then finally they entered, and then they again had a hard time entering logically, you know, logging into the computers. So that was very interesting again, and I'll get back to it. You see, when they finally managed to go into the things and put them working, they had another problem, and this is the only problem they solved rightly. And that's about resilience, yes. So when you have major outages, even normal outages in town, and maybe KAUST already had that, you cannot restart everything at the same time because it creates a surge. And the surge says there's something wrong and brings the whole thing down again. And you would have that problem. So you have to stagger the recovery, be it of energy or networks or whatever. So that part, they did well because they had been rehearsing when the storm happens. So this is super funny, and actually I had a company time ago, we would do audits, dependability and security audits of companies. And classically, the companies would prepare for, you know, fires and earthquakes and blah, but they would not prepare for informatic storms, informatic disasters. So they had been prepared, so the only thing that worked is because that part of the resilience, they had already thought about it, and so they restarted the things hours later. Now, the last bullet is a very important one. Remember I told you security, dependability. But this is classic things that had been working in isolation. And actually, there was a huge security dependability gap in their mind. Why? Because they hardened the system so well, so strongly from the security side, that from the dependability side, they cannot fix the problem. They could not recover from the outage that was caused by an error. So things to be learned. Okay, so a few notes before I move on, which is the best resilience was with the people, because people then, and people in operators, even Cloudflare, they said, okay, this is down, let's go somewhere else. And so they saw, queries peak to the other guys, Twitter signal that were working. But this was diversity. So this is something that you use in fault tolerance. You just follow a diverse path and try to get there. But made by hand, and it's a poor outcome. So let's stop here and think, okay, so that was really bad luck. No, because this is not the first significant problem with Facebook. So obviously, this goes back to the mind of how their techno structure, gets to these problems. And, I'll just let you read, but there were several problems already. And some problems were really, be it security, also stored passwords in plain text. That's really worrying. And then, of course, the Cambridge Analytica and the whistleblower, that Frances Hogan, which I had the privilege of hearing in the Web Summit, the recent Web Summit that happened. Okay, so, but still, is it just this company? No, of course not. Fastly, Fastly does something similar to what Cloudflare does. It also went down, and then since it went down and it stays, as I told you, between the content providers and the content users, a lot of things disappeared. This was not so recently, but this year, in June. And actually, it was pretty much the same thing. Fastly took down its own network with the bad software update. So we keep seeing these things that have to do with violation of very important principles in dependability. If we went to analyze the Fastly thing, there was someone, highly responsible saying, well, for a system so complex, full of interconnections, any one fragile part can bring it down. This is the denial of dependability. Actually, were it like this, you would not fly planes. No, it's what we call the single point of failure syndrome. You cannot have a part of the system that is responsible for bringing the whole system down. You build these things I told you about nuclear power stations, trains, blah, blah, blah. You build those systems so they don't have single points of failure, so that then they can fail gracefully. Get weaker but still work. And then some other person was saying, yeah, but the companies can switch. Yes, but that's improvised fault tolerance. That's not how you do it, because those configurations are themselves also subject to errors. The good thing is that there's a word which we use in dependability called mean time to repair. And in Fastly, not in Facebook, it worked very well. It was under an hour. So the recovery, the mean time to repair, if it's under an hour, it's not fantastic, but still it's acceptable. Now, this was an accidental fault. It was not malicious, a configuration. The Facebook VP said that. We have to believe him. There was no malicious activity behind this outage. So, of course, now you say, I thought you were running a cybersecurity center, and you kept talking about dependability. Hey, please explain this. Well, that's the point. You see, some of us over the past 20 years or so have been telling that whatever is wrong in your system will be used by the bad guys. What can be used can be abused. All the actions done, you might say it stupidly, that brought Facebook down could have been done by the bad guy bringing Facebook down. This is what in my classes of security, I call the well-behaved hacker syndrome. It's like you say, good morning, Mr. Hacker, welcome, and here's the list of, you can only attack here. Thank you very much. No, the hacker will attack wherever he or she wants if it has reachability. And so, in case that still you say, well, yeah, but that's not the same thing. There's cybersecurity, that's really for the bad guys, and the dependability is for accidents. Well, let me tell a little bit. We have been working on this area, autonomous vehicles, I don't know if you know, but there's a certification process, not just for cars, which is a very interesting process where people thoroughly review what's going on in this architecture and so on and so forth. And in the end, they produce a report and saying, to the best of our knowledge, industry practice, blah, 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 we certify that whatever residual, probabilities of faults in the system carry an infinitesimal and or acceptable, it can even be quantified, right? Probability of catastrophic failure. So the system can fail, but doesn't kill people, doesn't blah, 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 okay? So this is accepted. And during years, talking with these people, I've been in some meetings with this kind of people, the innovation and research people in car makers, they will, when we started saying, but you see, there's the hackers. Your cars, especially when you started connecting them to the internet, they can be hacked. And they will say, yeah, but then, it's in infinitum, even if they're hacked, it's not, no, that's the problem. You see, over the years, people started understanding what I just said, minutes ago. If the defect is there, now it becomes called a vulnerability in cybersecurity lingo. There's a vulnerability, and the hacker being able to reach it will attack it definitely. So will be attacked. It's not may be attacked. And if he or she can, will cause a catastrophic failure. It's just, and some of us know how to do that. So you see, this is very interesting. And actually, in a paper that we published in a workshop of CCS in 2016, we were, I guess, the first to provide this system-level view, because at that time there were already several hacks, but it's the hack to this, the hack to that, etc. And we gave the view that this is really a problem. And it's got to do with the autonomous car ecosystem. And whatever defects that are there, that it tried to, because the defects you try to solve them for accidental causes, so you're happy. You get some 0.9999 of reliability. But this, if it's in the hands of a hacker, he doesn't like stochastics. Hackers don't like stochastics. They have this problem. And so they will make it happen, and it's no longer several nines. All right, so this introduces exactly the word resilience, because resilience, this is from the dictionary. The property of resuming original shape or position after being bent, stretched, compressed, elasticity, plasticity. And you will say, what does it have to do with computers? Well, that's the point. Imagine that Facebook was doing this, and the system shrunk, etc., and then in minutes, it gets back to the original shape. This can be done. There's a lot of research now. This is a field that has developed during the past 20 years. There's a lot of, so there's a lot of artifacts, and this is not what my talk is about. There's a lot of artifacts that can get you this. And you see very quickly, it's like this. You must build systems with baseline defenses. They have to be there, even if you're selling T-shirts, so to speak. And then you have to be able to configure those defenses, be it accidental faults, design or configuration errors, here we go, cyber attacks, unexpected operating conditions. It has to solve all this. And until now, or until recently, systems would either solve, configuration blah, or accidental faults, or attacks, or whatever. No, they have to work together. And do it in an incremental way, being able to adapt then to increasing levels of threat, for example. There should be no such thing as, my system resists this hacker that is not so good. Does it resist the, nation-state hackers? Oh, no. No, it should be incremental. And then, and this is where the frontier now stays, and this is what we are doing here now in the research about resilience in KAUST, is the system should work forever. So there should be rejuvenation, which is also something like looks like science fiction, but actually there's quite a few works about that, systems that rejuvenate, that self-heal, special, not only in software, but in hardware. All right, so now you understand, if because of the notes I made, you will remember that Facebook missed quite a few of these rules. So that's the point. So, and actually, just let me give you then, a little, and I'll finish my talk giving you little pointers to how this could be done, to techniques that emerged from research in the recent years that really could take care of that. Cloudflare commented that actually this is what they tried to do, and actually some people could try, well, if it doesn't go this way, it can go that way. So, but that's manual. And of course, if you do it manually, it's non-principled and prone to error. It's going to be slow, and probably several people are doing it in an indisciplined way. So although it worked for some people, that's not the way you want to develop it. Now, let me show you how this is done under a resilience perspective. These are quick slides from a project that we were involved some years ago. Now, this is, SIM is, and now you understand how things are interconnected. SIM is Security Information and Event Management System. So see, this is a typical cybersecurity and dependability thing, because actually they care, this kind of systems care about accidental faults and malicious faults. But to be done well, but that's what we're saying at this time, because the architectures would not, so at this time, we were at the point of architectures that would have the same problem of Facebook. They were trying to monitor from inside the architecture. We were the first, this group of people, it was a European project, to say, no, you have to have an overlay, you have to have the red thing, which is overseeing the blue thing, so that if the blue thing fails, the red thing should not fail, which is typically what we saw happening in Facebook. And so you have then to have a systemic view. You cannot think about this component or this component, because when you do these configurations, if you don't have the global perspective, you're going to fix something and break two. And so this is what people call a threat plane. So these are threat vectors. So this, what can go wrong in this kind of the blue system, and then we design the red system so to see what's going on. Now, the interesting, there were more slides, but what I want to bring here is how the networking aspect should, and I hope they think about it, be done, which is with systematic path redundancy, and even, you know, something that today is being used, which is sending always through diverse routes a piece of the information, so that if some route breaks, you can go through the other way. And actually, I'm very glad to have seen a post from my friend, Professor Adrian Perrig, from Switzerland, ETH, which is a great school. And actually, he's been pursuing, you know, a dream, which is called SCIEN. And SCIEN is the new resilient internet architecture. If you go see the post, it's saying pretty much similar things that I'm saying, which is that would the network architecture follow SCIEN principles, it would not have failed in this way. Okay, so you might say, yeah, but okay, so that's networking. Maybe the rest of the world doesn't suffer this. I mean, do we need to really do a big change, a big move? I don't know, but I'm sorry to disappoint you, but it's ransomware attacks, it's the Amazon or whatever cloud failures, it's the, you know, autonomous vehicles that are killing people, having crashes, power outages, problems with biomedical data privacy, well, Facebook. The recent thing you heard, the Colonial Pipeline, right, that stopped in the US and all that. So obviously, this is a common problem. And so, you know, complex problems need complex solutions. I'm sure you heard Einstein's famous quote, or attributed to him, right? Things should be as simple as possible, but not simpler. So really, maybe we have to you know, rethink our way of doing cybersecurity classically, and think about what serves, you know, the problems that these big things can happen. And actually, you see, it's the internet, cloud, and web, you know, complex, which is central to this thing, and then cyber-physical edges that have to do with factories and process control and connected cars and transportation networks and so on and so forth. And to tell you another part where resilience techniques have been solving problems, you see that cloud thing is today on the verge of being this what I call single point of failure. And because the infrastructure is cloud-based. If you're not believing that very, very much, do you remember WannaCry, the ransomware virus or worm, whatever you want to call it, in May 17? You see, it was devastating. That was really reclining, wow, single point of failure from the viewpoint that a single thing could, you know, bring down a huge amount of things in several sectors. By the way, the e-health sector, you know, the health was one of the most affected because at that time, and regrettably still today, it's a sector that does not understand that we really need security and dependability. But anyway, techniques invented some years before that, and now they're penetrating industry, it's always that, would have minimized dramatically this problem that seemed to be a huge problem. So ransomware could be minimized by a technique that was invented around 11 called DepSky. And DepSky combines security and dependability techniques. I don't have time to go into details, but essentially what it does is that it gets your piece of data, it could be a file, right, and then just extrapolate to millions of files, and hashes it in pieces, and then do some coding to add some redundancy so that if you lose some pieces, but not all of them, you can still recover the file. This is beautiful, see, because then a part of the system failed, but the rest recovers it. And then you encrypt it. But you encrypt it with a very nice technique called secret sharing, which is the key is split also in little pieces, so that if someone gets a piece of the key, he cannot decrypt. And then you put both the pieces of the file and the pieces of the, I'm sorry, but the pointer doesn't work very well. This is too modern, so we cannot point laser. And so and then that's the secret. It's put in several clouds. So the concept is stupidly simple. Instead of using one cloud, use several clouds, because they will not fail all at the same time. I mean, we hope, but it's a decent assumption. And then if they don't fail all at the same time, we can always recover our stuff. So this was the principle. And then, several colleagues, for example, from IBM Zurich, were building on this principle to create file systems. It got also, to a file system that would imitate pretty much the Dropbox metaphor, but all never fail. And actually something in biomedical, so a highly protective, information system for biomedical data. All right, so, approaching the end, you could see, yeah, but okay, so how much of that is okay, nice research, we believe, but how much of that will ever, get it? Well, in the US, okay, when I arrived in Luxembourg, doing maybe resilience 1.0, so starting, my team in Luxembourg that was working in resilience, General Rogers, who was at the time both the leader of the Cyber Command, which is the cyber defense part, and NSA, the fundamental cybersecurity agency in America, was saying, quoted publicly, oh yeah, intrusion prevention, prevention, which is the classic cybersecurity workhorse, is nice, but we better do resilience. We better keep things going while we're attacked instead of trying to bring a wall that is never penetrated, because that's impossible. And he was saying that in September 14, the month I arrived in Luxembourg. That was very good omen for what we did and achieved in Luxembourg. And we had a lot of fun, creating new techniques around this area. That combines security, cryptography, dependability, and so on. But much more seriously is that the European Union, who took some time to wake up to this, in the beginning of this year announced their cybersecurity strategy. It's a 22-page document. I love it because strategy is hard to be short. And it repeats the word resilience some 30 times. And a good dozen of them are about resilient computing, resilience in the computer world. So yes, we will see, and we are seeing that. And so I'll leave you with my quote, the quote that I really like, and I believe this is the quote that you can find on the page of RC3. Resilience is the cybersecurity of the 21st century, and we are ready to cooperate, hire brilliant people that want to work with us in developing this. Thank you very much.
Thank you very much again for this amazing talk. So now is the moment for questions from the audience. No question? Okay, we have one.
Hi. So thank you for the talk. My question is more related how we communicate this with the general public, and also how can citizens be more aware about what is cybersecurity and how this impacts their lives. So we know this from the catastrophic level, so we're talking about right now, for instance, if how can the things like nuclear plants can be hacked and can be accessed from far away. But on our day-to-day lives, now we're talking a lot about data sharing as well, and it's a problem, privacy. But what do you think is the biggest challenge in making people aware that this is a really important topic that needs to be discussed? Because throughout history, we talked about security. Okay, I'm in my house, I can close the doors, I can get, in our countries where you can get guns to defend yourself, but this is something different. This is another level of security that I think most of the general audience is not aware of. So do you find that communication in this field is something really important?
Yes, that's an excellent question. You know, one of the things that we all had to learn when we started working in this area is that this area carries a different, social weight than other equally meritable areas, like, thinking about here, desalination or climate change or whatever, they're all super important. But of course, security carries this weight. And I'll be more obvious when I explain now that, to answer now your question, I think that the biggest problem is lack of transparency. And it's difficult to handle that. We are taking steps, but it's certainly easier to handle it in countries that separate cybersecurity from cyber defense. Because let me make this clear, both of these things are important to countries, except that with cyber defense, you can be less transparent. This is the defense of the country. With cybersecurity is the society. And this has been, compounded in several countries. It's not a criticism, not in my origin country. But the countries that separate cybersecurity and cyber defense are able then to present a much more transparent view of what the problems of cybersecurity, and even create education and literacy, above all literacy, in this domain. They separate how you live your life every day and what the military do to protect your country, which is very important. This said, on the industrial world, I think that GDPR, which originated in Europe, I think it's contaminated, in a good sense, it's contaminating other countries in the sense of, companies, organizations have to be very, transparent about what they're doing. And GDPR is related to data privacy, but there's a companion specification that has deserved also interest. Actually, let me tell you, I had the privilege of being consultant to the Brazilian government on cyberspace policy. And of course, I addressed this part. And it was very interesting to see the reactions of people exactly in terms of we should be honest, if you want, transparent about how things happen, but this because it's the only way we can explain the population what are the problems. So your question, I wanted to be more, I want to elaborate it more because, yes, now you see that the problem is complex because it has a lot of ramifications that other more civil aspects don't have. But I continue thinking, well, whatever system, it's for if you want to protect the nation, you should be transparent to the nation about what may happen. Thank you.
Hello. Thank you. Your talk was really interesting. I just had a question based on your cloud of clouds.
Sorry?
So the cloud of clouds.
Cloud of clouds.
What would happen, for instance, if a group of hackers got together and attacked simultaneously all of your clouds in your cloud of clouds? What are we doing to future-proof ourselves? So obviously the resilience is something that, emanated from problems that were in the past. So looking towards the future, what do you think the potential next threat will be?
You go to your house on the beach or on the mountains, which in principle should not have my advice. I managed to do it during a lot of years in this 2 weeks that I would spend on the house on the beach in Portugal. I would not, I would not have internet, but then my kids, blew it up. So now we have to have but actually, half joking, let's try to train yourselves to live without a smartphone and your PC during, I won't even say a week, a day is already enough, I think. And so learn, meditation techniques and all that. Now, okay, now to be serious, because, yeah, that would be the doomsday. All that works fails. And when I said that I love physics, and my only advantage towards my colleagues who specialize in mathematics, like I do, of course, but their training did not include physics very much. I don't know if you know that, but that's the typical training of many computer scientists. They don't have, they have one course of physics. I have 4. And so, since I love physics, I learned to understand that it's not all about data. Data doesn't compute. Data is data. And if the system doesn't compute right, there's no good data. So you see, the systems then will fail because it is important, because data is so abstract that my colleagues, super bright colleagues, focusing on data, they don't see this because data doesn't fail. I mean, it's numbers, algorithms, and all. I do algorithms, but I know they compute on systems fail. So all that works fails. There's a phrase used, and I like it, of course, which is, a provably secure cipher. What is a provably secure cipher? It's a mathematical, artifact that never fails, and it's really encrypts and blah. But the moment you build it, you put it on a system, there's no provably secure system. It doesn't exist. And then you say, oh, but then we're doomed. No. You do a good system, that's the kind of things I do. You do a good system whose reliability, which is the probability of never failing, is 0.999, and you go on 99999. It's parametric. And now I can answer your question. That is not impossible, but depending on where you are, it can be made infeasible. Just buy more clouds. But, super highly motivated, aggressive, blah, 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 they will spend, thousands of millions, but that's life. There's no risk-free life. This said, then, you understand that for most of the things that you're thinking about, 4 clouds, there are, of course, the papers have statistics, 4 clouds get you to, I don't know how many nines, a huge, incredible 6 or 7 nines, which is already, attacking all of them is really very much infeasible, for even very skilled hackers, yeah. But thanks, that was a very good question.
Since there are no more questions, so let's thank again.
Thank you very much.
Professor. Thank you for your interesting talk. And I just want to remind you that there's going to be another keynote talk here at 6 p.m. So join us for the next talk as well. Thank you.
Hi, and welcome back. I'm Carolyn Unk here, the Manager of Research Communication at KAUST. And for our first interview during Research Open Week, we welcome Atif Shamim, who is a professor of electrical and computer engineering. Welcome, Atif.
Thank you so much.
How are you doing today?
Awesome. It's nice booths out there and lots of technologies, so I'm enjoying the week.
Great. Thank you for being our first guest.
I didn't know I'm the first guest, but okay.
So tell us, Atif, tell us a little bit about your research, the scope that fits maybe into sustainability in line with our theme for the week.
Okay. Yeah, for sustainability, we are actually looking at from two angles. One is with respect to the environment, and the other is with respect to the renewable energy. So with environment, you know, there's a lot of emphasis on this, especially talking about the Saudi Green Initiative. And the problem we see, or which we are trying to solve, is that a big area in the kingdom, actually in the world as well, but in kingdom particularly, is not monitored for air quality or environmental conditions. And the reason is that there's large area, and to put an infrastructure there with lots of sensors or weather stations is very, very expensive. So we look at this problem. If we can solve this problem if we can make like very low cost, dispersible, kind of disposable sensor nodes which have the wireless connectivity, and if these can be, let's say, spread out or dropped maybe through a drone or another way into large areas, and these can sense the environment, like the air quality, and then they can send this information through wireless connectivity to the servers or to the decision makers. So you are basically real-time monitoring that's what is missing. So any abnormalities or changes in that they can be reported, and of course corresponding actions can be taken. So as a first step, you need to monitor and find out the problem. So we are looking at that from protecting our environment, which is part of sustainability, through these wireless sensor nodes or wireless sensor network aspect.
Okay. What kind of challenges might you face with having these sensors everywhere, monitoring our environment?
That's a good question. Actually leads to my second part, which is the renewable energy. Now, if you are throwing or dispersing millions of sensors nodes for monitoring, and with changing their batteries or even charging their batteries or replacing their batteries is a nightmare. You cannot do it. It's almost impossible. So this means that you need to find a way where these either batteries could be charged or these sensors could be made self-powered through the ambient energy. So ambient energy harvesting. So that's another part of which is linked to sustainability, is that we are trying to create useful electricity, of course, for these wireless sensor nodes from the wireless signals which are all around us. So this is called radio frequency energy harvesting. And we are also trying to harvest energy with our partners in this project is MIT from USA, which is the day-night cycle. There's a temperature difference, and from that day-night cycle we can actually harvest energy. So from these two modes we can harvest enough energy to power these sensor nodes by themselves. And now question may arise, you know, there's solar energy all around, so how does these two technologies fit in? So there are many places where solar is not available. For example, in the night, in bad weathers, indoors, even so underground, you know, tunnels. So that's where these sources are very, very important, where solar is not available. And we have shown that we can actually harvest energy even if the sensors are embedded in the ground.
Wow.
So the challenge of powering these sensors is huge, but I think renewable energy is the answer to that.
Sounds great. Does your booth show any of this work, Atif?
Yes, actually the booth, which is the first one on the extreme end, shows these both these wireless sensor nodes, as well as it shows the energy harvesting modules, both RF and thermal energy. So everything is actually displayed there. So anybody or the visitors who are interested in this topic, they're more than welcome to come to our booth, and we will be able to show more and explain more to them.
You have some nice visuals there, I bet.
We do have, and you know, we would love to host people come to our booth, and we can talk more about this.
That sounds great. Thank you so much,
Thank you so much.
Thank you.
For having me here.
Thank you. Bye-bye. Welcome back. I'm now joined by Manuel Aranda, Professor of Marine Science. Thank you for joining us, Manny.
Thank you for having me.
A lot of your work sits, I think, very closely with sustainability. Can you tell us a little bit about how your work pulls in sustainability?
So I'm working on corals and their abilities to acclimate and adapt to changing environments. And this is, of course, a very hot topic, given that climate change is having huge impacts on coral reef ecosystems. So we've been losing coral reefs at an unprecedented rate due to what is called coral bleaching. So heat stress events due to the increasing temperatures lead to the breakdown of the symbiotic relationship the corals have with their algae, which then leads to what we call bleaching. The colonies become pale white and basically slowly starve. And if the temperatures don't go down, then they basically die. And this happens on a massive scale. So we're basically using entire coral reefs throughout the world. And to put this in the context of sustainability, we're talking about an ecosystem that supports 25 to 30% of all marine animal species. So yes, small surface area, about 0.1% of the ocean floor is actually covered by coral reefs, but supporting almost 30% of all species. So you can envision what kind of impact it would have to lose these ecosystems for our oceans, right? So from a sustainability perspective, these ecosystems are essential for a healthy, functional ocean, and this comes with all the services this environment provides to us, from fisheries to just mere things like protecting our shorelines from erosion, which is very important to many of those small island states in the Pacific, if you think about it, but also other regions in the world, to ecotourism. So there's many countries where a lot of people rely on these ecosystems as the main source of income, from people who come, go diving, go fishing, and just enjoy these beautiful ecosystems.
Okay. This sounds very much like what you had written in KAUST Insight, our new research publication. You quoted, "The temperature is increasing so fast that corals might not be able to naturally adapt." So what should we do? If they can't naturally adapt, what options do we have?
Help them.
Okay.
Right? And that's where I came in. So originally I'm an evolutionary geneticist. And when you think about the current problem, corals have already endured much hotter temperatures, right? They actually were born 240 million years ago, right after the largest extinction event, you could say. But since then, they have survived the extinction event that killed the dinosaurs. They have survived the highest temperatures on Earth about 54 million years ago, the EMT. But during those times, they were basically facing temperature changes that took place over hundreds and even thousands of years. So as every other species, they could slowly adapt to these increasing temperatures. And sometimes when the temperatures went beyond what they could handle, you would see that coral reefs mostly disappeared and they survived in little patches. And once the temperatures got better, they basically bounced back and started building big reefs again. Now, looking at an ecosystem that provides essential services to us, we're now looking at the problem that the temperature increasing so fast that this natural way of adapting doesn't work. Very likely they will not go extinct. They might bounce back like they did before. But for us humans, it would mean that we lose a very important ecosystem that provides essential services. So they provide livelihoods to more than 500 million people. So what are they going to do if we lose them? So the way we think about it is that if the natural process of adaptation is too slow, the only way to move forward is to try to speed it up. And that's what we do with things like selective breeding, for example. We've recently shown in the publication that if we pick the right parents, we can produce offspring that already has about 3 degrees higher temperature resilience than if you would use just the local parents that you find. So by selecting specific colonies and making sure that they can procreate faster and more broadly, we can maybe change the population structures and increase the number of colonies that will be more resilient. And to do this at a pace that allows us to maintain ecosystem functioning until, and this is a very, very important thing that needs to be stressed, we manage to curb emissions. Because like I said, there's a natural maximum level of temperature that they can withstand. If we do not stay below that, then anything we do won't be helping, right? So the only thing we can do with this is try to buy time. At the end of the day, we really need to curb our emissions to make sure that whatever we do will be fruitful also for the next generations.
Right. It's all connected, isn't it? And there's no one answer or one thing that must be done. It's a little bit of everything, which is, I guess, why it's a suitable topic for an open week about research, because just about everybody's research can contribute something. So that's really nice. And you have a booth here as well, right?
I have a booth.
What will I find if I stop by your booth?
So what you do there is, I mean, been talking about the research that we do, how we can speed up the process of adaptation, right? But this doesn't change that you still need to go out in the field and bring those individuals that you identified into the field in a way that allows them to actually procreate more efficiently and produce more babies. And for this, we have developed several products for what we call coral gardening and also coral nurseries. So the idea is current efforts are taking out corals from the environment, growing them in land-based nurseries or even in nurseries in the water, multiplying them and then bringing them back to the reef. Problem here is that you bring back exactly what you took out, right? So now we need a platform that allows us to implement all of these things that we research, so selective breeding, environmental hardening, so that we can bring out something that is more resilient than what we took out in the first place. And to do this at a much lower cost. The problem with corals is they need to go back into the water, which requires divers that then glue each fragment onto a suitable substrate, and this takes time and is quite expensive. So we're working on a platform that allows us to grow the corals already in a nursery in a way that allows us to track each individual and to learn about it, what is it that it likes, what are the environmental parameters that it prefers. Then we have a platform that allows us to bring in more fragments much faster. We're currently working on a Twitter challenge for one of our tiles that we use in the system that allows us to place about 50 fragments per diver per half an hour. This is about 5 times faster than any other method that is currently used in this field. So the idea is to have a complete platform where we can do the research, the selection of the right individuals in the nursery environment, understand where each fragment should go ideally in the reef so that we make sure it's happy and has the best chances of survival, and then being able to bring them out in larger numbers at larger scale to really tackle the problem at a level that, that is meaningful. To give you an idea, during the past decade, we have lost about 50% of the Great Barrier Reef. So it's a massive scale we're talking about. It's about the size of Italy. So imagine half of Italy and to be repopulated by actual corals, people planting them by hand. So this is a scale that is crazy to think about. So anything that we can do to speed up the process and to at least start restoring some parts so that these beta corals can now slowly take over the populations and spread out of the small area that we work on, is for us currently the best way forward to gain the scale that we require in the long run.
You mentioned 500 million people's livelihoods depend?
Yeah, likely more than that.
Will there be a stage where these people can take part in?
This is the idea, right? At the end, because we always talk about things like the Great Barrier Reef, but what about all these island countries in the Pacific? What about countries like Indonesia, the Philippines, where people are much, much poorer, where people really rely literally on coral reefs for the food on their table, literally, right? So the idea is to find ways how we can, for example, sell our products to rich people, like corporations that have large ecotourism projects, for example, and use that money to then fund restoration efforts in parts of the world where people cannot afford these things, but actually really rely on these ecosystems, right? So we're basically looking currently at different ways how to do that and to translate our science that we do to a broader, more meaningful scale.
Great. Well, that sounds good. I'll stay tuned for that and check out your booth later.
Thank you very much.
Thanks for joining us, Manuel.
Bye.
Bye-bye. Welcome back, everyone. I now have Hussein Hotay. He's a professor of petroleum engineering. Welcome, Hussein.
Thank you, Caroline.
So Hussein, when I think of petroleum engineering, sustainability isn't the first thing I think about.
Sure.
But I bet you've got some tricks up your sleeve. So please tell us how your research aligns with sustainability.
Sure. Well, thank you, Caroline. Yeah, as you mentioned, actually, I'm a professor in petroleum engineering. So our main focus is related to how would you produce more oil, and more efficiently, and in an efficient way and a cost-effective way. But as you know now, there is the the emerging challenge about the fossil fuels and its impact on the environment, greenhouse gas emissions, which is now a big challenge, right? And this is already recognized by essentially everybody that this is a problem now. At the same time, the fossil fuels remain a primary source of energy. And we all agree that renewable energy from solar, from wind, geothermal, and others are the energy of the future. So this is, I think, everybody agrees on that. But these technologies are not ready yet to displace or replace fossil fuels, all right? So all the calls right now to stop producing hydrocarbons, for example, and fossil fuels, it is not reasonable, in the sense that this technology, the alternative, is not ready yet, right? So we're going to go through some transition period, right, until actually get ready. And you've seen now many countries worldwide start to, announce, put their plans for emission, net zero emissions by 2050, 2060, and so on, right, for that. Now, until then, we need to find some solutions, right? Fossil fuels, especially oil and gas, will stay, a source of energy and primary source of energy till then. And this is where our roles comes in. What can you do within this transition period? Whether it is 30 years or 40 years or 50 years, you cannot keep emitting, right, these greenhouse gases to the atmosphere. So based on our experience as, from the petroleum engineering, and this industry has a long experience in dealing with fluids, in dealing with gases, including carbon dioxide. And what we're working on right now, we try to switch or give a bit more attention to the environmental aspects, especially about CO2 emissions. So now, besides producing oil and gas, now we're trying to say, all right, what can you do about the emitted CO2? Can you capture this CO2 and do something about it? So this is where actually it comes. We have several projects we're working on right now. Some of them are related to reusing this CO2 for enhanced oil recovery, where you can entrap CO2 in the hydrocarbon reservoirs while actually producing oil. And then there's also other technologies related to capturing CO2, storing it, or injecting it into deep aquifers, and entrapping it permanently in underground.
Wow.
So, and of course, there's different challenges for these technologies that we are working on right now.
Okay. What's the greatest challenge, would you say?
Of course, this technology, it has two main components in it. One is, the capture part, right? So when you burn hydrocarbons, like gas, say, or oil, we use air, right? Air actually goes to the combustion engine, and with that, you emit basically nitrogen, for example, and other gases besides CO2. So when we store, the main actually challenge is mainly for CO2. CO2 is the if you like, the major component in these gases. So we need to separate it from the other gases, to capture it and eventually transport it to inject it in the subsurface.
Okay.
So one of the key challenges of this technology is how you reduce the cost of the capture right now. So the technology is there. We know how to capture CO2, separate it from the other gases. But there is actually cost component to it that is still preventing this technology to be extended at large scale. The other component to it is, once you capture this CO2, now you need to compress it, drill deep wells, and inject it in what we call the reservoirs, which is underground formation that can entrap that CO2.
Okay.
So in the other component, that once you inject that CO2, you need to make sure that you don't perturb the this subsurface in terms of seismicity, for example. You don't damage the underground formation. You don't create, let's say, fractures or faults that eventually may allow that CO2 to leak and escape and get back to the atmosphere. So there is several engineering aspects that we need to study. We look at the rock mechanics, for example, the strength of the rock. We look at the CO2 interaction with rocks, like CO2 can change the acidity of water, for example, underground. It can dissolve some minerals, precipitate other minerals, and also interact with the subsurface fluids. It can dissolve in brine, for example, which is the saline water underground. So all these aspects need to be studied. And this here we have in our lab, actually at the Ali Nuaimi Petroleum Engineering Research Center. We look at these different mechanisms at different scale, starting from the molecular scale, looking at the micro scale, looking at how would that CO2 flow in the pore throats or the small spaces within the rock, how they flow within this rock, how they get entrapped within these pores, and also how they react with the rock. And then we take it to another scale. So we're going from the micro scale, we take it to a larger scale, which is a lab scale or core scale. We take rocks, we put them in the what we call core flood system, where we can mimic the subsurface conditions, like put it at high pressure, high temperature, inject CO2, see how that CO2 could displace the existing fluid, and then how it interact with it. Also, we look at the different mechanisms related to long-term mechanisms like reactivity, how would the reactions happen, and so on.
Okay. The monitoring, you do have to do quite a bit of monitoring of what's happening underground.
Right.
Is my memory correct in that you have a collaboration with Professor Satoshi Habuchi on this work? And actually we covered it in Insight. Right. So have you had a chance to see your story yet?
Yes, I did.
You had?
Thank you very much for it.
Is it what you expected? Was it what you hoped it would be?
Yeah,
tell the story behind the discovery?
And I think this is what's fascinating here about KAUST, right? Having all this expertise and the multidisciplinary activities and work, because these problems are really major problems, right, that we're dealing with. Okay, and it is beyond the capability of one disciplinary or one institute or even one country. So it requires collaboration, right, from different aspects, different disciplinaries, and so on. And then that work that you mentioned with Professor Habuchi is although they are in the bioscience, right, technology, and we're in the petroleum engineering, so
seemed like such an unlikely coupling.
What's the coupling between these two? And for that work, because I mentioned that we are interested in understanding these fluids at the molecular scale, right? They are important for us because they are what determines, how these fluids behave, how they interact with the other surrounding formations, and so on. And working with Professor Habuchi helped us to try to look at that scale. And this is something was beyond our capability in the past. So we're able right now to tag some molecules and tag them, meaning that we put some fluorescent particles to them. And under the microscope, we're able to see at the dynamic conditions. So as these molecules flow, how they interact with the rock, for example. How would they get absorbed to the rock, get attached to the rock, and how they flow within the pore throats or the narrow channels within the rock. Sometimes they get tangled with each other, they accumulate, they can clog some pores. And this is something that we know from theoretical part that this is happening, right? So we have some analytical models that describe how these fluids flow, and interact. But this was the first time we're able to visualize them, look at that scale, and see, how this happens for it. So this was a great, great achievement in terms of actually trying to understand and helping us understand how this mechanism happen.
It's so helpful to be able to actually visualize it with your own eyes. A model is helpful, but great to be able to visualize it.
Right.
It's such an interesting collaboration, so I hope everyone will check out the story in KAUST Insight. Professor Hotite, is there anything about your booth you'd like to tell us before we head off? Or should we just tell people to pop over and have a look?
Absolutely. So we have very exciting booth here. There is three projects associated with it. And I need to mention about my collaborators on it. So one, we have Professor Carlos Santamarina, Professor Abud Afifi, and also all the other faculty at AMPARG as well. So three projects on them. One is related to CO2 mineralization in volcanic rock. So we have some rock samples that actually shows how CO2 get mineralized naturally, actually turning CO2 into rock. Okay, and this is how the magic of chemistry happens. CO2 interact with like calcium cations, and they form calcite. Rock. So we have some samples here. We also have some nice experiments. We talk about visualization, right? So, so we have a sand pack where we mimic the subsurface layering. So different formation, different layers, and we inject CO2 from. Like we mimic the injection well, we inject CO2, and we show you how CO2 actually get percolated and flow on the subsurface, and how it get entrapped in the reservoir. So we have the system here, and we have also the video that was taken for that experiment. So you can see how the CO2 flows in the subsurface.
Very
so
cool.
Feel free to stop by, and for everybody here in the community, stop by and have a look. I think it's very interesting to see.
Yeah, sounds great. I'm going to check it out.
Yes.
Thank you, Hussein.
Okay,
Thanks for joining us today, and have a good week. I'll see you at your booth.
Yes, see you. Thank
you. Welcome back, everyone. I now have Hussein Hotite with us today.
afraid. Welcome back to the auditorium. Welcome to the last talk of this afternoon session. I will leave the stage now to Professor Mohamed El Hosseini.
I'm honored and excited to introduce today a very special guest to me and one of the most talented research lead I have worked with at Facebook. Manohar Valluri is a research director at Meta and leads an organization focusing on perception and robotics effort in AI research. His team is part of the AI research organization pushing the frontiers of AI and helping create breakthroughs moments in perception and robotics. Prior to his current role, Manohar was leading the applied computer vision and augmented reality teams, serving image and video understanding capabilities for hundreds of products across all of Meta families of apps, serving billions of people every day. His interests lie in pushing the frontiers of computer vision, conversational AI, multimodal reasoning, and before Meta, Manohar was pursuing his PhD at Georgia Tech and working at Google Research, IBM, Watson Labs, and Sarnoff Corporation, now called SRI. Without further ado, a lot of people are excited to hear from you today. Manohar, the stage is yours, and Manohar will talk about computer vision at Meta.
Thank you, Mohammed, and thank you everyone for tuning in. Hopefully, the setup is good and everybody can hear me. I know I'm in between a movie night and the rest of the day, and it's been a long day for all of you. And I wish I was there in person, but because of COVID and other travel circumstances, I could not. But I'm still very excited and honored to have this opportunity. I remember the research weeks in my university, and they were some of the fun moments where I learned a lot. And hopefully today, from this talk, a lot of you will learn about computer vision efforts here at Meta. And just a side note, this is the first external presentation I'm giving as Meta. Previously, whenever I give such a talk, it was always about Facebook. So it's very new to me as well. But thank you again for tuning in. Hopefully everything works. And over the next 40-45 minutes, I'll try to give you a whirlwind tour of some of the computer vision efforts, as well as start talking about some of the future research that we are actually doing to make metaverse a reality, and what are the breakthroughs that we need in embodied AI specifically. So with no further ado, let's get going. So actually, just to recap, Meta, which originally was Facebook, the mission for the company was to bring people closer, connecting people. So building technology that brought people together. And of course, metaverse is the most crazy incarnation of that, where you are physically in a place, but you can get to any other place, have social connections without physically transferring yourself, right? And kind of digitizing the world. But if you look at the importance of computer vision and specifically AI in this mission, the world has moved from textual interfaces to visual interfaces. Every moment that you capture today is visual in nature. Everything that you want to express today is visual in nature. So the medium of communication is becoming richer and richer. And that is why computer vision as a field is so critical in the subfield of AI, as a subfield of AI. And that is why we are investing so much in computer vision. Now, when I started in Facebook back in 2012, Facebook was a social graph. And one of the projects that I was leading was kind of making that social graph a semantic graph. So you have a bunch of people using Facebook's family of apps. At that time, Facebook Blue app. They're connecting with each other. They're adding friends. They're communicating with each other through posts. They are communicating with each other to photos and videos. So again, richer and richer. And one of the core problems that we faced then was to understand what is this conversation about, what is the photo about, what is the video about. So we can actually help build products, some of them to actually remove bad content or policy violating content from our network, but the others showing the right content, which is the feed systems, retrieving the content, which are the search systems, building accessibility features, which help visually impaired, and so on and so forth. So this basically required us to understand all of this media in a way that is scalable and in a way that is useful for many, many products. And that is the project around converting social graph to the semantic graph, where you understand this content, provide the metadata, and once the metadata is available, any product can actually take it and go with it. So while I was working on this project in 2012, I don't know how many of you are familiar. This is an AI day in the research week, so probably by now you are. Back in 2012, there was this big revolution around deep learning models. And especially in computer vision, or at least it started in computer vision, where we started using these deep networks that are hierarchical in nature, many, many layers. And fast forward a few years, deep residual networks started becoming a thing and started beating bunch of benchmarks. The bottleneck though was you had to train a network for a particular task. And if you change the task, you typically have to train another network. And if this was a 1 minute or a 5 minute or a 1 hour job, it would not have been a problem. But each of these training these networks at large scale took days or weeks and sometimes even months. So one of the questions we asked ourselves was, how do we actually bring that down? So the observation that we had at that time was, when you take apart this network, there are a bunch of layers, and the layers below were very general and could be used for various tasks. And the layer closer to the tasks above are fine-tuned for a particular task. And this simple intuition actually allowed us to build systems where we would fine-tune the top layers for each task, which would take minutes, but we would preserve the bottom layers irrespective of the task because they are task agnostic. This actually allowed us to push new computer vision models to various product groups within minutes instead of waiting for days or weeks. So that is how we were able to, as part of my applied computer vision hat and building that organization, which I'm really proud Mohammed was also part of at some point, we really were able to supercharge many, many product experiences that use computer vision models, whether it's enforcing policies, helping newsfeed, helping ads, creating moments, creating experiences like on this day, where we understood particular moment to be more nostalgic than the other, and so on and so forth. So we added all of these branches on the top within minutes to basically power a new product experience without having to retrain the network, which takes weeks or months. So the progress in image understanding at the time was astounding. And for folks who are not in computer vision, image understanding is quite general and subjective. So you can kind of break it down into multiple components. So if you take a photo or an image, classification is actually telling what is in the photo. Detection is drawing bounding boxes or doing detection of the regions where the particular object is. Semantic segmentation is giving a label for each pixel, and that label also carries information of the class that it belongs to, whether it's a man or a dog or a sheep or a grass and so on. And instance segmentation is basically segmenting a particular instance. So if you have multiple instances of the same thing, the instance segmentation algorithm will know this is instance 1, instance 2, instance 3, and so on. In this case, the 5 sheep. And attributes are basically going into more fine-grained understanding of not only saying this is a man, this is a person wearing a hat, they're standing or they're running. And then you can keep on increasing the vocabulary, increasing the understanding by bringing in relationships, going even more fine-grained, where you're not just saying it's a bird, but saying what type of a bird it is, what kind of a beak it has, what color, and so on and so forth. And even go to subjective things like aesthetics. Is this photo more beautiful than another photo? Is this photo more, is better focused, and so on and so forth. So the progress in image understanding was astounding. And one of the things we did in Facebook AI was push these models to basically power such experiences, where we went from basic classification to detection and segmentation and human pose estimation, as well as start segmenting every pixel, including the background, the stuff, sky, and so on and so forth. So that's what we had back in 2019, 2020. And to do this, and this is a little bit more technical, but I wanted to at least give you a flavor of what happens in the background. To do this, we had to actually add new heads. Remember this deep residual network with a bunch of heads? We had to actually add new heads for each of these tasks. So we had an instance segmentation head and we had a semantic segmentation head. And both of them were working in conjunction to basically segment every pixel that is in a photo. And once you have such experiences, you can really build powerful capabilities, powerful product experiences at scale, whether it's understanding concepts at thousands of vocabulary in a particular photo or video, understanding people, recognizing people, or recognizing text and trying to translate them, or trying to actually extract the text so you can actually handle text in a way that is similar to other objects. And text and people are the most frequently occurring ones, so you need to pay special attention. And the models that we have are more dedicated to those entities. So there's an example of a video so where we actually use this technology, and one of the proudest moments, because we actually won the FTC award. And this is basically taking research from lab to production and to real users at scale, where when you're browsing Facebook, if you're not visually impaired, the experience is kind of seamless, especially when there are so many photos and videos. But if you're actually visually impaired, think about their experience, because a lot of it is visual. They kind of don't know what is going on. So what we used is the technology. I know the audio is off, that's intentional. What we use is a technology where we would actually take these classes and tell the user, this is a photo of a beach with 2 people, and one of the person is wearing sunglasses and they're smiling, and so on and so forth. Or this is a photo of pizza, and in this case, I'm having it for dinner. So basically, this is really giving accessibility experiences, bringing them to life, which otherwise without this technology would not be possible. And it's helping millions of people today across the world. So this is one such example. So as I said, I want to give you a whirlwind tour of computer vision and get into the embodied AI aspects, which is looking into the future of metaverse. One of the things we noticed as we were building the systems was not just about accuracy or efficiency and latency. It was this really big bottleneck of supervision. And if you're in AI, working in AI, one of the things that is not so natural is you have to spend a significant amount of energy to train these models. And that a significant amount of energy or resources comes in the form of annotation, where you basically take a photo or a video or text and you annotate what is in that or what specifically you want the model to learn. And that's supervision. And manual supervision and fully supervised is basically you're annotating every photo with every detail or every entity with every detail so that the algorithm can actually learn. And you have to do this at thousands or millions of scale, not like human learning where you kind of do it at instance level a few times and the human starts generalizing quickly. Of course, babies take longer, but as babies grow and they learn, they start piecing together things, and they don't need that kind of supervision. So what you see here is this push by the community to go from fully supervised to self-supervised. And in between are weakly supervised and semi-supervised. So very quickly, weakly supervised is basically you don't necessarily give full accurate labels, but you do give some labels. And sometimes those labels have noise, and that's why they're weakly supervised. And the job of the algorithm is to learn from it and discard the noise and extract the signal. And semi-supervised is you have a plethora of data, and you basically take part of the data and you have annotations for the data, but the rest of the data you don't have annotations, but it's still useful as raw data. And self-supervised is the holy grail, where you just have the raw data, you don't have any supervision or annotations. The structure of the data itself is used to learn these models, or to learn the to basically train these models and fine-tune for a particular task. This is important because once you start getting into self-supervised, you can start increasing the funnel. And this was a really big bet for us, because when you are in fully supervised, you're limited in scale. But when you're in weakly supervised, you can start expanding the funnel, and in semi-supervised, even expand even further. And self-supervised, you really can use entirety of its data, which kind of allows you to build better models. So for good or for worse, the AI models of these days are hungry for data, and you need lots of data to train these models, but you don't have lots of supervision or annotations. So one such project that I'm really proud of is we noticed that we have in Instagram specifically, we have a lot of the photos that come to the network that have hashtags, and hopefully many of you or all of you have used it. And these hashtags are weak supervision. So many times these hashtags contain valuable information. So one of the intuitions we had was, can we leverage these hashtags to train a model? But remember, these hashtags are very noisy. So they can come, and especially at a billion scale, they can come in many forms. The noise and the difficulty comes in many forms. So in fully supervised, you have all of the nice data that you need to train the model, but in unsupervised or self-supervised, you don't have. In weakly supervised, which is the hashtags, you have sentences, you have hashtags that might be correct, that might be wrong. So in this case, you might have a hashtag cat, which is correct, but you have non-visual labels, love, for example, which is one of the most frequently used hashtags. It's not useful to train a model because visually there is no representation for love. Of course, we as humans can understand what it means. And there are obviously missing labels, because when you actually add hashtags, your job is not to enumerate everything that is in the photo. And of course, there's also noisy labels where many people just put breeds of certain dogs, even though the dog is not of that breed, or this particular hashtag doesn't even exist in the photo. So what we did in this particular research effort is we took billions of such photos with billions of hashtags, and we trained a model for months. And this was the largest, to our knowledge at that time, weakly supervised training that we did, where we used billions of images, humongous models with hundreds of billions of parameters and thousands of labels. So typically, when you have the vocabulary of the model, it's in the order of a few hundreds or 1,000. But in this case, we went to 20-odd thousand. And we used distributed training, because if you did it on one GPU, it would take you almost a year to train. And by doing this, and we used a lot of research that was done already. ImageNet in 1 hour is one such research where we were able to train in parallel using data parallelism and model parallelism. And we were able to get state-of-the-art results that were significantly better than what other models. And the important bit here is these models were trained in a weakly supervised manner. That means the annotations were not perfect, whereas the best numbers that were there on ImageNet at that time were actually trained in fully supervised way. So you had two big wins. One, where you had a better accurate system, and second, where you were not relying on fully supervised data, you were relying on weakly supervised data. And you get very fine-grained information of a photo, which was not possible before, because you have an expanded vocabulary. And you take these models and you put them for various tasks. So in this case, we are using it for describing a photo. The model that we put together described the photos in a much more richer way than the previous models. And we actually made these models available for anybody to use. They're called weakly supervised learning models, WSL. They are available in PyTorch for you, and you can actually fine tune them for, excuse me, for your task. So can you actually take this for videos? Absolutely. One of the nice things about video is it has a lot more data, but one of the most important problems in video is to identify the important moment. So if you treat video as a bunch of frames and sample the frames, you might actually miss an important moment. So in this case, the thing that happened between those two frames was the dunk. And if you know basketball, then you know that actually the act of dunking is the most important one, not what happened before or after necessarily. So when you are actually working on video understanding, you need to really carry all of the temporal information when you're building the model. And right now, to take that multiple minutes or hours of temporal information and spatial information and compress it together into this video understanding models, it's a big challenge for us. So what we have done historically is kept pushing on the spatio-temporal visual modeling, where we started from C3D back in 2014, almost 7 years before, and kept improving the accuracy. What you see here is a plot of how we improve the accuracy, but more importantly, also efficiency. Remember, any of the models that we build, we have to run it at billion scale. So any efficiency we get is critical for us to be able to run the model and actually use it for various products. So over the last few years, we actually kept pushing on efficiency and accuracy. And we applied the same weakly supervised learning techniques that we used for photos, even for video. And we found that it actually translated the observations we had, and the value of this weakly supervised information was useful in training better video models as well. And here, one of the interesting challenges we had in video was this long tail, because video has objects, scenes, actions, and combinations of them. Understanding the video meant we actually had to scale up. Even though the 65 million sounds less than billion, remember, a video contains thousands of frames. So honestly, 65 million is starting to become around 6 billion or 60 billion. So it's one of the most largest scale video training that we know of. And we actually trained on a large number of videos, large number of GPUs to get state of the art even in video understanding. I'm going to skip a particular number here. The entire message here is to basically be able to scale video understanding models to get state of the art accuracy on video benchmarks. And the good news here is there is no difference between images and videos with respect to weakly supervised learning. You could apply the same techniques that we had. Of course, the models that we used for videos were different compared to what we had in image models. So fast forward today, this is where I want to kind of wrap up the old way of passive perception, where you get the raw data like photos and videos, and you actually build models and run them on the cloud so they process and understand. As I mentioned, the best way to increase funnel, where you leverage all of the data, is to move towards self-supervised learning. And there's some really interesting self-supervised learning. This is one of the hottest aspects of learning and computer vision, and even in general, broader core learning, which applies to language and audio, is self-supervised learning, where you actually use the raw data. And just to give you a flavor of what self-supervised learning and why it is so exciting is, in fully supervised learning, you basically get your data, you label it, and you train a model for a particular task, right? In self-supervised learning, you get a lot of unlabeled data, typically orders of magnitude more than fully supervised, because you don't have to annotate. You just take the raw data and you do what we call this pre-training, and you train a much larger model. Because you have a lot of data, you can train a much larger model on a pre-task. So just give you a little bit more information on what pre-training and pre-tasks are. In case, let's take the example of a text. So if you have a sentence, the nice thing is the sentence has a structure, the grammar. And when I make a sentence, when we all write or speak sentences, you have an implicit understanding of how English works or how your language works. And you use that structure and you use the words in the right way. That structure is actually useful to train models, language models. So what we do in the pre-task here and the pre-training here is to take the sentence and you mask the word. You basically take away a word and you force the model to train, fill in the blanks. You basically say, hey, fill in this blank. What word will be here? And because you know what word existed, you can actually correct the model if it predicts wrong. So this is called pre-training. And this particular task is pre-task in text, for example. You can have the same thing in images. You could basically mask out an image and you say, predict the pixels in this region. You can have the same thing in speech. You mask out a particular part of the waveform and you say, predict the audio here. And in all of these tasks, you have the raw data. So you can actually learn the model, train the model using raw data without any annotations. And this gets even more exciting when you come into multimodal data like video, where you have audio, text, and images. And you can even come up with very creative tasks across all of these modalities. So in case of video, you can say, match whether this video and audio are coming from the same entity. And you basically mix and match the video and audios. And by doing this, you're forcing the model to learn the natural structure of the data. And what is the use for it? I mean, these tasks are not necessarily meaningful, right? You, at the end of the day, want to take this language task and use it for another other product experience. So what we could do is, once you have trained this at scale, that's a self-supervised model that you have. You now take this very small amounts of label data, which you would typically use for a fully supervised model, and you fine tune it. So you basically fine tune the model, the self-supervised learning model, for your particular task. The beauty is, for fine tuning, you don't need that much data. And when you fine tune, you carry all of the structure that you already had when you train the self-supervised learning model. So you can now fine tune it for another task. If you have a new task, you can take the same self-supervised learning model, you take the new label data, and you can fine tune for another task, and so on, and so on, and so on. And the beauty is, once you start fine tuning for many tasks, you can actually expand these capabilities of the self-supervised learning model to basically do multitask learning. And that is where the current field is, and the current industry is, where people don't necessarily use fully supervised learning models, because self-supervised learning models with fine tuning give you the best results. So I wanted to, for people who are more technical and deeper into this, this area, I wanted to flash two works that I think are very relevant for people to know. One of them is bringing in transformer architectures. So as I mentioned, the architectures that we have in deep learning and vision have transformed over times, have changed over time. They started with very basic convolutional networks, then went into residual networks, then went into, now we are in a world where both residual networks and transformer models are kind of head to head. In some cases, some work, transformer architectures work better and residual networks work better. So we'll see over time what happens. But it'll be very good for people who are in this area to know about both self-supervised learning, which is the way how you train these models, but also know about the architectures that you use to train these models. And this particular one is kind of touching on transformer architecture. And the second work is from Jan and team on Barlow twins, basically trying to do better contrastive learning by making some assumptions on the underlying distribution being more Gaussian and so on and so forth. But again, I really don't want to go into the deep technical details here. I felt it was important for people to be working in this area to know about the latest works, and these two are the latest works. So, as I mentioned, I really want to make sure I talk more about the future rather than delve too much in the past. And but it's really important to know what we did in the past, what models we built, where the computer vision field is heading, and over the next few years, I think there'll be a lot of exciting things that will happen in both self-supervised learning, large-scale learning, multitask learning, in video understanding. There'll be a lot of new product experiences built. But getting back to the vision of Meta, we really believe that the evolution of computing is something that has kind of stagnated over the past 2 decades, right? In the sense that after the mobile phone revolution happened, we are kind of in the mobile era where the phones are becoming stronger, more sensors, more capabilities. But there is, the question for all of us is, what is evolution of mobile computing? And that is where metaverse comes in, where you will actually start having more wearables, and these wearables, along with the mobile compute and compute on the go, will become a lot more of mainstream and a reality. And more importantly, thinking of browsing the internet on your phones, change your perspective to thinking of living in the internet, or basically as you're doing your daily activities, as you're actually let's say commuting or working from home or working from office or in meetings, you really have information at your grasp. You really have sensors and variables that are actually guiding you and assisting you. In that embodied world where you are the agent, and the glasses or other variables are the sensors and the computing platform, you really need to start pushing the frontiers of embodied AI. And two specific works that I want to touch on is one in 3D perception, and the other one is in egocentric perception. So the 3D perception, so if you have worked in computer vision, COCO, which is common objects in context, has been one of the most revolutionary benchmarks. And before COCO, it was ImageNet. And before ImageNet, it was Pascal, VOC, Caltech 101 and Caltech 10, and then going back in the beginning was MNIST. So the evolution of all of these data sets really supercharged progress in computer vision, all the way from MNIST to Caltech 10 to 101 to Pascal and to ImageNet and then COCO. One thing that we found was the 3D perception lacked such constructed data sets. So we proposed Co3D, which actually even won an award recently, common objects in 3D. So give you context on what Co3D is. It's basically the problem that we are trying to solve is how do you digitize the world where you can start bringing real world 2D instances of things into full 3D reconstructed version of it. So we can actually see it from any angle, experience it in AR, experience it in VR. So the core problem we are trying to solve is 3D shape from 2D images. And if you have multiple 2D images, you can actually reconstruct the 3D shape. This is a well-known phenomena. Multi-view geometry has been studied very well. Using deep learning is obviously a new way to do it. And the value of doing this is humongous. You can obviously, if any of you have tried Pokemon Go or tried HoloLens or tried any of the 3D experiences, whether it's Gear VR or Daydream from Google, just augmented reality is a really powerful application where you supercharge not just going from text to visual, but from visual to 3D and 3D to in real world, where you're mixing realities, where the physical world along with augmented world are giving you much more richer ways of experiencing things. So augmented reality, automating 3D for graphics, so you can actually start rendering things in a viewpoint that you want, in colors that you want, in textures that you want, and obviously even virtual try-ons, which is one of the most important problems, especially during COVID, where you're sitting at home and you want to buy certain things. It's very hard to visualize how it will look, and you can actually, using this technology, make it happen. So learning 3D object categories is actually a very hard problem. And so you can make this problem easy or hard, depending on how you pose it. So for example, if you have many views, you can actually do a good job in 3D reconstruction. If you have few views, you can do a decent job in 3D reconstruction. So this is where the real research is. It's like, how do you actually take few of these views and create 3D? And if you take a plot of various efforts, of course, we are not the first ones to build data sets in the space or think about the space. There's a lot of awesome work that has already happened. And if you map that work, some of them fall in like fully supervised, less difficult, or some of them fall in less supervision, more difficult. So for example, if you take synthetic data like ShapeNet and all of these related things, you have full annotations because it's synthetic, right? Once it's synthetic, you can render it in any way, any form, and propagate the labels in the way you want. And you can scale it. You can create as many views as you want. But the challenge is the domain shift. From the synthetic data to the real data, there's a significant domain gap. So how do you actually counter that? And then on the flip side, the ones that is very, very difficult, but is real, is from a single image, you want to reconstruct the photo, reconstruct the volume, the 3D volume. How do you do that? And that's very difficult, but you don't have much supervision. You have very less supervision. You basically just give a high-level structure of the bird or the car or a chair, and the model has to adapt to new instances. So the in-between is a very big area where we can actually make meaningful progress without having to go to the extremes. And that is where Co3D comes in, where what we are basically saying is it's real data, but you don't need to confine it to very less supervision and make it super difficult. You can actually create data set of common objects with multiple views in a controlled environment. So you can actually train models on real data. So you don't have to do domain adaptation, but you also have multiple views so you can train better models. And this sweet spot actually allowed us, so this particular video is a very illustrative way of telling what is it that we're doing. So what you do is just capture a video with multiple, like it's turnstile like video of common objects, and using those multiple views, you do structure from motion, and you triangulate the camera point as well as the individual point clouds points on the object, and you reconstruct both of them to get you the full 3D structure of that object. And this is done at scale of daily objects. So now you can start thinking about common objects in your life, getting them into 3D, so you can start actually experiencing them in AR or in any other application that makes sense. This is not done for at this scale before, especially for common objects. They were done for specific domains like chairs and furniture and so on and so forth. So what this particular project is trying to do is collect turntable-like videos of objects, and then we ask the Turkers on Amazon, Amazon Mechanical Turk, to actually do this for us, where they put common objects and they take videos which are like turntable, and we pass them through structure from motion and reconstruct the camera viewpoints as well as the object point clouds to get the full 3D. And as you see, for any natural distribution of things, there's a long tail. So you have a lot of frequently occurring things that are common, and there are a few instances of rarely occurring things, but we wanted to tackle all of them. So what you see here is example collected videos of the teddy bear, cup, bench, fire hydrant. And just to give you a more qualitative comparison between various data sets, there's a number of category scale, number of object scale, and it's real life. And you basically, with this data set, you get the point clouds of the full object as well as the camera positions that you can use for your learning algorithms. So I'll move on to why this is useful. So when you actually start doing the camera tracking, I'll fast forward this. So this is example camera tracking of the object, where you actually, for each video frame, you know the camera position, you know the point cloud of the object. This is for various objects. This particular algorithm doesn't know what the object is. It's just doing structure from motion. So it's agnostic of what it's looking at. It's just trying to triangulate the camera as well as get the point cloud information. So the important bit is common objects in 3D is actually publicly released. So if you're doing research in 3D perception, this is one of the data sets that you can leverage. It has much larger vocabulary. It has much larger number of objects and videos. And the most important bit is when you actually introduce a new data set, it's the beginning of the research. Then you start formulating the problems around it. So in this particular one of the problem formulation is reconstructing independent objects. So you get a video of a single instance, and you need to be able to reconstruct that instance. So in this case, fire hydrant. So in some senses, overfitting, because what you are doing in learning is trying to understand the high-level structure of that object. So when you see a new instance of it, you kind of rememorize, bring back from your memory, from the network, that, oh, I think I know a rough structure of a fire hydrant. I'm going to use that. Plus, I'm going to use the new views of this particular fire hydrant and put that together to get you the 3D reconstruction of this particular fire hydrant. The second task is you actually learn the 3D reconstruction of a particular object. So you basically say, here are 1,000 videos of apples. Of course, each one of these apples is a different instance, but your job is to learn the common apple structure and apply it, so I can do 3D reconstruction of each one of these video. So instead of doing it, the input here is not single apple video. The input here is multiple apple videos, and the output is 3D reconstruction of each individual video specific to that instance. It's a little bit different to task one. And then the third one is you basically do few view reconstruction. So you have learned the model of fire hydrants, and you get, instead of a video, like subset of views, like 3 or 4 or 10 in this case, and your job is to do 3D reconstruction. So all of these 3 tasks, and there are many more tasks that we can obviously create now that we have the data set and we have the annotations. That's where the real learning algorithm starts. So this is an example of how we are trying to push 3D perception in embodied AI and in general 3D perception, so we can bring a lot more real world objects and real world instances into AR, into 3D. So we can reuse them, we can digitize them, we can actually render them in ways that are new, whether it's changing the lighting, changing the texture, changing the size, duplicating them, and so on and so forth. So the second part of embodied AI that I want to talk on and kind of end this talk, so I can take more questions. I can take questions is in Ego 4D. So one of the things that we noticed is when you do vision, there is a difference between doing passive vision and active vision, but also there's a difference in doing third-person vision and egocentric vision. In egocentric vision, the camera is at the eye level of your eye, and what the camera is seeing is kind of very, very similar or analogous to what you are seeing as an actor or what the robot is seeing as an actor. And that's where Ego 4D comes. And I know there are a bunch of names here. Co3D is common objects in 3D. Ego 4D stands for egocentric vision in 4 dimensions, which is space and time. So 3D plus time. And this is a large team of almost, I think, close to 70, 80 researchers that have been working over the past 2.5 years to push egocentric perception across many universities and industries where we have students and people working in Facebook. And what the problem is, what we're trying to tackle here is first-person perception. So the status quo right now is more from disembodied photos or web photos. It's like you take a bunch of photos from your phone or from third-person view and kind of share them on social networks or on the web. And the learning algorithms are trying to understand the world from that perspective. Whereas what we are trying to do in egocentric perception is you're really trying to learn the world from the viewpoint of the user or of the robot or of the embodied agent. So if it could be the camera on a car, for example, how is the car seeing the world? And so the models are actually seeing the world in the same way as the car or as you as the robot. So that's why it's embodied AI. And egocentric video versus third-person video has some really interesting property differences. So what in egocentric video, you know what the person or the agent is focusing on. You know, there is a lot of jitter, there's a lot of movement, there is field of view changes and occlusions, a lot more than in third-person view, which are a lot more smoother and not as natural from an agent understanding point of view. Why? Hopefully by now this is evident, but if you start building better models for egocentric vision, then you can actually start making the variables that are at your eye level much more richer and much more capable. So they are also seeing the world in the way you are looking at. And this can be also useful for robotics, not just for AR. And it's, again, this particular space is not like completely new or radical. People have been working in egocentric perception for a while, but the problem has been about scale and diversity. So what we did with Ego 4D is really trying to tackle the scale, which is the number of hours of video, and trying to tackle the diversity where the video data is coming from multiple people across the world. So you put those two together, and the North Star for Ego 4D is scale and diversity of egocentric data. And this was not easy to achieve because it's not natural for people to actually go where variables and record video. So we had to obviously make sure we were doing everything with respect to privacy, everything with respect to how people actually what is their day-to-day life, and capture the day-to-day life moments rather than a particular subset of moments. So we are really proud to have almost 3,000 plus hours of data. We partnered with multiple universities across the world to make sure that we have a good representation of, and obviously we are still expanding this. We are still trying to get to more countries and more universities and more partners so we can actually have even more diverse representation of the world. And the most important thing when we were doing this was to try and have daily life scenarios rather than specific scenarios. So it included unscripted daily life activity rather than scripted, where you go into a particular environment and capture. And it also included using various kinds of sensors, various kinds of data capture, data acquisition devices, rather than a singular mono device of the same thing. And we went through rigorous privacy and ethics questions, is like blurring the faces, blurring the audio, license plates, text information, anything that is sensitive. So we make sure that when we are doing this, we are doing it with in a way that doesn't encroach on people's privacy, while also pushing the research forward. Without such a data set, it's extremely hard to build best egocentric models. So this is an example scale. This is a scale of what we were able to collect: almost 3,000 plus hours, 900 plus people, 1,400 hours of audio, 80 different real world scenarios, 100 to 300 common objects and actions, very good geographic diversity, very good occupational diversity. A lot of people who were capturing were students, sports people, and so on and so forth. And they are all unscripted. So they're not trying to follow a script. They're actually doing their daily life activity. This is an example. So let me play this so you have a sense of what first person video actually looks like. This is a person driving their motorcycle, probably on a way to commute. I don't necessarily know which country this is. Maybe it's a good classifier that you can build. This is somebody going and working in their lab. So again, as you see, one of the nice things here is the video contains hand-eye coordination, clear focus of what the person is trying to do, what is the activity they're trying to achieve, a goal they're trying to achieve, or the activity that they're doing, various objects that they're interacting with, their focus at a particular instance, their gaze, and so on and so forth. So this is somebody shopping, groceries, and so on. Like again, I'll do a fast forward. In some subset of this video, we actually have 3D scans, which is fantastic. So that's another sub part of the research problem. In some cases, we have the eye gaze. So we specifically know where the user is looking. So we can actually start training models to do autofocus. And then this is the first public release of Ego 4D at this scale that we know of, which unscripted data, and any researcher can actually leverage this. So there are a bunch of challenges that we are actually hosting. It's called benchmark tasks. One of them is episodic memory. So this is something that I want to spend at least a couple of minutes talking about this. So once we have this raw data collected at scale, and we can train, and we are actually annotating these data sets for people to use, we can start training models and powering experiences. So for example, how often have you had this instance where you're like, where did I forget my keys? Where did I forget my wallet or my backpack, and so on and so forth? Or which is my coffee cup, if there are multiple coffee cups that people are drinking. And in episodic memory, you can actually start answering such questions. You kind of remember where you left a particular thing. In hands and objects, you kind of start building models. It's like, what is the activity that the person is doing? What objects are they interacting with? What are changing the state of the object? In forecasting, you basically start predicting into the future. 5 seconds from now, they will add salt, or they will take a left turn, and so on and so forth. And then for audio video diarization, you are really trying to do conversational AI, where you're trying to understand who is speaking what, when. So you can say, take reminders on meeting notes, or reminders for yourself saying, hey, you were going to wish this person, or you had to wish this person, or you had to call them back, and so on and so forth. And then social is, how are we interacting? Is a particular person paying attention? Let's say whether it's in a classroom or whether it's a meeting, and kind of guide the speaker or guide the individuals. So the interactions become much more richer and more fruitful. So these are some example benchmarks. Each one of these is trying to get at the problem of, so in case of episodic memory, it's around places. In case of hands, objects forecasting, it's about objects. And in case of social and audio visual diarization, it's about people. I mean, basically, I already explained the task, so we don't necessarily need to go into it. In episodic memory, the richest way one could think of is for the system to basically give you a 3D view of where the object was and guide you there. So you have, by basically augmenting your memory when you wear these glasses, or when you wear this, when you have these new capabilities, and you know very clearly where in the room the keys were, or where you put the wallet. And in hands and objects, you really are recognizing, oh, I'm opening the lid, I am actually mixing the batter, and so on and so forth. So you can actually guide the user to say, you need to do this faster, you already added salt, don't add it again, and so on and so forth. Forecasting is basically anticipating the movements. So here you can basically say, hey, you need to do this at this point to get this recipe right, or you forgot to switch off, close the garage door, or switch off the stove, and so on and so forth. So you really have to kind of see what the model predicts and what you're doing, and if there is a mismatch, kind of flag the anomaly to the user. And in audiovisual, like I said, you can actually take meeting notes and get back, or have contextual reminders for people. So all of this, this is not future. This is basically the present. The data set is released. We are actually, you can see the license and you can use it for research purposes. We are actually hosting a challenge next year where people can participate in the conference and in the workshop and see where we are on the models. Right now, the models are actually at a very low accuracy, so we have a lot of work to do over the next few years. The reason I kind of touched on Co3D and Ego4D is those are the efforts that are really pushing us forward into the metaverse, which is where Meta is going, and which is where I think a lot of cool research can be done. With that, happy to take any questions. Hopefully this was useful and entertaining, especially given that I'm between a movie and a long day. Thank you for listening to me, and thank you for having me.
Thank you, Manar, for the exciting talk. Now it's time to have questions. Anyone who have questions, you can please come up to the microphone and please feel free to ask your question. In the meantime, I have a question for you. It seems that we have a very, I would say, organized plan to get to the metaverse. So, Co3D, is that a way to bring real object to the metaverse, or how would you, what are your thoughts on that? Right.
No, it's, I mean, it's a great question, Mohammed. And yes, one of the big pushes is, this is a prediction, okay? And it's a little bit superlative, but I think this prediction will be true, I don't know, at some point in future, hopefully sooner than later. I think once we start having augmented reality capabilities, there will be a time where there'll be more virtual objects in your field of view than real. And I do believe that such a future is not too far. And it actually allows us to have even more richer way of experiencing the world and a richer way of doing something. That might not be the case all the time, but there will be scenarios or instances where there will be a lot more virtual objects in our field of view. And to make that a reality, you need to digitize, you need to bring a lot of real world objects, real world experiences in full 3D into metaverse, right? Into this augmented world. And Co3D is a way for us to accelerate that future.
Oh, we have a question. Please start by saying your name.
Yes, so my name is Ruben Costa, and I have a question more regarding the topic of the Research Open Week, which is sustainability. So I can see a lot of applications for the metaverse in terms of entertainment and the social aspect. In terms of sustainability, can you talk about the type of things we can do, the actions we can do in the metaverse, like simulations and things that can be accomplished in such a platform in order to advance both socially, economically, and environmentally our development? Thank you.
No, thank you for the question. It's a great question. I mean, one of the things that we should, COVID specifically has been pretty harsh for a lot of people and even for the world, but one big realization for us is that we could do this without me, sorry to say this, but without me putting a lot of carbon footprint by taking a flight, being there in person, if it's a possibility, right? So so when we think about metaverse, we really think about various verticals like fitness, entertainment, education, work, home, and so on and so forth. And in every aspect of it, I don't think we should ever replace physical interactions completely. That is absolutely something that we thrive as humans. But at the same time, we should really be mindful of when we should actually have that carbon footprint and go visit a particular place or visit a particular person or do a certain thing in the physical world versus when we can actually try to minimize that carbon footprint, try to minimize a plundering of the environment as much as possible, and try to be more digitized. And this is one angle. The question, so once we did that, let's say, that can be a lot more sustainable future where I can actually interact with folks, give such talks, or attend many talks like that without causing a significant churn for the environment. But on the flip side, the question is, hey, is this optimal, what we are doing right now? It's like, to do this, are we actually spending a lot of energy? It turns out that you actually, the entire usage of, let's say, Facebook, or replace Facebook with any other online platform that you might want to use, for a year is equivalent to one Starbucks coffee. Think about it for a minute. So if you didn't have, if you just use such a conferencing system your entire year, it's equivalent for you to go and have a cup of coffee, drive, get a coffee and come back. So this mode of communication, when possible, is kind of very efficient and could be leading to a very sustainable world. So I am for, so what I'm trying to say is the answer for your question, which is a very important question, is metaverse does allow us to choose in what way we want to interact, when. Without that future, we are confined to suboptimal tools where I would rather be there in person and have this conversation when possible, maybe always, which was the history that we were in, which was a period that we were in before COVID. When COVID actually convinced people we can do a lot of things without having to be physically away from family in various places and so on. Having said that, I still wished I was there in person. There are some important moments and important key things that we should always try to strive, whether it's social interactions with loved ones or an important conversation that we need to have and so on and so forth. So you need to strike that balance. And I think this future of metaverse does allow us to strike that balance. Hopefully that answers your question. Sorry, it was a long answer, but it was a complicated way to explain. Thank you.
Right, next question.
Hi, this is Ahmed Dawood from the Royal Commission for Al-Ula. Thank you for an extremely engaging talk. A few questions.
For some reason, I'm not able to hear. I'm sorry.
We had this problem.
Mohammed, maybe can you repeat the question, or?
We have a funny cube microphone here that gets passed around. So, can you hear me any better now?
Yes, I can hear you better. Thank you.
Fantastic. So again, my name is Ahmed Dawood, and I'm Director of Innovation for the Royal Commission for Al-Ula here in Saudi Arabia. A couple of questions that I had, on the note of sustainability. While a Zoom conference in itself is definitely more energy efficient than a flight to go meet a client, a partner, what have you. When you look at the aggregate compute power needed to power this, when you look at the compute power needed to power all the computational vision modules and the learning modules that you need, especially if you're projecting out a world where we potentially see more augmented or virtual entities than real entities in our field of view. Does now the carbon footprint look very different than a Zoom call, and what could be done to offset this? Furthermore, when we talk about this potential or impending reality, is the compute capability available on the edge now to make this a reality, or is there a gap in technology here that's not being adequately highlighted, and there are latency impediments to what you're describing as a future state based on the current technology in terms of the edge computing capacity on the end user devices?
Thank you.
Yep.
Yeah, go ahead.
Lastly, I wanted to just ask about, what are some real valuable practical applications of this, other than, being able to virtually interact with your NFT unicorn, but, could this be used, or have you modeled scenarios where this could be used, for example, in assisted living, where, you have people with maybe cognitive degeneration, and you're able to extend their independent lifespan, so to speak, where there can be now real tangible value that would offset the arguments or the skepticism around, say, carbon footprints, going back to my first question full circle. So 3 questions, a bit broad, sorry.
No, these are great questions, and thank you for explaining and detailing the questions. So let me take it one by one. The first one, there is if you look at the current goals for many of the tech companies, whether it's companies that are providing cloud services or companies that are providing product experiences powered using their cloud, but not necessarily providing cloud services. Both of them have a very clear goal of using 100% sustainable energy for their data centers. So to me, it kind of like you need to take a very complex problem and break it down, streamline it. Once you streamline it, then you can actually go to the source and make things better and more optimal, and you have a lift the tide. Like basically, when you lift the tide, all the boats come up, right? So in this case, the answer to your first question is if this compute was run on carbon, that would be basically pushing one problem to another problem, and then you're like, okay, this is essentially it's not solving the problem at the end of the day. But whereas if you're saying that a lot of this compute and what can be done is actually done using sustainable energy, then there is one around efficiency and second around sustainability. In both cases, you have a win-win situation. And right now, the push, and in fact, if you look at all the new data centers that at least have been built by Facebook, they're all 100% sustainable energy. And I believe that is the case for majority of the big companies. I don't know off the top of my head, so don't quote me on it. So that is answer one. For answer two, you are absolutely right. I mean, that is one of the reasons why this is not a future in 1 or 2 or 5 years. This is a future potential that could take a decade or even longer. And it's an evolution, step-by-step evolution of things where there'll be a lot less compute-intensive experiences, and over time there'll be a lot more compute-intensive experiences. But going back to your question, is the edge compute enough? Absolutely not. But there are a lot of things that your phones can now do that 5 years ago we as AI researchers didn't think was possible. Whether it's running full HD ResNets or convolutional nets or things of similar sorts. So fast forward 5-10 years, you could build custom chips, custom optics, custom compute capabilities with thermal limits that can make progress towards that, where I do believe that a lot of the things can still be done on the edge. And in some cases, you might want to do some on the cloud as well, which don't require low latency, or which are okay from a privacy point of view, for example. And the last point is a very good one. I mean, as I mentioned, one of the things that we've been thinking about is how do we make sure this metaverse is useful in a way that is tangible in various verticals. I mean, if you look at VR right now, it's already been proven to a large extent on how useful it is in fitness. I don't know how many of you have tried Beat Saber or Supernatural or likes of that. It's basically you put on this headset for 15-30 minutes, you're basically doing the physical exercise. That is, at the end of the day, fun and as well as healthy, right? So if you look at the verticals, whether it's gaming, fitness, the other one is work, home, social, and so on and so forth, you can have many experiences. So health is definitely an experience that we are thinking about. But right now, the focus is actually to build the technology, to do the research to make it happen. And then once you have the computing platform, then there will be a lot of other companies as well as us trying to create specific health experiences. Like what we have done for accessibility. It's a small % of population that require it, but it will be tremendously useful. It's a game-changing thing for that small population, right? So right now it's more creating the possibility of the platform and making it even feasible. Then there will be a lot more applications that will be built by not just Facebook or Meta, by many, many companies. Hopefully that answers all 3 questions quickly. Sorry, it was a long question, so I had to give a long answer.
Yeah. Thanks, man. Next question.
Yeah, thank you, Munahir, for this great talk. I'm Abdullah Hamdi from Bernard Ghanim Group. We're actually part of the our group is part of the EGO4D project, contributed to that. So my question regarding the metaverse, like what is the ultimate goal? From my perspective, I don't think it can be to make us connected, since we are lonelier than ever with all of the social media platforms. But from the way I see it, it's a great future where it can create purpose for people. When the AI will take over all of the jobs in the world, we need another, I don't know, call it a purpose creation machine. And metaverse can be that, purpose creation for so many people to live meaningful life. Now, the other thing which I think is great from the metaverse is the type of the data that it can create. Imagine all of the people doing all of their work and living inside the metaverse. The type of the data in 3D that is generated is completely different from what we have seen so far. What are the applications or possible applications of this data? Like, is it psychology analysis? Is it, I don't know, treatment? Or is it something else? Like, other than creating purpose for people in the metaverse, what are the uses of the tremendous data that can be generated from the metaverse?
Yeah, so thank you for all the contributions you and your team has done for Ego4D in supercharging egocentric perception. That was, our collaborations are what makes this project a big success for us, and it's the beginning of the journey. To answer your second question, probably. So the first question is actually simple. I don't think we all have an answer. And I think each company or each person has a different definition of metaverse, which kind of makes me excited about it, because you now have various minds thinking about it in the way they think it should be, which is what it should always be, rather than one particular entity or one particular person saying this is the future and everybody else has to confine to that. So in that sense, it has that flexibility, and each one of us will have our own principles and that we will use to shape it in whatever we think will be useful for the world, right? But just to give a more tangible version of it, it's like the entire idea is the physical world is not disappearing, right? It's basically overlaid on the physical world. This is the most important part. And you still are going to be connected to the physical world in a big way. It's basically how you transform the physical world along with that augmented world that actually makes your life more richer, more experiences more richer, have information at your fingertips, have your social connections at your fingertips, no matter where they are in the world. It gives you superhuman capabilities, whether it's superhuman memory, superhuman perception, superhuman audio, and so on and so forth, right? Just want to make sure that is coming across, and that is something that we should be very mindful of. For the second one, I honestly think right now the problem, at least on the research side that we are thinking about, is how do we think about the next computing platform? It should not be a screen in your hands, a smaller screen, a better screen, more screens, and so on. It should be really, you are in control, you're seeing what you're seeing, you are hearing what you're hearing, but you want to augment it in a way that you want. The control is in you, with you, but the context that you want to use, where it's a more powerful assistant with you all the time, those are things that actually make a huge difference in terms of your entire experience. So honestly, from the research point of view, we're not thinking about it as collecting data for this or looking at a particular vertical or health or so on and so forth. Right now, we are really thinking about the next generation of computing platform. Is it contextual? Is it multimodal? Is it real time? Is it on the edge? So really, we think about privacy first. And is it actually useful for each one of them in their own way? Right. That's going to take a long, long time, right? It's not going to be done in a year, 5 years, 10 years even. So, but we are starting, and on the research side, we are trying to basically take these hardest problems first, whether it's thermal, latency, what models we need to build, what AI models. Right now, just tackling vision models is one. Now tackling contextual models is an even bigger conversation, right? Thinking about conversational AI models is a very, very big challenge, and so on and so forth. So that's kind of how we are thinking on the research side.
Hello, this is Riham Al-Mubarak. I have a question for you. Given the latest scandal with Cambridge Analytica and Meta, how are you trying to tackle the public perception of Meta, especially when it comes to artificial intelligence and ethics and collecting of data and build public trust, basically? Are you even tackling that?
So I'm not an expert in necessarily public relations and comms on that, but I can definitely speak on the AI research because I've been here for at least 9 years, and I know Mohammed has also been part of FAIR. We really, when we think about AI research, we really think about a few principles and values, right? If you look at whatever I have presented, they have all been research done in the open. Whatever we have built, we have pretty much like PyTorch, including PyTorch, the weekly supervised learning models, including any research that we have done. We publish in the top tier conferences. So it's not just a particular company that is benefited from it. It's basically the whole world. So they have access to the best models. They have access to all the research and knowledge that we have, even models that we have, the platforms and frameworks that we have, and so on and so forth. So when we think about AI research aspect of it, we definitely think about openness, publishing. We think about freedom for both researchers in the company as well as people who want to use the stuff that we build. We think about platforms and open sourcing them so others can actually use it. We actually think about responsibility. So when we actually are building some of these experiences, so there's no necessary business value of building accessibility. And it requires a tremendous amount of investment and compute, but we do it because we are like, even that 1 million people out of the 3 billion people that use Facebook who are visually impaired need to have the best experience possible. So we really have those basic principles. So in AI research, we really are like, what does responsible innovation mean? So we recently also announced that we are not going to be using face recognition for tagging photos or in general, because we felt the value versus the risk is significantly higher now compared to the previous instance of the world where people were a lot more open, or people are like, I want this feature. And tagging people was one of the most requested features. Now it's like, no, we would rather not have that and manually tag. Okay, we will not have face recognition. Even though we know that capability will exist or does exist, we don't want to use it. And there is a blog post and a press statement that we made on it. So really at AI Research, we are not trying to build technology or do research and say, I don't care how it impacts the world. We really are trying to be responsible from the beginning, during when we do the research, and after we do the research. And we are trying to make sure that everyone else benefits from it, not just a singular company.
All right, any more questions? Okay, let's thank the speaker. Thank you so much, Manwar.
Thank you all
for
having me, and have a good evening and a great movie night.
Okay,
rest of the week.
Okay. Right. I think actually we all enjoyed that. Maybe not many people need a movie night. We have already part of the movie night. All right. Thank you for joining us.
Take care, guys.
Right.
Thank you very much for joining this talk from in person or online. We hope to see you tomorrow at 9 for more keynote talks. Thank you very much.